Good morning and welcome everybody to the first meeting of the review of U.S. Human Spaceflight Plans Committee. Just wanted to welcome everybody. It's a very good turnout today. I'm glad you guys could join us. And to everybody that's watching on the computer and on NASA TV, we want to welcome you as well. My name is Phil McAllister. I'm the Executive Director of the committee. Just a couple quick notes. This meeting is governed by the Federal Advisory Committee Act, so this is a public meeting, obviously. All the comments today are on the record. Ask that you please silence your cell phones. It's just like the movie theaters, so that we can get through the agenda, which is very challenging today. All the presentations today will be posted on the committee's website, as well as the minutes today. The committee's website is http://hsf.nasa.gov, so please visit there. We do have copies of the agenda also that are available for anybody who wants to see it. Let's see. I will be notifying the presenters about 5 minutes before their end so that we can make sure that we get through everything. I also wanted to mention that all members of the committee have been reviewed by NASA's legal counsel. They've analyzed all potential conflicts of interest, and they've resolved any and all significant conflicts in consultation with the Office of Government Ethics. So we're in good shape there. There's going to be two public comments periods today, one right before lunch and then one right at the end of today. We're very much looking forward to that, and we're going to ask people to come to one of the two standing microphones during those periods and make your comments. If you could limit your comments to about no more than 3 minutes, that would be preferable. We'd like to get as much public comment in as possible. We'd also request that we would strongly prefer that you ask questions via the website. So if you have questions today, it'd be much better to submit those on the website so that we can answer them and they can be posted on the public's the website for all the public to see. So for today, we're predominantly looking for comments from the public for those two periods. For members of the media, we'd also like those public comment periods to be for the public. We've set aside a half hour at the end of the day today at 5 o'clock for the media, where the chair, Norm Augustine, will be made available to answer all those questions. With that, I'd like to turn it over to our chair, Norm Augustine.
Okay, thank you, Phil. Good morning, everyone. Your presence today and the interest that we've found in our assignment, I think, speaks to the care and the importance that is assigned to the topic. I would encourage you, as Phil did, to use our website. It's set up to handle a very large capacity. We've already received a lot of comments, and we look forward to more. I'm not going to take time to introduce all of my colleagues. Their names are in front of them, and you probably know many of them. Their biographies are on the website. 3 of our members had commitments prior to their knowing they were going to be doing this summer. So we are depending a lot on wiring people in by video conference and telephone conference, and that seems to work very well. We've been able to take some preparatory steps for this meeting, some administrative things we've set up. Let me quickly cover them so you'll kind of know where we are. In terms of administrative actions, have set up 4 task groups or subgroups that will be working on specific aspects of the overall charter that we've been given. We have taken steps to have the Aerospace Corporation assist our panel directly. And they will be responding to tasks that we may assign them where we'd like to get more detail and more background than we may have ourselves as the members. Today, we're just going to be able to do a snapshot overview. We'll be going into much greater depth as time goes on and through our subgroups. And as Phil said, I've asked him to kind of keep us on time as the day goes on. And so with that, the first thing I'd like to do, it's my privilege to introduce Dr. John Holdren, whom you know is the science advisor to the President and also the head of the Office of Science and Technology Policy. And it was really, I think, in large part his efforts that brought about this review. John, we'd surely welcome any comments you'd like to share with us.
Well, thank you, Norm, and I want to start by thanking you and the panel for stepping up to the challenge of conducting this assessment of the future of U.S. participation in human spaceflight. The President is grateful to you for this service. I'm grateful. NASA Acting Administrator Chris Scalise is grateful, and I'm sure the nominee for Director of NASA, General Bolden, would be grateful too if he were allowed to comment publicly on anything before his confirmation. I want to start by emphasizing, to put this in context, the importance that President Obama places on science and technology in general as keys to the country's ability to address the great challenges we face across a very wide array of issues, as you know, including the economy, health, energy, climate change, other resource and environmental issues, national and homeland security. We face a truly daunting array of challenges across these domains, and only with a major contribution from innovation driven by science, engineering, and indeed the social sciences as well, are we going to be able to meet those challenges effectively. Our capabilities in space are a very important part of that. I like to think of our capacity to meet that whole array of challenges as defined by a set of cross-cutting foundational capabilities, which include the health of our great fundamental research institutions, our research universities, national and private laboratories, the capabilities of our infrastructure, information technology, transportation, communications, energy, the capacity of our teaching institutions in science, technology, engineering, and math education from preschool to grad school and beyond. And I think of space as one of those foundational cross-cutting sets of capabilities that are essential to our ability to meet the full array of applied challenges that we face. Space, of course, is also a marvelous venue for expanding fundamental knowledge, for improving our understanding of the universe and our place in it. It's a wonderful vantage point for looking down as well as looking up, for understanding what's happening on the surface of the Earth, whether it be changes in land use, emissions of various pollutants, activities that we need to understand to monitor our arms control agreements, a huge array of important functions of looking down. Space is also, historically and in the present, a way of inspiring the next generation to take an interest in science, technology, engineering, and math. It fulfilled that function admirably during the space race, when a whole generation of scientists and engineers, including, I should say, myself, were inspired to go into science and technology, in part because of the attractions and the lure of space. It continues, along with other challenges, to be able to play that role. And of course, human spaceflight is a particularly important component of that. The extraordinary capabilities, the extraordinary achievements. One only had to look at the shuttle mission to the Hubble, most recently 5 spacewalks, extraordinary accomplishments in fixing things that were never designed to be fixed in space by astronauts using their ingenuity and responding on the spur of the moment to the conditions they faced. Underlined why it is, always has been, and always will be important to be able to put human beings in space. Robotic space exploration is important too. The other missions of NASA are important in fundamental science, in Earth observation, in aeronautics. But we have to maintain the viability of our human spaceflight program. The President is determined to do that. He's committed to human spaceflight. He's excited by human spaceflight. He has spoken with the astronauts while they were in orbit in each mission that has taken place since he was inaugurated. He'll continue to do that. He met with the Discovery astronauts after they returned. I'm sure we'll meet with the Atlantis astronauts as well. This is a president who gets it. He understands the importance of space. He understands the importance of human spaceflight. He was clear in his campaign and since about his commitment to continue U.S. leadership in space, to go back to the moon, other destinations beyond low Earth orbit. And so the work of this panel is truly important to the President, important to me, important to the leadership of NASA, as a way of making sure that we have assessed all of the reasonable options for our human spaceflight program going forward, to make sure we have the best answers possible to the question of how to minimize the gap in our capacity to put U.S. astronauts into space on U.S. launchers, the gap that will ensue after the scheduled end of the shuttle program at the end of 2010 and the beginning of the capacities to put U.S. astronauts in space in the Constellation program. The panel will be looking at the challenges of how to utilize the International Space Station after 2016. It will be looking at the various kinds of balancing that have to be done in NASA in an environment of constrained budgets among the different missions and the different components of NASA's activities. It is a daunting challenge for the panel, but one, when I review the qualifications of this extraordinary group, one which I really could not imagine finding a more qualified set of people to address this set of issues. Of course, one possibility is that the panel will conclude that the course we're already on is the best one available, and we will stay on it. It may also conclude that there are variations that should be pursued. I know that this panel, with its extraordinary set of abilities and the independence and integrity of all of its members, will tell us whatever it is they think we need to hear about those options going forward. We are looking, as Norm and the panel already know, to get the panel's findings by sometime in August in order to be able to influence a whole series of decisions that the NASA leadership and the administration will be making going forward. That timing, too, is a great challenge, and again, all I can do is express my gratitude and the President's and that of Chris Scalise, who for understandable reasons happens to be in Florida at the moment, to the panel for taking this on. I know that what you find will be of immense use to us as we figure out how to move forward in the most expeditious way with this immensely important program. So thank you again very much, and thank you all in the audience for coming to this first public meeting of the Human Spaceflight Review.
John, thank you very, very much for being here and for the support you and your office have given to us. And I think about all the challenges our nation faces, space being just one of them. So many of them are rich in technology and science, and we couldn't have a better person in the position of advising the President on those issues than Dr. John Holdren. So again, John, thanks for being here and thanks for what you're doing. We now would like to hear from Mr. Chris Scalise, who is the acting administrator of NASA, as you know, who has filled that job for some months now, and we've had the chance to visit with him briefly before, and we'll be spending a good deal of time with him, and we've also had a chance to just very briefly have conversations with his successor, who we'll be able to speak with more when he's officially in position. But Mr. Scalise has agreed to make a few remarks this morning, and if everything works the way we hope it will, and it looks like it is, Chris, welcome, and we'd love to hear not only your comments on this panel, but what's happening where you are.
Okay. Good morning. Well, I guess I'll start with what's happening down here. We, of course, had to scrub the launch last night. We have detected a leak in the GUP, which is the area where we vent the liquid hydrogen, or the gaseous hydrogen. The size of the leak is about the size of a pinhole, so it's very small, but still it's something that we need to be concerned about. We don't yet have the cause for it. This happened recently. The mission before the Hubble servicing mission, we were able to go in there and fill in do a replacement and a repair, and everything went fine. We did the same thing this time. but this time we didn't succeed. So we're going to have to take a step back, go off and look at what occurred, understand the data, and then go back and we'll have an attempt again no earlier than the beginning of July, when we'll try and fly this mission then. But of course we're going to fly safe, and we're going to understand what occurred on this latest activity, and then we'll proceed. But this morning I'd like to thank the panel for agreeing to do this. We know how busy you all are, and we really appreciate you taking the time to go off and work on this very important task. It's hard to add much more to what John discussed earlier. This is something that's critical for the nation. It's critical for NASA. We recognize clearly the importance of space and aeronautics to the nation and to the world, and human spaceflight in particular that we're going to be reviewing here. There's a number of challenges going on in the budget environment that we live in. There's a number of options that clearly can be considered, and we hope to hear those from you and work with you on that. To that end, I want to assure you that NASA is going to be very open and thorough in our support of the team. To that end, we put two of our best and brightest, Phil McAllister, who introduced the conference, and Mike Hawes, to support the team. Mike is the head of our program analysis and evaluation. He's uniquely suited to be able to support the team because he looks at the entire agency. He looks at all of the things that we do. So human spaceflight is one component of that. He has a long history in that activity and understands it very well. I assure you, and I've told him, that he has access to everybody within the agency, and I'm sure Charlie Bolden, when he's on board, will make sure that continues. As we proceed, probably a couple of items worth mentioning. I know the team is going to work very hard. The review committee is going to work very hard looking at what we do. And one of the things, or some of the things that I think are important as you look at us, are to consider the mission that we have to get humans out of low Earth orbit now. That's going to require us to do something we haven't done in over 40 years. The challenge is going to be greater because this time we're not just going to go back to the moon for a few visits for a few days, but ultimately to travel beyond the moon, ultimately to Mars and other destinations that will require long-duration spaceflight. Critical to that, of course, is our understanding of long-duration spaceflight and our International Space Station that is up there today, crewed by 6 people now, and beginning to conduct the research that we need to do to understand long-duration spaceflight. So there's some components that we need to consider there. I'd ask you to consider that the comments of the CABE that looked at the aftermath of the Columbia accident and made some recommendations to NASA about separating crew and cargo, providing crew escape, and those types of activities. Also looking at our international partnerships, both our commitments that we have today, but also what we need to do in the future. Space is an international venture. Everything that we have done almost since the beginning of the space age has involved international partners, whether they be in our robotic missions or in our human spaceflight missions. And we expect that'll be something that'll be continued in the future. And of course, we have to look at our program and understand it in terms of the budget environment, the technological capabilities of the nation, our industrial capabilities, how we maintain those, our academic institutions, and how we preserve the pipeline of scientists and engineers and technicians that will need to operate not only these systems but other systems, and how we motivate them. So that's really about all that I can add to it. Again, I'd like to thank you for agreeing to serve on this commission. I want to let you know that we will listen carefully, we'll work with you closely, and we'll work with the administration as we develop responses and respond to the options that are presented. So thank you again.
Thank you very much, and particularly under the circumstances where you're very busy there, for taking the time to talk to us. And, the support we've received from Mike and Phil has been fantastic, and as we've tried to organize it and get ourselves prepared to move ahead. So thank you, and we look forward to working with you as well. And I think that brings us to our first briefing, which appropriately enough is to take a look at past studies that have been conducted. We're not the first to look at the human spaceflight program by a long shot, and one of the things we'd like to do is to learn from those who've gone before us. Mike Hawes, who you heard Chris describe his position at NASA, has been assigned to give us technical support, and as I say, has done a terrific job of it. And Mike, if you would care to give us a little bit of a summary of past studies that relate to our charter.
Thank you, Norm. That's exactly what I'd like to do, and I only have one, well, it's actually a double-sided chart, and exactly as you captured, this exploration mission question has been studied a number of times by NASA and externals. Some of the studies we have provided you in your homework packages that, you know, we have been sending you weekly since you got named. Some of them we'll be able to hear and discuss in our preparatory sessions, and some of them you'll actually hear beginning today in this public session. So that's really what I wanted to just set that kind of context. We kind of reached back and went back. We didn't go all the way back to Wernher von Braun, but we went back into the late 80s anyway and have pulled out. And I would say that the words here are mine. If anybody disagrees with the characterization of perhaps what the themes were in here, you can feel free to snarl at me, you know, outside during lunch or something. So we start with the Exploration Office case studies back in the late 80s. The 90-day study, which was Dr. Aaron Cohen. The synthesis report, we heard a little bit from General Tom about the synthesis report. We've had provided that for you with copies, so you have multiple versions about that. Followed on with the Office of Exploration, a lunar outpost study in '93. And then continuing in the theme, Dan Golden, as administrator, initiated a number of activities that were all exploration focused. One was focusing on the human lunar return issue, and then an update of a Mars design reference mission is what we mean by DRMs. We have actually also completed some more recent work on updating that Mars design reference mission, given the change in our technologies and environment. The decadal planning team was another activity that was NASA-led, that was in the early 2000s as we have gone through. We have the output of those materials that we can certainly make available. Chris mentioned the CABE report, and in addition to the things that Chris highlighted in terms of separating crew and cargo and the crew safety aspects, the CABE also took time to make comment on the value proposition of human spaceflight, and that value proposition being driven by moving beyond the low Earth orbit that we have been in for the last few decades. So just in that aspect, I cite the CABE for you. Just after the vision was released, we went through a variety of what we called concept exploration and refinement studies. We've actually provided you, I believe, most of those studies in terms of the study packages already. And those studies were across a very broad set of topics and several teams and companies involved in those, so there's actually a wealth of interesting stuff here. When Mike Griffin came in as administrator, he kicked off what has become known as ESAS, the Exploration Systems Architecture Study, and ESAS has set the foundation of where we are today. And so much of what you'll hear from the baseline program has its roots in ESAS, but it has grown and modified in ways as we have gotten really into the detailed design, given the maturity of the program today. There are a few alternative options that are out there. The direct option is one that's well-known and well-publicized external to the agency. We'll actually hear from the direct team this afternoon, so you'll have an opportunity to actually hear that. We did a study within the agency that we called Exploration Acceleration. This was done by Ralph Rowe. As you know, Ralph is on my team. It was done with the full cooperation of Doug and Jeff and the whole Constellation program team, and looked at potential ways to increase our cost confidence for the program. And I think many of the steps that Jeff and Doug are taking now are well tied to that study activity. And then we heard a little bit as well, and has been in your homework, a recent Congressional Budget Office report that kind of lays out some of the constraints of various scenarios of exploration given NASA's budget profile. So that's the context I wanted to set. There are probably many more. You will hear some other variations of activities today. That was the goal for today, was to get all of this kind of laid out on the table for the panel, and then have you work with the NASA team to determine what are the actions that we need to take and go study in more depth. Any of these that you're interested in that we haven't provided, certainly let us know, and we'll find a way. Some of these predate our easily electronic age, so we'll find a way to turn them into electrons so as to kill less trees, but we can certainly make all these available for you, and that's really all that I wanted to try to accomplish this morning.
Mike, thank you very much. And we have been, frankly, inundated with documentation, and we'll be putting much of that on the website. That which is not proprietary or have other sensitive aspects, we will try to share with you as much as we've had available to us. The next topic on the agenda is logically enough, I think, to talk about the existing program that's being pursued, the Constellation program, and Doug Cook of NASA is going to give us a very quick snapshot of that to sort of fill out the reading material that's been available.
Thank you very much, Chairman Augustine. I appreciate the opportunity to talk with you and your panel. I represent the Exploration Systems Mission Directorate, and our primary program, most visible is Constellation program. We also have a human research program, a technology program, a robotic program, and we also have the COTS effort within our program. These are all important to us, and most of which feeds directly into the Constellation program and helps support it. Our focus at the moment is a program driving toward initial operating capability in March of 2015 with a mission to the space station with Ares 1 and Orion. We do have a focus also long-term on moving beyond low Earth orbit with exploration, and that's very important to us, and we have quite a bit of our effort in understanding the end-to-end architecture that we work toward. We have a number of milestones coming up very shortly. Actually, in the next 3 days, we hope to launch Lunar Reconnaissance Orbiter and the Lunar Crater Observation and Sensing Satellite, which is both of which are going to the moon, robotic spacecraft, and will be getting us rich data that will feed into our understanding of the moon. So we're really looking forward to that, and they're ready to go. We also have this summer the first test of a 5-segment solid rocket booster, which is the first stage of Ares 1. That will be in August. We have a preliminary design review on Orion in August as well. We have the Ares 1X first test flight no earlier than the end of August, but within that general time frame, and a pad abort 1 test this fall. So we have a lot going on, and we're making a lot of progress. We hope to show that to you in this presentation. Next chart. There's a lot of discussion on vehicles concepts, but to us, we consider the entire mission. What is it we hope to accomplish? And we have we have gone through an international set of activities and with 13 other space agencies in developing objectives and themes for what we want to accomplish as we move forward on the moon in particular. As we have developed concepts, we look to this for the lunar operations, which we've studied a lot. Actually, we've had teams going on that for since 2006 to define what exploration means on the moon. What is it you actually do and achieve? So that has informed the overall transportation architecture, which is shown here. And so as you develop those lunar scenarios, we came up with the idea of an outpost at a polar location that tends to drive your lander, which then backs up into end-to-end performance understanding on your entire end-to-end transportation architecture with the appropriate allocation of mass and performance margins to all the vehicles so that end-to-end it all closes and it works. So this is an integrated architecture that we've been working on, and it has informed our current vehicles. The performance obviously affects the designs and performance of Ares 1 and actually the Orion. Things like trans-lunar injection loads when we fire the Earth departure stage to send Orion and the lander to the moon. You have loads and those loads have been studied and has affected the structural design of Orion, for instance. So all of this is being worked in an integrated fashion as we develop and mature the design for Orion and Ares 1. We go to the next chart. We also have a number of top-level objectives. We have a cascading set of requirements that derive from this, and they derive originally from policy. That is national policy, including authorization acts of 2005 and 2008 that have focused our attention and designs to meet this. That includes a retirement of the shuttle in 2010, reducing operations costs in order to be able to operate effectively and have a sustained program in the future, to develop the systems that we have in terms of building blocks for future exploration to Mars and beyond. We have as a primary focus as a design factor safety. This program was born out of the Columbia accident, and we have had a focus on loss of crew probabilities as we develop our systems, and they have driven actually many of our component designs. We are to, in our planning, are to support space station by 2015 and get to the moon by 2020 with lunar missions. A driving factor, Chris mentioned it earlier, separate crew from cargo, and we also have to pay attention to our existing infrastructure and assets, people, workforce, in terms of both NASA and the supplier base. It's an important factor in all of this. Other factors that we have driven into the design are global lunar access, anytime return with the vehicles, use of space station for exploration goals, which we do through our human research and technology programs, as well as we will with the Orion, and to promote international and commercial participation. We think all of this has to be looked at in terms of an integrated architecture. If we can go to the next chart. We've gone through a decision process to get to the vehicles that we have that are driven by this guidance, and I won't go through step by step because we want to get to some of the other aspects of the program. But basically, we've gone through decision steps that have led us to where we are. The fact that we go beyond low Earth orbit has driven us to heavy lift, to the physics drive you to a capsule-type design versus wings in terms of entry speeds and that sort of thing. And also in terms of understanding the transition of workforce and infrastructure facilities that were developed for Apollo and the space shuttle, it has affected the approach that we've taken, which is a shuttle-derived design, the Ares 1 and Orion and Ares 5. And through that decision process, we have looked for the opportunity to have synergy between these vehicles. We do between the solid rocket boosters, the J2X upper stage engine, which is important to both, and other systems. We can go to the next chart. And so as we assess this capability in our initial approaches to supporting space station and the moon, we also have assessed it with respect to Mars missions in terms of lift capability with a heavy lift and crew size with the Orion. And it is capable as the basic transportation infrastructure to support various destinations. Next chart. So an important factor I mentioned briefly is the transition of shuttle capabilities. We are making use of a significant set of capabilities, both facilities, people, and hardware at a number of locations. We have manufacturing capability that was developed for Apollo and is used by the external tank of the shuttle at Michoud. That is one that we're going to use as we develop the upper stage and build structure for Orion. We have other capabilities. We have the big capabilities you see at KSC with the VAB and the launch pads, and we have a significant supplier capability in ATK with building solid rockets. We have Pratt & Whitney Rocketdyne building liquid rockets for our human spaceflight vehicles. So there is a significant synergy, and actually has been very important in trying to efficiently and effectively move from shuttle to station in terms of figuring out how to transition all of this infrastructure. And so it's important as we move across these boundaries in the retirement of shuttle and the flight of Ares 1 and Orion that we understand how we work through all these capabilities that we have in the agency. So that is a part of our decision process and why we're on the path we're on. And I would like to now turn it over in a minute, so if Jeff would be getting ready, we can go to the next chart. I have two charts that show where the work's being done currently. We do have all of Ares 1 and Orion on contract. We have civil servants with various responsibilities all over the agency. We've spread out a number of the primary responsibilities. All of the NASA centers are involved in this work. Next chart. We also have, as I said, contractors in place that are working on all aspects of this, including now EVA, the EVA suits, but located in places across the country supporting this program. And if Jeff would come up, I would like to hand it over to him to go through some of where we are in status and our approach to this, as well as address some of the issues and the progress that we're making.
Thank you, Doug. Good morning. So I have a short movie to show you in just a minute to kind of really most efficiently express to you the progress over the last 3 years, where we're at. Before I get to that, though, I do want to touch on a couple of the issues that I know get discussed now and then in the community, and I thought I'd update you on our progress on those. So next chart. First, this is the key driving aspects of our lunar mission that we're designing to, and while many of these or all of these affect the solution for going to the moon, the couple of them are most significant. Global lunar access, global surface access, is really probably the main driver in what size is this architecture. But all those parameters have been studied. They've been parameterized. We've done a significant amount of work to understand what this integrated architecture must do, as Doug was pointing out in his remarks. Next chart. And we've looked beyond the moon. We've gone and refreshed the Mars studies of the 90s for human missions to Mars, and to refresh that, looking at it from the standpoint of applying constellation elements and making sure that the decisions that we're making today have a feed forward, not just to the moon, but actually are building a capability that will eventually result in an ability to realize a human Mars mission. Next chart. And we've looked at other applications of this hardware. There's many possible things that one can do with this robust heavy lift architecture that we're trying to foster with Constellation. We've got a capability to put cargo on board the Orion, be able to do missions other than just the crew transport mission to the space station or to meet up with a lunar lander in low Earth orbit. We've looked at other applications of the, us and others have looked at other applications of the Ares 5 lift capability. Not only is it unprecedented in terms of the amount of mass it can lift to low Earth orbit, but also the volume. We've sized it so that volumetrically it will be unprecedented. In this cartoon here, the lower right that's not a sophisticated satellite. That's several school buses that are stacked inside the Ares 5 shroud. Very significant capability. Next chart. And so here's a couple of the main issues that folks bring up every now and then, or they hear about, that I thought I'd give you the latest information on. First of all, as we've just pointed out, it's an integrated architecture, and so mass is one of the driving parameters, both the lift capability of the rockets and how much the elements that the rockets carry weigh as you go through the entire life cycle of a mission, from liftoff on the launch pad until the crew is recovered after landing. And so here's where we're at today with for the ISS mission for the amount of margin that we're currently carrying. For Ares 1, it has 22% lift capability margin, which is very good for where we're at today, which is just after PDR for the rocket. The spacecraft sitting at 23% mass margin for the ISS mission. And I am holding at my program level an additional 5% margin on top of that. We're doing very well for Block 1 of Orion and for Ares 1. The lunar mission, still healthy margins, but probably the most driving one that you see there on the chart is the 10% for Orion. We'll watch that very closely. I've got that additional 4% in my pocket in the event that we need that, but the rocket, again, Ares 1, doing very well to be able to lift the Orion to do both the lunar mission and the ISS mission. The limiting factor in this architecture today is, in terms of the Orion's mass, is its ability to land under the parachutes. The mass limit for the three big main parachutes is really the driving the parameter that sizes how heavy the Orion can be. It is not the lift capacity of the rocket. Another issue that gets talked about is what we call tower clearance or launch drift, and this received some notable mention a few months back. If one goes and looks at a video of the Saturn V lifting off launch pad during Apollo, watch it closely from the right vantage point, and you'll watch that launch vehicle walk off the pad away from the launch, actually steer away from the launch tower, and the Apollo crew members speak quite eloquently about what that sensation was like. Well, this is no different in this case. Every launch vehicle needs to assure its way as it takes off the launch pad. We have one specific wind direction with a very stiff wind, near hurricane force winds, where we would need to actually steer away from the launch tower, which we can easily do. We have a design in place that could realize that. We can also look at limiting the wind conditions for that one case, which would not be a significant impact at all to what we call our launch availability, our probability of launching on any given day of the year at the Kennedy Space Center. So that issue is for all intents and purposes really now just focused on how do we minimize plume damage to the launch tower as the vehicle flies away. For any rocket and spacecraft system, one of the driving issues that designers deal with is induced environments. That's the loads and the weather that you gotta fly through, and the speeds at which the rocket is traveling, and what that induces on both the rocket and its payload. And one of the conditions that gets talked about quite a bit is the phenomenon of thrust oscillation. And this is the phenomenon for about a 10-second period in the 130-second burn of the first stage. For about a 10-second period, the solid, which is really just a big tube has a resonant frequency. It's like an organ pipe. And so there can be conditions where for that 5 to 10 second period, it can resonate in a way that will vibrate not just the solid motor, but the entire vehicle if the vehicle is tuned up to it. So we have taken active steps to mitigate that through putting in isolation planes between the solid and the second stage, and between the second stage and the spacecraft in order to mitigate that, and we're moving forward with those designs. And that design will give us not just for a single set of conditions, but for a range of conditions that could, worst case conditions that could occur with that phenomena. In addition to that, we continue to work, as every team of rocket designers does. We work on vibroacoustic loads. In other words, the sound levels, both at liftoff and during flight, the sound levels have to be accounted for in the design of the spacecraft and of the rocket and selection of the components. And that's all normal work for us. Next chart. Loss of mission, loss of crew. This is where we want to make a historical jump in the safety of the systems, both for launch and in flight. An order of magnitude improvement over what we enjoy with the space shuttle today. We believe that we are on a path to achieve that. The rocket and the spacecraft, from a board capability perspective today, we're doing much better than 10 times of what the statistical analyses of the shuttle suggest with respect to the ascent risk. And over 60 vehicle design changes have been made, and we've driven into Constellation a risk-based design culture that looks at the probabilities of particular components failing, what their implications are to the mission and to the crew's safety, and we have made our selections in terms of architectures in spacecraft systems and selection of components in order to make the safest and most reliable spacecraft and rocket system that we can. Post-landing crew survival, we've got a system that can survive for 24 hours, landing anywhere in the water in the world, and we've also made sure that under the contingency condition that the spacecraft should land on land, that is in fact a survivable event for the flight crew. Budget has continued to be a challenge. There have been many numbers floated out there as to what the total cost to initial operating capability is today. We stand at $35 billion. That's with reserves to achieve the March of 2015 goal, and that's with a confidence level and cost of 65%. In other words, 2/3 a chance that it will not cost any more than $35 billion. That's really what all that really means. We did have an original plan to spend within the time frame of now through 2015 an additional roughly $9 billion to get started on Phase A of the lunar program. That's Ares 5 and Altair. That whole activity, of course, is under review by this panel. And schedule for ISS initial operating capability. Our external commitment of March of 2015 is stable today. We have a plan to get to that date. We are, by the shape of our funding profile, we are challenged to make sure that we get the right components in the pipeline to get the spacecraft built so we can get it qualified, tested, and verified to meet that March of 2015 date. So we are undergoing right now, as Doug alluded to, a program-wide content review looking at the entire breadth of content in the Constellation program to see if there's any economies that we can find, whether we can eliminate certain configurations, and one of those notable ones was the 6 versus 4 crew. We eliminated that strictly to simplify the path to get to initial operating capability March 2015, and that was worked in very close coordination with the Space Station program. Next chart. So here we'd like to show our little video, if we could. And the hope is, of course, that the technology cooperates with us here.
It has been 3 short years. NASA began a journey to create the next space program, one that would take us beyond Earth orbit, returning us to the Moon, and extending our reach to Mars and beyond. No longer just a program on paper, Constellation has projects, hardware, and software in every stage of development. In just 3 years, Constellation is ready for its first test flights, launching a new era of human space exploration. Through the Constellation program, NASA has taken a vision, the idea of exploring beyond low Earth orbit, and strategically created a detailed space architecture, a plan to make the vision a reality. Constellation begins by conducting missions to the International Space Station, using the Space Laboratory as a destination and proving ground for a new generation of spacecraft. Next, Constellation sets its sights on the Moon, exploring the lunar surface in ways never before possible. Unlike Apollo, which was limited to the exploration of the lunar equator, Constellation's architecture will allow astronauts to explore anywhere on the Moon, staying twice as long as the Apollo missions, with twice as many crew members. This extended exploration capability has been a driving force for all of the Constellation spacecraft designs, which will be able to lift more mass and travel farther than any previous spacecraft. The Orion spacecraft is the crew exploration vehicle for Constellation. Orion borrows its shape and aerodynamic performance from Apollo, saving time and design work as well as reducing risk. However, the spacecraft is greater in size than Apollo, featuring updated computers, life support, electronics, heat protection, and other systems. The development of the Orion spacecraft is well underway. Several test articles have already been constructed and are being evaluated at NASA centers and engineering centers across the nation. Parachute drops have been conducted to test how Orion will return crews safely to Earth. The launch abort system, capable of pulling the spacecraft and its crew to safety in the event of an emergency, is set for a full-out test in 2009, while the rocket motors used in that system have already been evaluated in preparation for that flight test. The launch vehicle for Orion is called Ares 1. It features 2 key components utilizing legacy hardware. A solid rocket booster, similar to that used by the Space Shuttle, comprises the lower stage of Ares 1. The upper stage features a J2X liquid fuel rocket engine, derived from an Apollo-era rocket engine. Using these proven systems, the Ares 1 will get the crew into Earth orbit. The Ares 1 project completed its preliminary design review, the first such milestone in more than 35 years for a U.S. rocket. A test flight article of the Ares 1, called the Ares 1X, is slated for launch in 2009. The test flight will be a major turning point in the program, providing essential data on avionics, thrust vector control, and other systems, validating computer models by actually flying a full-scale vehicle. In preparation for the test flight, segments of the Ares 1X have already arrived at the Kennedy Space Center for assembly and processing. In addition, tests continue in all facets of the Ares program, from computer simulations to wind tunnel tests to engine test firings, providing engineers with the best information possible on how the crew launch vehicle will perform. Ares 5 is the heavy-lift cargo launch vehicle. It will carry the lunar lander and other large components into space. Again, using legacy hardware, the Ares 5 will utilize solid rocket boosters during liftoff to help get the vehicle into orbit. The crew on board the Orion will rendezvous with an Earth departure stage of Ares 5. The entire stack, Orion, the lunar lander, and the Earth's departure stage, is then sent toward the Moon, once again using the J2X rocket motor. Because several key components of Ares 5 are the same as Ares 1, much of the engineering work being done applies to both vehicles, from solid rocket booster tests to firings of the J2X rocket engine, which is the first component to pass beyond the critical design review phase. In all, the Ares 5 will be able to lift more mass than any previous spacecraft. Studies have already been conducted to see how this versatile craft could be used to launch scientific payloads, satellites, and even space telescopes. The Altair lunar lander will carry 4 astronauts to the Moon. Larger and more robust than its Apollo predecessor, Altair will be able to land anywhere on the lunar surface, even the lunar poles, previously an unreachable target by manned spacecraft. The Constellation program recently completed a lunar capability concept review, demonstrating how the Altair lunar lander will reach the Moon and later help build lunar outposts. Spatial studies by engineers have helped determine the interior layout of the lander, driving out better ergonomic designs for the crews who must live on board for extended stays on the Moon. Additionally, work has already started on testing and improving all the gear needed for exploration in the Constellation era. From lunar rover tests to planetary spacesuits to tools, NASA is taking hardware out of the laboratory and into the field to achieve the best possible designs. In addition to the hardware development, NASA facilities are updating their capabilities for Constellation. New launch pads, lightning safety systems, firing rooms, factories, and testing facilities are being completed to accommodate the new wave of exploration requirements. Most importantly, the Constellation program is about people. From around the nation, all NASA centers are engaged in this new exploration effort. Problem solving, building, testing, and taking on the challenges of human space exploration. It is an effort that brings together generations, those who experienced the Apollo moon landings and those who came after. Together, they are working on a brighter future, looking to return to the Moon and go beyond. As the Constellation program leaps off the drawing table and onto the launch pad, a new chapter in exploration history is being written, one milestone at a time.
Okay, if we could just return to the charts briefly here.
Doug, we got a hard cutoff with the
Gotcha.
video conference coming right up.
So
last
with
one.
that, there's photographs in the back of additional hardware, and thank you for your time.
Thanks,
Doug, thank you very much, and I think we've all got a lot of questions. We won't have time to take them right now, but we'll have plenty of chance to work with you in the future. What we want to do now is turn to another important aspect of the space program, which concerns our efforts with our partner nations. And we have the opportunity this morning to visit with two of our partners, Mr. Dardan from ESA and General Permanov from RSA. I believe they're together, actually, and we will set up a link here so that we can visit with them.
Say again. Okay. All right, well, we've hit our first glitch of the day. Apparently, the video conference link has had a technical difficulty in Paris, which is where our international partners were going to link up with us, but we do think we could get it addressed in about 10 minutes. So we're going to take a 10-minute break.
Well, wait a minute, why don't, instead of taking a break this early, why don't we ask some questions
Oh, that's a great idea.
of Doug here, if you don't mind?
Yeah, we,
Maybe we can let him.
Both of you, I'll start out with one while my colleagues are thinking here, if that's all right. I was struck on the LOC calculations that on the shuttle that we know a lot about, we show a range of uncertainty about a factor of 2, 160 to 270, and yet for the Constellation, it's 1,200 or 2,850. And I'm not trying to nitpick, but just the question is, if we're so uncertain about today's system, how can we determine with certainty or anything approaching certainty?
Well, that's a great question, and it's probably in the way that we chose to express it in the charts. The number that we cite for Orion Ares 1 is the mean, and there is a distribution around that that would have a low and a high value. It could be as low as a certain number and as high as a certain number. I don't have those numbers with me today. The way we use these numbers is really in comparison with alternatives in the design that we might choose for various systems. The probability numbers are really informing the design. And so as we do comparative analyses, really the absolute number is less important than as long as the analysis is done in comparing the alternatives in a apples to apples way. That's where we would get the most value out of those numbers.
Thank you. My colleagues?
Certainly we could provide
Wanda's got a
backup to
question
that,
here.
too. We'll provide backup to that.
Yeah, and in particular, it'd be interesting to look at what are usually called the P5 and P95, you know, the statistically significant lower and upper bounds of those numbers to get some insight as well.
Wanda?
Yes, you indicated you had a 65% confidence in the cost numbers. What's your confidence in the schedule of March 2015?
Right now, the model that we have the most history with is the cost. We're actually developing a schedule model to get that type of calculation, and we're working through that with PA&E at headquarters to get to a point where we have a good schedule calculation in terms of probability. Our schedule, we are actually at this point we have moved from internal dates that we were planning for to our commitment date of March 2015. So we're realigning our internal schedules right at this moment. We know we have areas we need to work, and so it's a tight schedule. That's certain.
Chris?
Thank you. Your chart that you showed us on influence of key drivers on architecture selection compared loss of crew probabilities for EELVs to Ares 1 and argued that it was really that distinction, if I understood the chart properly, that preferred Ares 1 to EELVs. You've just said in your remark that there's a range, of course, with respect to that estimate for loss of crew for Ares 1. Does that, does the 1 sigma and that extend over into the EELV range? Can you give us some sense of whether there's really a statistically significant difference between the two?
I think in terms of the numbers that we showed you, the relative differences are important. There are certainly probabilities associated with each one, and once again, I don't think we have those numbers here, but I think they were calculated in a apples-to-apples sense.
We will get those numbers.
Yeah, we'll get you the background on that.
It's important to note, though, that the methodology used to assess all of the launch vehicle options was a common methodology. That's what ESAS really was about. It was to take the synthesis of prior analysis and bring it apples to apples against a basic set of mission requirements and compare on a level playing field as best we could.
Roy?
I have a question about the Orion. I know the nominal plan right now is to land in the water, but I noted in your charts that in a contingency you can land on terra firma, and if that's the case, I'm wondering why we don't go back to that now.
The reason is, in a contingency sense, we don't carry as much redundancy in the systems. If we use it as primary mode of landing, we would have a lot more redundancy in it. It would weigh a lot more, and that's really the primary reason that we went to the water landing. We wanted to make sure that we had the capability to land the crew without injury, but there's not the level of redundancy in systems to get to making that a nominal case.
Okay, so even in the reduction of crew size from 6 to 4, that's still the case? I mean, you're still too heavy to land on land.
The thing is that we don't want to lose the capability associated with 6 crew. So if we fill up that with weight, then you don't get to that point again. And also, it's important in the time frame that we'd be traveling to space station that we are able to carry up mass and down mass. So we don't want to give up the mass, any mass savings that you'd have there. We don't want to give all that up to that capability or to get away from the original requirements.
Mr. Chair, our link is back up with France. Unfortunately, we're only going to have an audio, and we need to cut over right now. Sorry, Doug.
Hey, Jeff and Doug, thank you very much. Appreciate it. Is the audio link live now?
Yeah, just go ahead and make the introduction, Mr. Chair.
Okay, fine. This is Norm Augustine, and I'm here with my colleagues on our committee looking at the future of the U.S. human spaceflight program. We understand our video link is down, but the audio link is working. We're very appreciative of your taking the time to speak with us. I've already introduced you to the audience here in the room and on the television here in the U.S. But to both Mr. Dardon and General Permanov, as I say, we're very anxious to hear your thoughts. Whatever it is you'd like to share with us, but a few things that I think we'd be particularly interested in would be what you see as...
Mr. Dardana and Mr. Permanov did not arrive yet because we were struggling to get the video link working. They will be arriving in a second. Sorry to interrupt you.
Let's see, I believe I heard that Mr. Dardon, you were there though, right? Can you hear us?
Norm, this is Alan Ladley. We can hear you, and Mr. Dardon is now coming in the room.
He's not coming in the room. He's not coming in the room.
Okay, do you hear me? Jean-Jacques Dordain speaking. Okay, so can I start my remarks?
Well, thank you. And let me just say a couple of things that we would be particularly interested in hearing, and we'd welcome whatever you care to say to us. We'd be very interested, I think, in your view of the utility of the ISS beyond 2016. We'd be, I think, also very interested in your thoughts of what international programs might go beyond the ISS into the future. We'd certainly welcome any comments you have on future international relationships and on some of the lessons we've learned from our partnerships to date. So with that, let me turn to you, and again, thank you for sharing your thoughts with us.
Okay, no, thank you from my side. Thank you very much for giving me the opportunity to make a contribution to your committee. Just to start by saying that this hearing is very timely, since for the first time in the history of the International Space Station, we have a crew of 6 on board, made of 5 different nationalities, meaning that each international partner is today represented in orbit. So we are represented in orbit not only with hardware but also with astronauts living and working together in orbit as we are working together on ground since 20 years. So this is just a fact which should inspire our reflections. There is not anymore, for any of the 5 partners, a separate human spaceflight program. We have all together one human spaceflight program shared among 5 partners. Obviously, ESA cannot have a separate human spaceflight program because we are dependent on other partners, in particular for transportation. But it's interesting to see that NASA and Russia could have a separate human spaceflight program, and they have not. They have just a contribution, a significant contribution, but to a joint human spaceflight program. And this is the reason why I am attaching a great importance to the hearing of today, because your conclusions may have an impact on our own plans, but also I hope our inputs might have an impact on your conclusions. So I would like to thank Mike O'Brien to have sent me 4 questions that you have recalled, 4 questions of interest for you, and I shall start by answering your questions. It being understood that I am ready to answer any further question you may have, either today or at a later stage if it is necessary. So I have not prepared a presentation of the European Space Agency, its programs and activities. However, I would like to underline 3 characteristics of ESA, which could explain a lot what I shall say when I am answering your questions. So the first characteristic of ESA is that today ESA is 18 member states, which according to the ESA Convention pool their resources for developing space systems for both science and applications to the citizens. This means that the overall ESA activities range from science of the solar system and the universe, science of the Earth and its environment, life science, physical science, to operational meteorology, operational services for environment and security, operational navigation systems with Galileo, without forgetting obviously our activities related to the guarantee of access to space and the development on competitive technologies, in particular for telecommunications. So as a result of that, and this is the first characteristic of ESA, human spaceflight activities in ESA represent less than 15%, 15%, of the total ESA activities. And member states will never decide to increase their contribution to human spaceflight activities to the detriment of science and services to the citizens. And I shall come back to that. The second characteristic of ESA is that this balance between different types of activities, what I have called science, applications, innovation, launchers, human space flights, is organized and even protected by the fact that there is not one ESA program and one ESA budget, but as many programs as type of activities. And each development program is subject to one legal decision through which the member states participating to that program are committed up to completion of that program within the limit of 120% of the initial budget. So this process that I have described makes decisions at ESA difficult, but on the other hand, it provides a fantastic solidity in each decision. meaning that I dare to say that ESA is certainly the most reliable partner in the world because our member states are committed up to completion of any program. The third characteristic that I would like to underline is that if there is one topic on which ESA can teach the world, it is about international cooperation. International cooperation is our daily life. It's 18 countries of Europe working together every day within ESA, but also cooperating with almost all space powers in the world, starting obviously with NASA, because ESA has started under our cooperation with NASA, so we don't know what means working without NASA. So NASA has always been a partner of ESA, and we are working with NASA more and more, not only on the space station, but also in science, in environment, and a lot of different subjects. With also Canada, with a very special place for Canada, because Canada is both an international partner, but also not a member of ESA, but I would say a cousin of ESA, Canada having the right to contribute to some ESA programs. But we are cooperating also with Russia, with Japan, with India, with China. So we know how much cooperation is difficult, and I can tell you that as a Director General, I appreciate that every day, that cooperation is difficult. But I can report that cooperation is also successful. My usual mantra is to say that it's always easier not to cooperate, but always more difficult to succeed alone. So this is with this background, and I am sorry to have spent 5 minutes on ESA, but you have, I wanted that you appreciate this background to tell you how I am answering to your questions. So now let's move to the fourth question. So your first question what has ESA learned from ISS partnership? So I am deeply convinced that the partnership is the most important asset of the International Space Station, which will live much longer than the hardware in orbit. The ISS partnership, I would call that an operational G5. I must say that every day we are hearing about G8, G20, G something. I consider that we are a G5 working every day together to reach common objectives. This is a very solid partnership because it has been built up through a long list of problems, technical problems, financial problems, political problems that we had to overcome together, and even tragedy, the worst being obviously the loss of Columbia, that we had to face together to reach a common objective, completing the assembly of the International Space Station and maintaining a permanent human presence in orbit. So ISS today is already a success, a technical, operational, and management success, a fantastic success based on partnership. The first lesson, and maybe the most important, the first lesson of this partnership, and I shall come back to that at the very end of my remarks. The first lesson of this partnership is the interest of keeping a partnership open to new partners. The partnership of the ISS has moved from the original 4 of the Space Station Freedom, United States, Canada, Japan, ESA, to 5 in '93, when the 4 partners, and I insist on that, the 4 partners, USA, Canada, Japan, and ESA, sent a collective invitation to Russia for joining the partnership. And I must say that 15 years later, we know that this was that decision which has saved the International Space Station after the Columbia tragedy. Without the Russian partner, we could not have sustained a human presence in orbit. So just to say that sometimes it's good to open the partnership. Now, and just because the partnership is so solid, we have to draw together the lessons learned coming from our common experience on board ISS. And in particular on what we could have done better to make sure that our future endeavors will be even better. And I must say that I think that I was the first one among the ISS heads of agency to propose to share the lessons learned. And the exercise is still ongoing. And this is the reason why today I would have preferred to give you the lessons learned shared by all partners, but the exercise is not yet completed. So I shall tell you which points must, in my view, be investigated for improvements. The first one, and this is obvious, there is a need for redundancy in key functions, in particular transportation functions. We have seen that. When the shuttle has been grounded, we were all grounded because the space shuttle was a unique transportation system for our modules. I am not even speaking of the crew. But all the partners were grounded when the shuttle was grounded. And that is a very important lesson learned, meaning that I often hear about interdependency. Interdependency should not mean a lack of redundancy. So you can be interdependent, but we need to accommodate redundancies for the key functions. The second lesson learned that, on which I would like to make some progress is the need for full standardization. Because interdependency requires standardization of interface. We have made a lot of progress on board ISS about standardization, but we are not yet at full standardization. And this would help a lot to have a complete standardization of our interfaces. The number three, and maybe it's because I was in charge of utilization of the space station 20 years ago, we need to balance the utilization, the assembly, and the maintenance activities in any big endeavor from the very start of the program. The choice which has been made, and maybe this was the only choice after the Columbia tragedy, but the choice which has been made to push back all utilization activities after the assembly complete is a big problem. Because we have postponed to the end the benefits. And we have even created a gap between the space station and the user communities, which had to wait for 10 years between the start of the assembly and the start of utilization. And that is a big problem that we have to solve. Users must be on board as soon as possible. So the evolution of partnership from freedom to International Space Station, as well as the sequence that I just described, assembly first, utilization second, has extended the program into a very long period. Too long, in my view. To the point that almost nobody was at the start, who were at the start of the space station are still at the end. Maybe I am the only one because I have started on the space station 25 years ago. But I look like a dinosaur now. But But it's a too long period, with no intermediate, concrete, and visible milestones, which could have focused the teams on shorter-term objectives, and could have attracted the attention and interest of governments and public much earlier. And if I say that, it's because I am from a very lucky generation. I was 10 years old when Sputnik was launched, and 3 years later it was Gagarin. And in less than 9 years, United States put a man on the moon. So to have programs extending for 20 years is much too long. So we have to create intermediate milestones which are visible, concrete, which can focus the short-term attention. And this is the reason why I would say that the last improvement that we could bring for future endeavors is to associate the public from all partners to the program. I don't think today that the public is attached to the International Space Station. So this is my answer to the first question. Now, I would like to say that unfortunately you have not the typed version of my remarks, but you will get that tomorrow. I have written that this morning, so it's handwritten for the time being, but you will get a typed version, because I am not so sure that my French accent is fully understood in Washington, D.C. But okay, I am doing my best. So the second question is, what is the ESA's interest in continuing the ISS program and why? First of all, as I said above, the ISS program has been sequenced in 2 successive periods, the assembly and then the utilization. And we are just at the end of the first period. And the second period is just starting. And I must say that speaking of continuation of something when you are just starting the sequence, which is interesting, I must say that is for me somewhat strange. Because the ISS, as I said, the ISS is already a technical success. But it's not yet a success in terms of utilization. We have still to demonstrate that. And I think that failing to demonstrate that, I am not so sure that the overall assessment of the ISS would be a success. So this is the first reason why we have to continue ISS operations. Just because we have to reap the benefits of the investments made by utilizing extensively the resources on board. The ISS is a unique laboratory, offering resources which cannot be found on Earth. And as for any laboratory, significant results are not coming within months, they are coming within years. So I think that for me the question is very simple. We know the cost. The cost of utilizing the ISS are well defined. We know how much it costs, which may be not the case for all laboratories. So it's already something which is good. So the only answer to the question, how long should we use the ISS as a laboratory, is, and this is always my answer, and this is what I have answered to Mike Griffin when we were discussing that. I always answered, as long as the benefits are worth the cost. And this is the reason why, as we are doing for any satellite, my position is the following. We have to organize every 3 years a joint assessment of the benefits of using the space station. And we have to jointly decide if, on the basis of such assessment, it is worthwhile to continue for another 4 to 5 years because we need some margins. But to have that every 3 years and to continue on the basis of the assessment of the benefit to cost, as long as, technically speaking, the space station can be used. And even, I would say that if the benefits are so worthwhile, we have already to think about a laboratory in low Earth orbit beyond the ISS, because I cannot tell the users today, you have to use a space station, but you better hurry up because we shall close in 5 years from now. I am not so sure that this is the best way to attract the best scientists. So let's continue to use a space station as long as the benefits are worth the cost. So this is the first reason to continue. The second reason to continue ISS operations, and this is a totally different rationale. It is because the space station is part of the human exploration program. This is not disconnected, and I shall come back to that, from the human exploration program. The ISS is the place to test hardware, to test operations, I would say to test astronauts, before they are used in a lunar base, and even more on a Mars base. I must say that even the space station is more useful, in my view, to test the hardware for human exploration of Mars than for lunar exploration of Mars. Because, and moreover, there cannot, in my view, there cannot be any gap between ISS operations and the operations of a lunar base. Because this is the same people which will operate ISS on one side and the lunar base. And the expertise is always with people. If there is a gap, we shall lose the people, we shall lose the expertise. So we should not have any gap between ISS operations and lunar base operations. So in conclusion of that question, there are two rationales for continuing the ISS programs, exploitation. One related to utilization, one related to human exploration. And by the way, the two rationales can lead to different dates. And this is the reason why, in my view, we should not define any date, but just a rationale. And we shall see. We shall decide when we need to decide. So I am going to the third question, which is how would you characterize the ESA obligation and that of the US to the ISS in terms of its operational life? So as I said above, it is more a question of rationale than a question of obligation. If we have a good rationale, I feel that it is an obligation. And if we have not a good rationale, I think that it would be stupid to continue. So I don't think that this is a matter of obligation, but more a matter of rationale. But since I am a good civil servant, I have looked at the agreement to see where were my obligations. So the obligations, they are defined in several agreements, the multilateral intergovernmental agreement at governmental level and in the bilateral MOUs at agency level. So the obligation of each partner is to maintain its own flight elements in order and to pay its share of common operation costs. Meaning that for ESA, we have to maintain the Columbus laboratory in order, and we have to pay 8.3% of the common operation cost. This is the obligation of ESA. And against such obligation, ESA has the right to use 8.3% of the resources on board. That is a right, it's not an obligation. I can use or not that right. So this is the first aspect of the obligation. Second aspect, when you read the agreement, or at least I hope that I have not made any mistake, I have not found any termination date in the different agreements, meaning that operational life continues as far as no decision is taken. But third, and that is an interesting point, each partner has the right to withdraw unilaterally at any time. And that I would like to say that there is a difference among the partners. Because if ESA withdrew, I think that the other partners could continue without ESA. But if NASA withdrew, I think that this is the end of the space station. So this makes a difference between at least NASA and ESA for the right to withdraw unilaterally. However, I don't think that a unilateral decision could happen. First, thanks to the solidity demonstrated in the partnership, I think that there is a real solidarity among the partners. Second, because the rationale is the same for all partners. If we have a good rationale, it should be applicable to all partners. So, the duration of operational life should rely on solid rationale and should be a joint decision by all partners. I would say that at the end, the only obligation of each partner is to match their budget with the objectives, but this is true for any program, including for non-space programs. So this is not something which is a great statement. And I am coming to the last question. How does ISS and its extension past 2015 connect to the ESA's future plans for human and robotic exploration beyond low Earth orbit? So the future plans of ESA for human and robotic exploration will be defined in several steps. So they are not completely defined. This is very clear. The next step is in 2011. But the first step has been taken in November 2008 with important decisions taken by the member states. First of all, the member states, they have decided to embark into an ambitious program of robotic exploration of Mars. With the first mission, ExoMars, which is under detailed definition, with a target date of a launch in early 2016, and with an objective for ESA to demonstrate landing, moving at the surface of Mars, and drilling capabilities. And follow-on missions are already being prepared. We have a Mars robotic exploration preparatory program beyond ExoMars, just meaning that there is a long-term vision in our member states to have a continuous robotic exploration of Mars. So I must say that on this robotic exploration of Mars, we had extensive discussion with NASA. And we are close to an agreement for a long-term cooperation on robotic exploration of Mars. There is a meeting at the end of June planned for that. And according to the discussions, there could be significant contribution of NASA to ExoMars and contributions to ESA to further NASA mission, exactly on the model of our fantastic success of Cassini-Huygens. Discussions with Russia are also going on, including an ESA contribution to the Russian Phobos Grunt mission. So this was the first part of plans taken by member states. For what concerns human exploration, the member states, they have just decided to start some preparatory activities to define a potential contribution of ESA to a human lunar exploration program. But it is clear that for human exploration, as I said already, number one, Europe is dependent upon other partners, and in particular United States, meaning that we cannot take decisions separately from your decisions. So obviously your plans are the starting point for any plans in Europe. But number two, and this has been recognized by all ministers, we need a high-level political decision in Europe for what concerns human exploration. Because any significant contribution of Europe to a human exploration program will require additional budget. Because human exploration will never be developed, as I said at the beginning, to the detriment of science and applications to the citizens. So we need additional money for human exploration, and for that we need a high-level political decision. This is not just business as usual for the Director General of the European Space Agency. And the first high-level political conference on the subject is already planned in October this year, to say that, okay, we are serious, at least in the reflections. But at the end, the most important connection between ISS duration of life, and future human exploration is the budget competition. Every 3 years we shall have to decide where do we put the money to continue to exploit the space station or to make new developments for exploration. And the question is, can we afford to finance both ISS continuation and the development of future human exploration? And this is the reason why one important rationale to continue ISS, as I said, is to make it an integral part of the exploration program. At least to put that in the same rationale, instead of having a competition between the two. And this is the reason why, on our side, additional resources will be necessary to make the two. And also because, and that I am speaking as an engineer, you cannot replace operations by development or the other way around. It's totally different expertise, totally different industrial capabilities, and you cannot just stop exploitation and replace by development, or the other way around. We are speaking of totally different industrial activities and expertise. So before closing my statement, Mr. Chairman, I would like to come back to a very important characteristic for a partnership to be sustainable. A partnership is sustainable only if it is open to new partners. And we, the 5 partners of the ISS, we must address an important question. Shall we invite other partners? And I would like to mention China, India, South Korea, because they are part of the reflection on the global exploration strategy. Shall we invite them to join our partnership under terms and conditions that we could jointly agree, exactly as we have done in '93 when we have invited Russia? It was under terms and conditions that Russia has accepted. So I don't want to anticipate the answer. This is not at all my point today. But my point today is that not raising the question among the 5 partners would be the worst option. So This is what I wanted to say, Mr. Chairman. As I said, I am sorry that you have not received the typed version of that remarks, but you will receive that as early as tomorrow. And I thank you for your attention. And again, I am more than ready to answer any other question today or at any time you would like to listen to me. But thank you for your attention.
Well, thank you so much for your candor and for sharing your thoughts with us, for sharing the benefits of your experience. We're very appreciative. And let me check at this point to see, is General Permanoff on the line anywhere? General, are you there?
Okay, Mr. Permanoff is arriving, is coming, yeah?
He is coming, all right. See, General Permanoff, have you joined us?
Yes.
Yes, Mr. Permanoff is with you.
Good. Well, thank you very much for being with us. We have a large group here in Washington and a group on television, public television, or available to the public. And we would be very interested in your thoughts on the subject of international programs, the long-term future of ISS, programs beyond that, and anything you would care to share with us. We have allotted about 20 more minutes for this session, and so if you could make any comments, we'd be very appreciative. I'm afraid our communications are broken down. We may have to reschedule this for another time. General, are you able to hear me?
No, we're okay now. We'll have to start again.
По поводу текущего суммарного плана НАСА и Роскосмоса о пилотируемых космических полетах.
Now the view of Roscosmos on NASA current plan for human space flight.
В части реализации программы МКС для нас критичными являются вопросы транспортно-технического обеспечения станции, так как Роскосмос сегодня прилагает значительные усилия для обеспечения пилотируемого полета станции, включая ротацию экипажей, их спасание, доставку полезных грузов, в том числе по заказам НАСА.
Roscosmos critical to the ISS program implementation are the issues of technical and transportation support, because today Roscosmos is making substantial efforts to provide for crew rotation, crew rescue, cargo delivery, etc. And it is done partly for NASA interests.
Мы можем только приветствовать стремление НАСА ускорить разработку пилотируемой транспортной системы ОРИОН, нового носителя АРЕС-1.
Roscosmos can only
welcome NASA endeavor to speed up the development of the new piloted transportation system Orion and the new launch vehicle Ares-1.
Успешная реализация программы же коммерческого использования обеспечения Международной космической станции КОСМОС позволит также упорядочить процесс транспортно-технического обеспечения станции, сделать его более планомерным и настойчивым.
Successful implementation of commercial orbital transportation services for the ISS will allow to streamline technical and transportation support of the station and to make it more systematic and stable.
Программа пилотируемых полетов НАСА представляется нам достаточно сегодня сбалансированной и устремленной в перспективу.
NASA human spaceflight program looks quite balanced and promising to us. The next view graph.
Второй вопрос. Совместная работа с НАСА по МКС.
Next issue, cooperation with NASA in the ISS program.
Мы считаем, что сотрудничество Роскосмоса с НАСА развивается достаточно эффективно и устойчиво.
We consider cooperation between NASA and Roscosmos successful and effective.
В результате сотрудничества обеспечен пилотируемый режим полета МКС после аварии шаттла в 2005 году.
And the results are the following. After Columbia accident in 2003, the permanent crew presence on the ISS was ensured and maintained.
Осуществляется ротация международных экипажей на МКС, возможность их спасания в случае аварийных и нештатных ситуаций, доставка на станцию полезных грузов, их утилизация с учетом планируемого в 2010 году прекращения полета Space Shuttle.
The ISS international cruise rotation has been conducted, including rescue capability in case of contingency situations. The ISS cargo delivery and utilization has been ensured, taking into account the planned Space Shuttle retirement in 2010.
Завершено развертывание американского сегмента МКС.
ISS US segment has been completed.
После запуска очередного корабля в мае «Союз ТМА» экипаж МКС доведен до 6 человек.
The launch of Soyuz TMA in May 2009 increased the ISS crew up to 6 persons.
Полагаю, что накопленный Роскосмосом и НАСА опыт сотрудничества позволит перейти к следующему этапу в использовании станции, связанному с масштабной реализацией национальных программ космических экспериментальных исследований и использования МКС как международной космической лаборатории.
I believe that cooperation experience accumulated by Roscosmos and NASA allows us to proceed to the next stage of the ISS utilization, a full-scale implementation of the national programs of scientific experiments in space and ISS utilization as an international space laboratory. Next few graphics.
Третий вопрос. Желательность проводимых операций МКС за пределами 2016 года. Слайд номер 4.
Point 3. Desirability of ISS operation beyond 2016. View graph 4.
Завершение развертывания американского сегмента МКС, а также планы Роскосмоса по дооснащению в ближайшей перспективе российского сегмента станции позволят существенно повысить потенциал МКС.
Completion of the ISS US segment deployment, as well as Roscosmos plans to additionally equip the ISS Russian segment in the nearest future, will significantly increase the ISS scientific potential.
К 2015 году станция будет обладать уникальными возможностями по проведению космических экспериментальных исследований, осуществлению технологических разработок, реализации гуманитарных, общеобразовательных и коммерческих проектов.
By 2015, the ISS will have the unique capabilities for scientific research in space, engineering development, and implementation of humanitarian, educational, and commercial projects.
Учитывая данные обстоятельства, а также рекомендации, принятые в этой части на совещании глав агентств в 2008 году, мы считаем целесообразным продлить срок эксплуатации МКС как минимум до 2020 года.
Taking into account these circumstances, as well as recommendations approved at June 2008 meeting of heads of agencies, Roscosmos considers it expedient to prolong the ISS utilization term up to 2020 at the minimum. Next few graphs.
Четвертый вопрос. Планы России на будущее программы развития пилотируемых космических полетов.
Point 4, Russia future plans for human spaceflight program.
Перспективы развития российской пилотируемой космонавтики определены Федеральной государственной космической программой России на период до 2015 года, а также концепции развития пилотируемой космонавтики на период до 2020 года, а также рядом других документов, утвержденных правительством.
The prospective plans for the Russian human spaceflight determined by the Federal Space Program of Russia for the period till 2015, the concept of Russian human spaceflight development till 2020, and a number of other documents.
Основными целями пилотируемых космических будущих полетов являются освоение и эффективное использование околоземного космического пространства, исследование освоения Луны, Марса и дальнего космоса для решения глобальных задач на Земле и в космосе, генерации новых знаний человечества.
The main objectives of the future human spaceflight are exploration and efficient utilization of near-Earth space, study and exploration of the Moon, Mars, and deep space in order to resolve global problems on the Earth and in space, and to generate new knowledge for the benefit of the humankind.
Для достижения указанных целей предполагается в период до 2020 года завершить создание российского сегмента МКС и продолжить его эксплуатацию в составе слайды 6, 7, 8, 9, 10.
In order to achieve the above-mentioned goals, we expect to make the following steps in the time frame till 2020. First of all, complete the assembly of the ISS Russian segment and to continue its utilization in full configuration. These plans are presented in view graphs 6, 7, 8, and 9.
Обеспечить создание перспективной пилотируемой транспортной системы на базе пилотируемого корабля нового поколения, слайд 11.
Provide the creation of the prospective crew transportation system based on a new generation piloted spacecraft presented on view graph 11.
К моменту окончания функционирования МКС создать и обеспечить начало эксплуатации первых элементов орбитального сборочно-экспериментального пилотируемого комплекса на орбите.
To build and prepare for operation the first elements of the orbital assembly experimental piloted space complex by the end of the ISS life cycle.
Разработать элементы, технологии и ключевые системы перспективных межпланетных комплексов для полетов к Луне, Марсу, новых средств и методов медико-биологического обеспечения длительных пилотируемых полетов, в том числе межпланетных.
Develop elements, technologies, and key systems of prospective interplanetary complexes for missions to the Moon and Mars, new means and methods of biomedical support to ensure long-term human space flights, including interplanetary.
Пятый вопрос. Как мы видим взаимодействие с НАСА при проведении космических исследований?
Point 5. How do we see interaction with NASA in space exploration?
Накопленный Россией, США и Европой опыт создания и длительной эксплуатации пилотируемых космических комплексов, включая работы по МКС, позволяет сегодня приступить к реализации более грандиозных и масштабных проектов, в частности, к созданию пилотируемых средств для осуществления экспедиций к Луне и Марсу.
Graph 12, please. The experience gained by Russia, US, and Europe in the area of piloted space complexes, including the ISS activity, allows us to lead to the implementation of the larger scale projects, in particular the development of piloted spacecraft for missions to the Moon and Mars.
Роскосмос поддерживает необходимость включения к реализации крупномасштабных технического и научного потенциала других стран.
Cosmos support the necessity of involving technical and scientific potential of other countries, such large-scale project implementation.
Но для России приемлемым является проект с равноправным участием сторон, в рамках которого должно осуществляться партнерское деление результатами, а также участие России в разработке критических элементов, средств выведения, энергодвигательных установок, технологий и опыт обеспечения долговременного пребывания экипажа в всем пространстве.
Russia finds acceptable those projects which ensure equal rights of partners who will share the obtained results and also Russia's participation in the development of critical elements, launch vehicles, power propulsion systems, technologies, and experience of own long-term cruise life support space.
В этой связи я полагал бы целесообразным создать совместную международную экспертную группу для проведения всестороннего анализа возможности интеграции в области космических исследований.
In this connection, I think it would be advisable to establish the International Joint Expert Working Group to conduct comprehensive analysis of integration feasibility in the sphere of space exploration.
Шестой вопрос. Какие уроки извлек Роскосмос из сотрудничества по программе МКС?
Point 6. What has Roscosmos learned from the ISS partnership? Paragraph 15.
Первое. Роскосмос извлек, что необходимо дублировать, резервировать критические элементы проекта. Это ракеты-носители, транспортные грузовые корабли, центры управления полетами.
Any critical element in the project should have a backup, should be redundant. And such elements include launch vehicles, crew and cargo transportation spacecraft, and mission control centers.
Во время фазы эксплуатации должно быть обеспечено дублирование отдельных функций, таких как обитаемость, энергетическое обеспечение, частично целевые комплексы и системы.
During the utilization phase, the redundancy should be provided for the specific functions such as habitation, power supply, and partially the payload complexes and systems.
МКС могла бы стать уникальным испытательным полигоном для отработки перспективных технологий.
The ISS could serve as a unique test stand for development of advanced technologies.
Этот процесс объективно уже начался, будет усиливаться по мере роста нашего опыта и возможности автономного пребывания на станции.
This process has already started and will expand as we accumulate more experience and capabilities for autonomous stay on the ISS.
Уроки МКС показывают, что важное место в ее использовании занимает образовательная и популяризаторская деятельность, что очень важно для привлечения в данную отрасль молодых людей на всех континентах.
The ISS lessons show that educational and public outreach activities.
Шестой вопрос. Какие уроки извлек Роскосмос из сотрудничества по программе МКС?
Point 6. What has Roscosmos learned from the ISS partnership? Paragraph 15.
Первое. Роскосмос извлек, что необходимо дублировать, резервировать критические элементы проекта. Это ракеты-носители, транспортные грузовые корабли, центры управления полетами.
Any critical element in the project should have a backup, should be redundant. And such elements include launch vehicles, crew and cargo transportation spacecraft, and mission control centers.
Во время фазы эксплуатации должно быть обеспечено дублирование отдельных функций, таких как обитаемость, энергетическое обеспечение, частично целевые комплексы и системы.
During the utilization phase, the redundancy should be provided for the specific functions such as habitation, power supply, and partially the payload complexes and systems.
МКС могла бы стать уникальным испытательным полигоном для отработки перспективных технологий.
The ISS could serve as a unique test stand for development of advanced technologies.
Этот процесс объективно уже начался, будет усиливаться по мере роста нашего опыта и возможности автономного пребывания на станции.
This process has already started and will expand as we accumulate more experience and capabilities for autonomous stay on the ISS.
Уроки МКС показывают, что важное место в ее использовании занимает образовательная и популяризаторская деятельность, что очень важно для привлечения в данную отрасль молодых людей на всех континентах.
The ISS lessons show that educational and public outreach activities are very important for attracting the young people's interest to space.
В рамках программы МКС хорошо зарекомендовала себя структура международного управления станцией. Целесообразно это использовать для реализации международных проектов.
The ISS international management structure has already demonstrated its success. It would make sense to experience to other big national projects.
Седьмой вопрос. Как бы вы охарактеризовали обязательства России и США на этапе использования МКС?
Point 7. How would you characterize the Russian obligations and that of the U.S. to the ISS in terms of its operational life? Paragraph 14.
На наш взгляд, основными задачами России и США на данном этапе являются следующие.
In our view, the main tasks of Russia and the U.S. at this point are as follows.
Поддержание функционирования российско-американского сегмента МКС для выполнения национальных программ космических экспериментальных исследований.
Maintenance of operation of the ISS and U.S. for implementation of the national programs of space experiments.
Обеспечение пребывания на станции экипажа МКС.
Fulfillment of mutual provision for continuous habitation of the ISS.
Выполнение взаимных обязательств в рамках заключенных договоренностей.
Fulfillment of mutual obligations under existing international arrangements.
Поддержание наземной инфраструктуры для обеспечения функционирования МКС.
Maintenance of ground infrastructure for the ISS nominal operation.
Транспортно-техническое обеспечение МКС в соответствии с достигнутыми договоренностями с НАСА.
Transportation and technical support of the ISS according to the agreements achieved with NASA.
Участие в управлении МКС.
Participation in managing the ISS program.
Обеспечение эффективного использования МКС.
Provision for the ISS efficient utilization.
Мы полагаем, что США, как основной координатор проекта, будет способствовать улучшению стабильности и планомерности реализации программы МКС, в том числе транспортно-технического обеспечения станции, и создания необходимых условий для пребывания экипажа на МКС, совершенствования структуры управления станцией.
We believe that the United States, the main coordinator of the project, will promote stable and planned implementation of the ISS program, including the transportation and technical support of the station, the required conditions for the crew presence on board, improvement of the station control structure, and so on.
Восьмой, последний вопрос. Каким образом МКС и ее продление после 2015 года связаны с планами России в отношении использования пилотируемых средств и автоматов за пределами околоземных орбит?
Point 8 and last, paragraph 15. How does ISS and its extension past 2015 connect to Russia's future plans for human and robotic exploration beyond low Earth?
Как я уже упоминал выше, к моменту окончания функционирования мкс Роскосмос планирует создать и обеспечить начало эксплуатации первых элементов орбитального сборочно-экспериментального пилотируемого комплекса.
As I already mentioned earlier, by the end of the ISS life cycle, Roscosmos plans to develop and prepare for operation the first elements of the orbital assembly experimental piloted space complex.
Он станет основой для отработки технических средств для пилотируемых полетов к Марсу после 2030 года.
Will become a basis for engineering development for future human missions to Mars beyond 2030.
Очевидно, что создание такого комплекса невозможно без предварительной отработки в условиях космоса, его элементов, проверки принятых технических решений и используемых технологий.
Evidently, it is impossible to create such a complex without a preliminary testing of its elements in space and verification of engineering solutions and technologies.
Опыт эксплуатации МКС показывает, что использование станции позволяет решать уникальные задачи по продлению ресурса как элементов самой станции, так и автоматических космических средств, совершающих автономный полет, телескопов и так далее. Это является дополнительным аргументом в пользу продления программы МКС до 2020 года, а возможно и далее.
The RSS operation experience demonstrates that the station utilization allows to solve the unique task of extending the life of both station elements and automatic space instruments, space telescopes, etc., in autonomous. This adds another good argument in favor of the ISS program extension till 2020 and beyond.
Спасибо за внимание.
Thank you very much for your attention.
Thank you, Mr. Perminoff. Our chairman had to step out for a moment, so we have a couple minutes. We have a couple minutes until our next presentation. We're making a few adjustments on the fly, but for now, if any of the committee members have any questions for Mr. Perminoff or Mr. Dordan, if he is still there, now is the time. And we also have our head of international relations at NASA, Mike O'Brien. I think I saw him in in the audience, so if we have any questions for Mike, he can address those now as well. We are just waiting on Representative Hall, who is at Mass in Third, I'm told, on his way. So for the committee members, any questions for... Okay. Oh, go ahead, Chris.
Mr. Perminov, could you tell us a bit more about how experience using the station in orbital construction is or is not crucial to your plans for the orbital assembly of the space complex?
Не могли бы вы более подробно подсказать нам, чего? Ну, эксплуатационный корабль и монтажный эксплуатационный комплекс. Работа по этим двум направлениям, сильно ли они между собой связаны?
Да, конечно, эти два направления работ, они связаны финансово. Поэтому все вопросы в части создания нового пилотируемого корабля, я имею в виду российского, будут проводиться только в рамках выполнения международных обязательств России по созданию и эксплуатации Международной космической станции. Во главу угла будут поставлена задача выполнения международных обязательств по Международной космической станции.
I would like to note that the program of development of a new crew transportation vehicle is linked to the International Space Station program, and the link is mostly financial, because we will design the new space transportation vehicle taking into account all our obligations under the ISS program.
Question is Jean-Jacques Dordan still with us? Because we have a question for him.
Yes, go ahead. I am here.
Monsieur Zodan, this is Ed Crawley, a member of the panel. I was very interested in your comments about the need to consider utilization of space assets and their development in parallel. Of course, you made this comment with respect to the development of the ISS, but I wonder if you could comment a little bit more in general about how you might see developments going forward in such a way that they did not rely on a long period of development before a period of utilization.
What I said is, again, the lessons learned coming from the ISS. Yes, as I said, pushing back the utilization at the end of assembly complete is a problem, and has been a problem to keep the attractiveness of the space station to the user communities. And in my view, if we could have done, but again, as I said, the scenario which has been chosen has been chosen after the Columbia tragedy, and taking into account the restricted number of shuttle flights left, maybe it was not possible to do differently. But in an ideal case where we could have selected an optimal sequence, in my view, we should have chosen a scenario where we could have started utilization of the space station much earlier, taking benefit of the first laboratories which have been launched and that would have required shuttle launches dedicated to utilization before launches dedicated to assembly. And that was not possible. So this is the lessons learned from the space station. Now, for any future endeavor, including lunar exploration, our interest is to make sure that we shall not spend 10 to 15 years just to build infrastructure and to tell the users, in particular the scientists, that they have to wait for 15 years before having a chance to use that infrastructure. So we have to have a plan which, as I said, should include much shorter-term milestones and include also a utilization program at the earliest stage of the development of a lunar base. So now it may be simple to be said, maybe more difficult to be accommodated. I think that the 5 partners should work together to make sure that we are able to associate the user communities as early as possible in the development of a new lunar base or whatever endeavor that we are making together.
Thank you.
Well, I think we should not impose any more on your time, but on behalf of those of us here in America, let us thank both of you for your willingness to share your thoughts with us. We look forward to having an opportunity to visit with you again as we get further into our work. And should you have anything additional that either of you would like us to be aware of, we would certainly welcome any contact. So again, thank you very much, and we hope you have a very nice day, both of you.
Thank you very much, and again, we are at your disposal for anything that you would like to get from us. At least I am speaking as ISA, but I am sure that Monsieur Perminoff will say.
Very good. Well, thank you.
Norm, just a couple quick, or Mr. Chair, a couple quick comments.
Sure.
As I said, we're moving things around a little bit on the fly. We all know the cliche that rocket science is hard. Well, running a meeting on rocket science is also hard. We've hit our first...
I could note that we get images from Mars quite well.
Yeah, that's a good point.
But I won't.
With respect to the congressional hour, the leadership of the NASA authorization committees were invited to address the panel and or submit information related to the human spaceflight provisions of the NASA Authorizations Acts of 2004 and 2008. Unfortunately, due to the press of congressional business, a number of the members were unable to appear in person. The panel would like to acknowledge that the following members will be submitting statements to the committee for their consideration: Congressman Bart Gordon, Chairman of the House Science and Technology Committee; Senator Kay Bailey Hutchinson, Ranking Member of the Senate Commerce, Science and Technology Committee; and Senator David Vitter, Ranking Member of the Senate Science and Space Subcommittee. In addition, Congressman Hall, the Ranking Member of the House Science and Technology Committee, has submitted a statement that's going to be read by Congressman Pete Olson, the Ranking Member of the House Space and Aeronautics Committee. So we welcome Representative Hall, and we're ready for his presentation. And then following Representative Hall's statement, we are expecting Senator Bill Nelson, Chairman of the Senate Science and Space Subcommittee, to also address the panel at approximately 11:45. So amazingly, we're kind of back on schedule. So Representative Olson.
Thank you very much. It's a tremendous honor and an opportunity to speak before you. And just to show you, we're going to throw you another little curveball. Ken Monroe from Congressman Hall's staff is going to read his statement, and I'm going to give a very brief statement myself. But thank you all for coming today. Mr. Augustine, members of the Review panel, thank you for the opportunity to speak today. I was pleased when the administration announced the members of this panel. It's an incredibly successful and well-respected panel, and we look forward to your work. You all bring different expertise to the task, and I look forward to working with you during your review, as well as afterwards. in response to your recommendations. As I'm sure you're aware, your work is being closely watched within the space community, in the media, and particularly where I work, on Capitol Hill. NASA and human spaceflight have bipartisan support on the Hill, but unfortunately, too many of my colleagues are unfamiliar with the challenges facing our human spaceflight program. Members and staff are going to give tremendous weight to your findings with respect to the future of NASA should be taking. I know you take this responsibility seriously, and I know you understand the influence your review will wield. I understand you'll be headed to Houston, the Johnson Space Center in late July, and I look forward to welcoming you. The Johnson Space Center is the lead space center, as you know, for Constellation. The Constellation system, the Ares 5 heavy lift launch vehicle, holds the promise of returning America to exploring the moon. The Congress has endorsed that plan since 2005, and NASA has had a remarkably stable direction for the last several years. Our problem has not been a lack of vision, it's been a lack of commitment. I'm proud to represent Texas, but my concerns are not limited to my home state. The United States is the global leader in aerospace. Aerospace is one of our most successful export markets and the driver of much of our new technology. For the past 6 months that I've been in Congress, we have decried the loss of prestigious industries that were once dominated by American companies. I believe it's good policy to foster the creation of good-paying jobs, and we have worked to establish educational initiatives to promote a technical and highly skilled workforce. Human spaceflight provides all of those things. You all know this, and I hope that these points will be reiterated in your findings. Most of us who follow the space program know the impending problems, but there are other members of my on Capitol Hill who will soon be asking why we don't have our own independent access to the space station that's been primarily funded by the American taxpayer. The American public will ask, why are we paying the Russians as much as $50 million to take our astronauts to the space station? Others will ask why we didn't accelerate the development of the Constellation to narrow the gap following the retirement of the space shuttle. And as we all know, the gap will be very damaging to our aerospace workforce. The job losses are real, and they are jobs we're not going to easily get back. As our economy struggles to rebound, this kind of job loss will not be ignored. It should not happen under any circumstance, but I'm just reiterating the context of the work you're undertaking. NASA and our human spaceflight program, as we all know, we're at one of the crossroads. In 1962, before I was born, John F. Kennedy stood on the football stadium at my alma mater, Rice University, and we were at one of those crossroads there. And he gave us direction that we'd go back to the moon, or we'd go to the moon by the end of the decade. We faced another time in the late 60s, early 70s. We were trying to figure out what we were going to do after the Apollo missions. And President Nixon put us on a course to develop the space shuttle, which led to the space station. And now we're at another such time. No entity in this whole debate is going to have a bigger say than this commission. I wish this panel the best, and I look forward to working with you. If there's anything I can do to help, please let me know, because we must maintain our preeminence as the leader in human spaceflight. And I thank you again for the opportunity to speak with you, and again, wish you well, and look forward to seeing you down in Houston. Thank you.
Well, thank you very much, and thanks for your leadership on this whole topic, and I've appreciated the chances we've had to speak in the past about this, so we will be doing our best.
Yes, sir. Balls and strikes. We'll take care of the politics.
Okay.
Thanks.
Very good.
Mr. Hall regrets that he was not able to be here today, but I do have a statement that I'll read, and we would like the opportunity to submit more information for the record. I want to thank the members of this committee for the important work you are doing on behalf of the nation. I also want to thank you for the opportunity to share my views on the human spaceflight-related policies of the NASA Authorization Acts of 2005 and 2008. The views expressed here are primarily mine, but I know they are shared by a number of my colleagues. I think it is important to note that the first Authorization Act of 2005, Public Law 109-155, was the product of a Republican-led Congress, and the second Authorization Act of 2008, Public Law 110-422, was the product of a democratically led Congress. Yet in both cases, the intent was the same: to enable NASA to succeed on its current path toward completion of the International Space Station, utilize the station to carry out world-class research, retire the space shuttle after completing its remaining flights without the constraint of a predetermined date, and develop a new launch system capable of taking humans beyond low Earth orbit, a feat the shuttle cannot do, for the first time since the 1970s. In both our authorizations, we allocated more money than the administration requested because, in our opinion, NASA was being asked to do too much with too little. I am concerned that we cannot continue to be a preeminent spacefaring nation without adequate administration support and appropriate funding. One of the most important issues facing NASA, and indeed our nation, is the impending retirement of the space shuttle and the subsequent 5-year gap in independent U.S. access to the $100 billion International Space Station. With the NASA Authorization Act of 2005, Congress endorsed the development of the new spacecraft and launch vehicles, and I stress launch vehicles plural, with the goal of launching the new system, quote, as close to 2010 as possible, unquote. In the NASA Authorization Act of 2008, Congress established the new system as a priority by stating, quote, developing United States human space flight capabilities to allow independent American access to the International Space Station and to explore beyond low Earth orbit is a strategically important national imperative, emphasis added. And all prudent steps should thus be taken to bring the Orion Crew Exploration Vehicle and the Ares 1 Crew Launch Vehicle to full operational capability as soon as possible, and to ensure the effective development of a U.S. heavy lift launch capabilities for missions beyond low Earth orbit, unquote. As a result, the Act sought to accelerate the development of the new system by authorizing an additional $1 billion in FY 2009. Looking longer term, we are very concerned that the current budget request has eliminated funding for the Ares 5 heavy lift launcher and the Altair lunar lander, without which America is unable to explore beyond low Earth orbit. The NASA Authorization Act of 2008 also recognized the Space Shuttle's critical role in completing and utilizing the International Space Station and added one additional mission, if it could be done safely, to deliver the alpha magnetic spectrometer. As authorizers, we are concerned that NASA may be unable to complete the remaining shuttle missions, including the AMS flight, before the end of 2010. Unless the administration and the Congress provide funds commensurate with extension, the agency could be forced to take resources away from the development of the Orion and Ares, adding delays that could further jeopardize the 2015 availability and contribute to further losses of our highly skilled aerospace workforce. I, along with many of my colleagues, am not in favor of excessive government spending. But in this time of economic turmoil and growing international technological competitiveness, many of us are in agreement that America's space program is well established on a path that, if sustained, will ensure our role as the world leader in space exploration and exploitation for decades to come. By pursuing human spaceflight, we challenge our industry and inspire America to dream big and succeed. That is what leadership is all about. Other countries recognize the strategic importance of the soft power we gained in the world through our audacious leadership in human spaceflight. The political and technological stature of America has been earned through our space program, is now sought by other nations eager to demonstrate their hard-won capabilities to the world. The International Space Station in orbit today is a remarkable achievement, bringing together the scientific and engineering talents and resources of many nations. That achievement would not have been possible without American leadership. But such leadership is built on trust that we will keep our commitments to our international partners. If we continue to underfund our space program, we risk losing the international trust and credibility that is vital for long-term success. Today, nearly 70% of the world's population was not alive to see Neil Armstrong walk on the moon. Their opinions will be shaped by what happens in the future, not what has happened in the past. We should not be in a race with China or any other country. We are the preeminent leader in space. But leadership is temporary. We should ensure that we take the necessary actions to remain the leader in human spaceflight. I want to thank the committee once again for this opportunity to share our minority views. Thank you.
Well, thank you very much for reading that, and please express our appreciation for the letter itself.
Will do. Thank you.
Good. Is Senator Nelson here yet? Do we know?
I don't think so. He is on his way.
And do we have, see, we were getting a letter from Senator Kay Bailey Hutchison. Has that shown up?
No. They're going to be submitting those sometime this week. Mr. Chair,
We've got a plan B on that, but
Oh,
okay.
faxed over? Okay, thanks, Mike.
Well, somehow we're ahead of schedule here.
Mr. Chairman,
I think what we can,
you could go to some public comment.
that's what I thought. Yeah, it'd be a good idea. We can start the public comment session early, and then we'll, when Senator Nelson gets here, we'll break and hear his remarks. Do you want?
I've got some public comment information that we can go to and show on the screen before we pull everybody up.
Why don't you just handle the public comment session here yourself, and
okay. Let's
ask everyone to hold their comments to 3 minutes out of fairness to others who would like to comment.
Bring this one up. Is that coming up?
We have microphones, I think, in both aisles.
I just wanted to acknowledge some of the comments that we received via the website. We went live on the website on June 1st, and as of June 15th, we had almost 300 comments telling us what to do and how to do our work, so it was very much appreciated, and that was it was an excellent response. And all of those comments and suggestions are getting read. Again, the website location is http://hsf.nasa.gov. Don't need the www. Anyway, you can see the pie chart there. That's the breakdown of the comments grouped by subject matter. Constellation received about 10% of the comments. The comments were mixed as to keeping the projects and some suggesting canceling them. Most that were for keeping them asked that it be used to fill the gap between the shuttle and the next vehicle. And those that were recommending canceling these projects mostly discussed the cost and potential unreliability. The shuttle comments were overwhelmingly in favor of continuing the shuttle. Reasons fell into three groups primarily: keeping ahead of the world in space travel, concern that we would lose the drive or ability to return to space, and lack of confidence in following programs. Budget concerns, another frequent topic. Most of the comments showed an interest in increasing the budget for human spaceflight, or a concern in the recent cut in the NASA budget that was announced on the House side recently. We got a spike in comments right after that was done. The moon comments stressed the need to reach the moon again. Most of the comments on the moon were in favor of that, also mentioning the need for a base of some sort to allow for either mining or solar power collection. Mars, most of the comments related to Mars stressed the need to skip the moon, go straight to Mars, or to have at least Mars as the ultimate goal for human exploration. Other destinations, there was a grab bag of other destinations. Most of those were sort of beyond Mars type destinations. And then a number of science-related comments ranging from not wanting to explore space at all and focusing on Earth and Earth research to using space exploration to increase our technology here. Also concerned that space exploration would just be used as political gain and not for actual science. So there was a number of questions along those lines. And I pulled out some examples. These were just mine that I thought were representative of some of the comments. Sending a man to the moon again and onto Mars has the value of growth of ideas and enhances the spirit of the people. We have failed as a people if we let the space program go on without the human being stepping his foot on another planet. With a U.S.-based commercial manned launch industry now maturing, Constellation would be the last manned launcher built by NASA. I hope the committee will examine a new role for NASA as an enabling industry for American spaceflight entrepreneurs. launching men and materials to LEO aboard commercial spacecraft so it can concentrate its resources on taking mankind back to the moon and beyond. A comment from a NASA employee. I'm an engineer working for NASA at KSC on Constellation. I wanted to express my desire to see specific recommendations and plans for this study. I fear we may see the same old general open-ended inspirational message which has left our agency adrift for far too long. We need to have a firm idea about what our goals are and how to achieve them. We need specifics. And then the last one, I had to throw this one out. I just wanted to send a thank you note to all those on the panel. I trust you will make the right decisions with regards to a fair balance between human and robotic space flight without making human space flight, taking human space flight from us completely. So I definitely wanted to end on a thank you to us. And then just one other thought on the website. We are encouraging a lot of participation. We want you to visit the website. We're also Twittering on the website, and as of June 15th, we had 721 followers, which I'm told is a very good number. So, so keep following us. I think we are also Twittering some messages real time from the committee meeting. So when you get back to your computer, check those. Okay. Status on Senator Nelson?
Why don't we begin public comments? Do you have a list of people who would like to speak, or should we just ask folks to come up?
Right. Again, per my comments this morning, please come up to one of the two standing mics. We have one on both sides. Please limit your comments to no more than 3 minutes, and preference is for comments and not for questions. Norm, go ahead and call them out as you
Let's see. Sir, we'll begin on this side. Could you identify yourself, please?
My name is Greg Zittison, and first of all, thank you for doing this important work. My concern with going back to the moon is that there's a lot of interest in the vehicles and in the technology, but there's still not a very clear idea, I think, in public about what we're really going to do when we get there. And especially given the idea of the moon as a stepping stone to future places, I don't have a good sense that we have a real plan in place, at least not publicly discussed, that really addresses things like what are we going to do, how are we going to develop things that are going to make the moon a good stepping stone, what kinds of, for example, manufacturing on the moon seems to be an important part of using that as a stepping stone, being able to produce things on the moon. That doesn't seem to be coming up a lot. So I would ask the committee to please bear in mind also not just the technologies that get us to the moon, but also what are we going to do once we get there, because that's going to be a very important role, I think, of anything in terms of trying to sell this program and in trying to keep forward momentum going. Apollo petered out very quickly, in part because people got very used, once we got past the anticipation of getting to the moon, we got very used to seeing astronauts against a gray background doing the moment-to-moment work, and I think we need a very good vision of what we're going to do on the moon if we're going to sustain that. Thank you.
Thank you very much. Sir.
Good morning. My name is Osa Fitch, and I'm a private citizen of the United States. I would like to thank the committee for this opportunity to provide input into your review of the plans for U.S. Human spaceflight. As an American taxpayer with a technical background in aerospace, I care about the United States human spaceflight programs on many, many fronts. I'd like to make the two major points to the committee. First is that the vision for space exploration, I believe, is fundamentally sound, and as an underlying mission and rationale for NASA's involvement in human spaceflight, I'd like to see that continue. Second, NASA's Constellation program, as currently structured, is really on a path to failure, I believe, and it will not achieve the vision for space exploration. It's likely to continue to fail until it is fundamentally restructured. Regarding the VSE, any United States government human spaceflight program needs to be shaped such that it inspires all Americans and it does not compete with commercial enterprises. The VSE, with its focus on moving beyond low Earth orbit operations, meets this need in both of these areas. I support this vision, and I believe that all Americans support this vision if it can be executed in a cost-effective manner. Human spaceflight also inspires people all over the world. Regarding NASA's Constellation program, there are two basic problems that I believe need to be addressed. One, the system requirements have been set in a manner that does not account for any of the real-world constraints faced by a government-run human spaceflight program. The largest issue facing the country at this point in history is the current economic crisis. Any government-run human spaceflight program must operate in an environment of fixed or declining real budgets. Picking arbitrary mission requirements and then assuming that the budget will be made available to develop arbitrary systems to meet those requirements is in a monolithic architecture is unrealistic in the economic and financial environment we face today. Two, the Ares Launcher Development Program has basically run off the rails. It is developing two all-new and unaffordable launch systems. The Ares 1 program, even if successful, fundamentally duplicates existing launcher capability without adding anything new of value, but it does so at great cost to the taxpayer, and that cost is growing daily. The technical limitations of the Ares 1 launcher have had significant negative impact on the other areas of the Constellation program, particularly on the Orion spacecraft, forcing multiple redesigns and the elimination of many important spacecraft systems, including safety features and reusability features. The Ares 5 has grown into a rocket with little commonality with Ares 1 and almost no commonality at all with the existing space shuttle system, including infrastructure. Because Ares 1 and Ares 5 are two different launchers, the flight rate for each will be lower than if a single launcher were used for both missions, driving up costs. Because of the enormous size of the Ares 5 launcher, its flight weight will be very low, driving up costs for it even further.
Could I ask you to wrap up?
I'm wrapping it up right now, sir. Okay, I'd like to make 2 points as possible solutions. One, switch to a capabilities-based approach and leverage systems that already exist. Do it with minimum development to get to an architecture that can be scaled and grown over time. You're going to hear several presentations today, I believe, including EELV, direct, space shuttle side-mounted options. Any of these may take that approach. I urge you to give strong considerations to those. Second, focus on cost as an independent variable. We've got to understand that we've got a fixed budget, take what we have, put it together in a different way to achieve a vision that can be grown over time. I will go ahead and wrap it up here, sir. Thank you very much.
Thank you very much. Sir.
Hi, my name is Henry Fingerhut. I'm a student at Georgetown University and an intern with the NASA Academy program. I guess I had more of, an open-ended or, more nebulous, per se, question, but given, or a comment. But given the trend of, tenuously bound projects that NASA has taken up since the Apollo program, and the remarks of Director Jordan of ESA about the importance of continuity when rationale for a current project is still valid, I just think it's important to, more critically question whether Constellation fosters, or to what extent Constellation fosters a compelling public image of continuity or overall direction for the agency. I know Representative Olson mentioned that the problem is not a lack of vision, but a lack of commitment. But it's important, I think, to look into how that commitment is made such that the vision isn't compromised. And finally, I just wanted to mention that I think we should be looking into the extent to which we can look beyond Constellation to ensure that it doesn't become just another in a series of, more incremental, discontinuous missions, especially, for example, through the end of our careers as the next generation of engineers and scientists. So I guess that's really more broad-based than a lot of the other questions, but I think it's still important to keep in the back of one's mind as they make these decisions. So.
We appreciate your comments. Thank you. Sir.
Hi, my name is Ephraim Lanford. I just wanted to voice a slight concern about the committee's, authority and perhaps charter to explore the implications and possibilities of international leadership. So if the committee thinks that there are ways to use the space program to draw attention to or reveal or distribute benefits of international cooperation in broad areas like global markets, weapons non-proliferation, perhaps human rights in maybe a particular country that some are considering inviting to the ISS, or to global aspects of more space-specific questions that are kind of more traditional, such as education and inspiration or industrial base, then I hope that the committee will, I mean, you know, this is my opinion, but not be abashed to seek the, I guess, input or guidance that it needs at a high level to consider questions of high-level policy and diplomacy to explore all these issues to the fullest. Thank you.
Thank you.
Good morning. I also want to thank you, gentlemen and ladies, for the serving on the panel. I started my career in the early '60s after the infamous Sputnik, and been involved in the industry now for 45 years, thereabouts. And I think one thing that I've heard several times here regarding the extension of the constellation to Mars, it's certainly my opinion, and I believe it's the Earth to Mars that is really going to have the technological breakthrough. Of course, most of us have been to Mars, or not personally, but the Mars episode, I'm sorry, to the Moon. And I think it's the Mars that's going to get us the real big next step in technology. Thank you.
Thank you very much.
Mr. Chairman, I wonder if I might make a request. The committee is sincerely interested in a very broad base of input from the national community, and particularly from the youth. As we've already heard several references today, one of the principal political incentives in creating a broad-based human exploration program is inspiration of the youth. It's continually referenced, in fact, even interestingly in the comments today by our Russian colleague. So I would especially invite the youth of America to comment via all the appropriate mechanisms that only they know how to do, like twittering back and blogging. There are several blogs going on, and we'd really like to hear from the youth of America what would inspire them and how they would like to get engaged.
I think that's a great request, and we hope that those who are watching on television will heed that request. While we have a moment here...
Norm, quick update. Representative Nelson is here. I'm sorry, Senator Nelson.
He's here too.
God.
I do not see the senator. Where are you here?
Just got it coming in through the atrium, I believe. I can't believe I got all the titles to all the committees correct. That was my big goal. So.
He was a representative once, I think.
Yeah, that's true.
Here means here in Washington or here in...
Doc, is he in the building or is he just driving up? Oh, okay.
Come in.
Oh, he got waylaid. Yes, that's right. Thanks.
He's getting lobbied in the lobby.
Yeah, I think he is.
That's why we call it lobbying.
Bill, how about going out there and seeing if you can get some action here? You want to do that?
Doc, can you bring him in? We're ready to go.
There we go. We, as you know, we're going through comments from the folks from Capitol Hill that have an interest in this program, particular interest in it. Senator Nelson, of course, has a long and personal involvement in the program and has been clearly one of the great supporters of NASA and the space program. We're awfully glad you're here, and we welcome your thoughts.
Thank you, Mr. Chairman, and I'm going to move over here where I can actually see you all. instead of looking at the side of your head. I want you to understand the extraordinarily significant position that this panel brings itself to the table, because in essence, what you decide is going to be the significant influence for the White House and therefore also for the Congress in where the space program is going. And so I know you all know that, but I want you to hear from somebody that lives it every day that if you decide that X is going to be the case, the White House is a lot more likely to embrace X. And whether or not I or others disagree with X, it makes it much more difficult for us to be able to round up the votes in this kind of financial environment other than what you say is X. So you come to the table with extraordinary influence. And I know you all take the seriousness of this very much, but I wanted you to understand when we're dealing with a budget that is out of whack, as bad as it is, and I've just come from the Finance Committee trying to figure out what we're going to pass in the way of health reform, and of course costs are a major consideration. And so a lot of what, I wish it weren't this way, but a lot of where we're going with regard to our space program, which 10, 15, 20, 25 years down the line, we may not have wished we had made in the prism of financial restraints. But that's the reality that we're dealing with now. So for your consideration, I think that you ought to seriously understand that from this senator's perspective, in what the Office of Management and Budget have laid out for the President's plan in the out years of 11, 12, 13, and 14 are entirely deficient for where we're going. Now, part of your charter is that you are to lay out options, and you're also to be mindful of the fiscal restraints. NASA simply can't do the job that it's been given with the President's goal of being on the moon by 2020 if you take the OMB numbers. I have clashed swords with Dr. Orzag, who I have a great deal of respect. I have sat in prayer sessions with Dr. Holmgren, and I just want you to know that if you come out with those numbers, there's no way that NASA can be on the moon by 2020. There's no way that with those numbers that are coming, and there's nothing magic about those numbers. Those numbers were a group of folks who trying to come out with a president's political document, in addition to it being an economic document, about showing how over the next 5 years that you get the budget deficit down to 3% of the gross national product. But the president starts out crippled because he's inheriting what he thought was a $1.7 trillion deficit in the current year, but in fact it's going to be closer to $1.9 trillion. So understand the context in which that is. If you adopted those out-year numbers of the president's budget, which I'm trying to tell you is really not the president's budget. Therefore, that's all the more reason your panel is important, because the president is looking to you to really come up with where we should go in our space program. But if you adopted those numbers, we would have a 4 or 5 year gap with no American human rated launch system, and that would expand to 6, 7, possibly 8 years. And I don't think anybody wants us to continue in the circumstance where we are the only way to get to the International Space Station, which we built and paid for, to the tune of $100 billion, that we want to continue to stay in a multi-year period dependent upon the Russians. It's my hope that our foreign relations with the Russians are going to get better, but who knows what the geopolitics is going to be later on in this coming decade. So I ask you to consider that. I also ask you to consider that the last several years of budgets haven't been realistic. NASA was asked to do too much with too little, and that has led us to the point that we are now, with a space shuttle that's going to shut down, but without the new rocket having been developed in time to pick up where the space shuttle leaves off. And a series of budget documents over the last several years that in fact were unrealistic because they only went out to 2015 and played like the International Space Station was going to go away in 2015. Well, if it's taken this long to build it, and it is really a wonderful tool in foreign relations in the fact that it truly is international, and if we've spent $100 billion, I don't think we want to shut it down in 2015. And therefore, I think you ought to consider in your deliberations the continuation of that. Now, you all had specifically asked me to make a comment, and then I will sit down within my prescribed time about where we are with regard to the NASA authorization bill. We authorized NASA's funding for the next several years in a 2008 NASA authorization bill. And the policy of that authorization bill is exactly what I've just said. The funding was not what I've just said, but the authorization for funding is what I have just said. That the policy was to reduce the gap in human spaceflight capability, and also because of that, to mitigate the impact of having to lay off a dedicated workforce of highly skilled workers. And so you will see that the authorization for the current year, 2009, when you add the $400 million that we got in the stimulus for exploration, it actually brought it up to the funding, the appropriations, it all actually brought it up close to what the authorization was, which was $3.9 billion for exploration in the current year. Whereas what we authorized for space operations, which was well above the president's request, I'll round it, $6 billion. What was appropriated was about $250 million less than that. And yet you still have to launch the space shuttle. So appropriations just simply didn't match what was authorized. We got some help through the omnibus appropriations and the stimulus bill of getting additional money in. But other than that, the projections for the future in the President's budget are unrealistic. Just a couple of other comments on the authorization bill. We said science and exploration should not be in competition with each other. They're compatible. We clearly nailed down the policy that we ought to be prepared to operate the space station until 2020, and that we had to put it in because back then NASA was operating like they had two additional missions. They had some term. They called them contingent. And as we would bring the administrator in front of us, well, why do you call it contingent? Well, I can tell you Dr. Griffin didn't want to call it contingent. He was calling it contingent simply because the Office of Management and Budget was telling him that he had to. And so we said, well, why is it contingent? And basically it came out in the hearings that that was just a name. So you're looking at a full complement of space shuttle missions to fully assemble and to equip the International Space Station. And then we did one more thing in the authorization bill. We authorized an additional flight. And that was there are a bunch of scientific instruments that were going to be left on the ground that were configured to fly in the cargo bay of the space shuttle, but NASA wasn't planning for it. It wasn't NASA, it was OMB wasn't planning for it. And to the credit of the new president, this is one of the commitments that he made in the course of the campaign, and he has fulfilled that commitment by adding the additional flight, so that from now on there are 8 flights remaining of the space shuttle. The one other thing that the President has committed to is that although budgetary-wise, NASA, because OMB tells them to do this, is planning that the space shuttle is going to shut down by the end of 2010, the President has committed publicly that if we do not get the rest of the 8 flights up by the end of 2010, that we will continue to fly the space shuttle until those 8 flights, which includes the last one, the scientific missions, including the AMS, until they are all flown to complete the construction of the station and the equipping of it. So that could have some financial consequences. If we go into 2011, then additional monies are going to have to be generated, and I made sure they got on the record publicly on this, and not take that out of the rest of NASA's budget. So that's a summary, Mr. Chairman, of what I wanted to tell you. Now, I would just add one other thing, that NASA is now going to have a great leader. And this is someone that I worked very hard to get drawn to the attention of the White House and the President. And it has been a very happy day for me, and I think many others in NASA, in the space community, that the President has nominated, and I expect soon to be confirmed by the Senate, Charlie Bolden. I think he brings the quality of being able to be not only a strong leader with an enormous understanding of both human and unmanned space, but I think he brings the qualities of a consensus builder which is so necessary at a time like this. So with that kind of leadership, with the imprimatur of what you decide, which I think is going to be key as to where our space program is going in the future. With the two of those, we ought to be off on a good road ahead for the nation's space program. I am happy to entertain any questions or comments from you all.
Well, Senator, thank you very much. You certainly encapsulate, I think, the challenge that the space program faces. Your comments are very sobering to us. I think we well realize the responsibility we have, and you certainly sharpened that in our views. Do any of my colleagues have questions that you would like to ask? I've had a chance to visit with the Senator some in his office on this subject in the last couple of weeks, so I won't ask anything, but if anybody else does, this is the time. And I think that nobody has anything for you, so we'll just thank you so much for being here.
Thank you.
All the best.
Thank you.
One other thing before we take a break for lunch, Senator Hutchison asked that I read a letter. She had hoped to be here today, and as you heard, the transactions on the Hill have interfered with the best laid plans. And so I will read her letter into the record here. This is, as I said, from Senator Kay Bailey Hutchison. Mr. Chairman and members of the Human Space Flight Review Panel, I want to thank you for the opportunity to provide a statement in this hearing to underscore some of the recent congressional authorization activity that is relevant to your review of U.S. human spaceflight programs. You have a huge challenge and a critical responsibility, and I appreciate your willingness to devote the time necessary to conduct this review. The first point that should be clear from both the 2005 and 2008 NASA Authorization Acts is that they reflect a broad bipartisan, bicameral level of support for the U.S. human spaceflight programs. More specifically, both bills express support for the goal of returning to the moon to conduct the kind of sustained human exploration that was not possible in the Apollo program. They express support for completing the International Space Station and making the maximum possible use of its laboratory facilities for microgravity research across a broad range of science disciplines. The 2005 Act designated the space station as a national laboratory and began its evolution to a facility that not only could meet NASA's research needs, but those of other government agencies, educational consortia, and private research and development concerns. Both bills conveyed the concern of the Congress regarding the pending gap in the U.S. human spaceflight capability, a gap that would begin voluntarily with the end of space shuttle operations, mandated not by technical engineering, structural, or systemic issues, but by a zero-sum budget plan that would require transferring the funds being spent on the shuttle to the efforts to develop its replacement vehicles, the Ares launch vehicles and the Orion crew exploration vehicle. Both bills also demonstrated a serious degree of concern for the difficult transition from one launch system to the next and the potential impacts to the highly and in many cases uniquely qualified and dedicated people across the country who support our nation's human spaceflight programs, whether they be civil servants, contractors, vendors, or suppliers. The potential loss of many of these skilled resources represents a severe disturbance within the gathering storm that the chairman has clearly outlined in his most recent contribution to U.S. policy in these areas of science, technology, engineering, and mathematics excellence and competitiveness. It has long-term implications not only in places like Houston and the Johnson Space Center in my part of the country, but across a broad spectrum of the country's industrial capabilities and the vitality of its most skilled workforce. We must also not forget that America's leadership in space plays an important role in our nation's national security. We have already seen the preeminent role in space-based technology plays in modern warfare and intelligence gathering. Maintaining our efforts in human space flight is an essential part of sustaining the nation's overall space leadership. There's not adequate time today to give you more than this brief overview of the primary intentions behind the actions and legislation of our subcommittee and the Congress that I believe you need to be aware of and factor into your deliberations. My committee staff has prepared a collection of the relevant language supporting and related information from NASA, the General Accountability Office, and the Congressional Budget Office, and a broader description of the issues and concerns we have addressed and continue to address as we draft a 2009 authorization bill, which we will provide to you. My staff will be available to provide any further detailed information you feel is needed. Finally, I want to stress my belief that you must be able to consider any and all possible options and alternatives to ensure the continuation and future success of the U.S. human spaceflight programs. I believe it's essential for your review to be unconstrained by any binding consideration, whether budgetary or programmatic. We in the Congress, and I believe the administration, must be given a clear picture of what is attainable and what resources would be required. We will then be in a position to make the judgments necessary to achieve the best possible and most affordable result for the American taxpayer. Again, I want to thank you for your commitment to this enormous task, and I look forward to seeing the result of your efforts. I commend you for joining with this administration and my colleagues in the Congress to derive the best possible path forward to sustain an essential national effort to preserve our country's leadership in space. We now are actually, due to very good chairmanship, 15 minutes ahead. And we could take a break for lunch. And what I would suggest we do is start the afternoon session 15 minutes early, because I'm a great believer in having contingencies and budgets and schedules. I've received a number of notes handed to me from my colleagues as I had to walk out of the room for a moment, saying that you're freezing to death. And so I wonder if there's, we're not trying to simulate the Mars atmosphere here, but if it's possible, could we get a little more heat in here before we come back? And we will plan to meet at 12:45 to continue. Thank you all. Everybody.
Good afternoon. I'm Mike Haas from NASA, and I would like to take just a few minutes to kick off our afternoon session and explain some of the content that we have this afternoon. As I described early this morning, there are a number of studies, a number of concepts and alternatives that have been proposed by a variety of folks, and we have tried to get many of those fundamentally on the table today through all these presentations. So I would like to just kind of walk through kind of a quick look at this afternoon's set of presentations, Norm. And since you know I need to duck out early, I appreciate the forbearance so I can do this and duck out. The first set of topics that we'll start right as soon as I'm done is we called EELV considerations. And in that, we would ask NASA Lynn Klein to talk about our current use of the EELVs. We would then ask ULA, and I believe it's going to be Mike Gass, present ULA's activities as well. And then everybody knows, imagine that there has been an aerospace study going on about use of EELVs. Is that a surprise to anybody in the room? Okay. We have managed to get to where we can have a public briefing of some of the summary comments from that report. Gary Pulliam from Aerospace will talk that. We don't have a final report yet. We've had to do a public version of that report, and we're still in the final throes of clearance, but Gary is here, and he's going to give us the top-level findings of that. After that, then we're also going to talk about some of our other launch providers, and particularly talk about our commercial orbital COTS program. And again, in a similar fashion, asked NASA, in the first case, Doug Cook, to talk about the COTS program in terms of its demonstration program, ask both SpaceX and Orbital to talk about their activities, and then also ask NASA Mike Suffredini to talk about, now in the follow-on, the cargo resupply contract that has just been awarded. Same two companies involved, but have Mike highlight the process and the importance to the ISS program of that particular activity. Then to close out, there are a couple other that I would call alternative architectures that have been out in the public eye, the blogosphere, whatever we call ourselves, for a long time. And we did want to have some discussion of those for the panel to at least introduce those ideas. One is usually called direct, and we have asked Steve Mitchen to pitch for the direct team, so we'll hear that. The other one is that there's a variety of options that can be called shuttle C, shuttle side mount. The challenge of that is that the shuttle-derived options some years ago had an industry team that had been put together and was doing a lot of that definition, but that had tapered off as we had proceeded down the baseline. And so to try to get that on the table, I was in kind of an awkward situation of finding a spokesperson that could bring the most recent discussions and ideas of that. So I will admit that it looks strange, but the person that I could twist his arm into doing this is John Shannon. So I know it looks a little bit odd of having NASA propose an alternative architecture, but as it is the most shuttle-tied architecture, I have asked John to tie those pieces together, even though it represents thoughts of a lot of different NASA and industry components. So don't read overly much into the fact that I browbeat John into doing that. That's just the best way we could get that option on the table. So with that, I will turn it back over to the chair and for any opening comments, Norm, and then we could start with Lynn.
Why don't we go right ahead?
Thank you. Good afternoon. Bring up my charts, please. I was asked to represent NASA's current use of the Evolved Expendable Launch Vehicle. Next chart, please. I'm going to first just put that into a little bit of context. We have a NASA Launch Services program that was consolidated in 1998 at our Kennedy Space Center, and this is our acquisition arm and also provides our mission assurance and management for commercial launch services that NASA acquires for its missions. We don't own the vehicles, we buy commercial services in this case. We use a mixed fleet of vehicles, range of performance classes, and we support to the largest degree our science mission directorate with their programs, but also some other NASA directorates. For example, the LRO mission that's on the pad today is for Exploration Systems Mission Directorate. And we also do some launch services for other government agencies. We use a variety of ranges, including out at Kwajalein, at Wallops, Kodiak, as well as the well-known Cape Canaveral and out at Vandenberg. We have a contract mechanism known as the NASA Launch Services Contract. This is set up as a competition-based contract. Proposers for launch services on-ramp to this contract. We have a fixed price arrangement, and as we have a particular mission we're ready to purchase a service for, then we do a competition based on the mass, the orbit, the class of payload, and the best value to the government. We are in the process of extending that contract, so we have a longer ordering period because the current one expires next year. Most recently, we did a buy of launch services for 4 missions, tracking and data relay satellite, the radiation belt storm probes, and the magnetospheric multiscale mission. All of those were selected to go on an Atlas V. Some of the issues we're facing in launch services is loss of a medium-class launch service provider, which has been 50% of NASA's missions historically, particularly for science. We're in transition, and I'll talk about that just a little bit. We have a compressed manifest, And we're also looking to the future as how the infrastructure costs are shared across the government. Next chart, please. This is our current planning manifest that we have, and I'll just make a couple general comments. If you look at the small class at the top, you'll see that we have an oversupply of vehicles and an underutilization. If you look in the medium class, this demonstrates the transition period that we're in with the Delta II discontinuation, and since there's a bit of a lead time when we put out a proposal for our science missions, you've seen a shift over into that intermediate class. And if you look in those awards that we have given in that intermediate to heavy class, NASA is a strong user of the Atlas V. Next, please. This is just a snapshot of our history of launches with regard to the expendable launch vehicle. NASA's first use of Atlas V was back in 2002. I'm sorry, the first Atlas V was launched in 2002, and NASA's first use was in 2005 for the Mars Reconnaissance Orbiter. The first use of Delta IV, NASA has not had its own mission on it, but GOES was on Delta IV in 2006, and another GOES mission is on the pad right now for Delta IV for a launch scheduled for the 26th. And we've had a very, very good track record across our program, which was recently marred with the failure of a Taurus with the orbiting carbon observatory on board. Next, please. This is really just provided to the committee for reference. These are the small launch vehicles that are available to us to use. Next. And then this is the medium to intermediate and heavy class vehicles, and it gives you a sense of the range of capabilities that they offer. Next, please. I want to talk a little bit about some considerations. Obviously, for the EELV, given that range of vehicles, this being the highest performance class, it is at the high end of the cost spectrum as well. Another factor to keep in mind is that the Department of Defense currently covers the infrastructure for maintaining this EELV capability. The National Space Transportation Policy calls for a review no later than 2010 to evaluate the long-term requirements, funding, and management responsibilities and infrastructure. So that is something that we as a government will have to address across the agencies as to whether the current financial base will be the one we continue to use or not. For our science missions, going to EELV is required for certain missions, but it also in many cases is more performance than we actually need. And if we use that level, not only do we have the higher cost of that vehicle, but it also can increase the cost of the payload, particularly if they start growing to fill that performance capability. And the more we pay for launch services means the less we have available for science missions. So those are very closely linked in what we can accomplish in our program. With regard to infrastructure, we have a pad on each coast for each of the EELV vehicles available. We are finding recently that the payload processing facilities near the pads are limited and becoming a bit of a bottleneck, and we've been collectively working on how to deal with that. With regard to the industrial base, I'll just say again, we have an oversupply in the small class. We have some uncertainty in the medium class. You will hear about the Commercial Orbital Transportation Services Program and our commercial resupply services. So wearing my hat of overseeing the space station program, we very much want commercial resupply services to succeed, to help us to sustain the station, and wearing my launch services hat, I want them to succeed because those are very likely new medium-class vehicles that we can use for our science missions. So the station is becoming kind of a market, initial market entry for them, for us. There are questions in the industrial base about related to mergers and supply chain. There's always a tension between having parallel capabilities and merging things for efficiency. The question is, to what degree do you integrate or use the same components and gain those efficiencies? But then if you have a failure, do you have a fleet-wide impact where we're all grounded for a period of time? There's a line about multiple users risk approaches. That is to say that NASA, the Air Force, NRO, commercial customers, we each have our own way of looking at and assessing risk for our missions and what our fallback options are. For NASA, we have been in the mode, particularly with our science missions, of flying unique payloads, one of a kind, don't have a backup. Others may be doing constellations or a series of satellites, so they have a different posture, and that affects how we look at mission assurance, how much risk we're willing to accept, what kind of reviews we need to do. The schedule right now is a crowded manifest, especially for Atlas V. Again, we've been working collectively across the community to see what we can do to increase the throughput there. Just a couple things to think about if one were to go down the path of doing human rating on EELV. Given our use of these for all these other missions and different approaches to risk, would there be 2 lines of vehicles or 1? Would there be a separate infrastructure, or would we have to figure out how to share pads and processing facilities and so on? And to what degree would we have common systems that affect the fleet, or different risk assessments for human versus robotic missions? And so those are all just, I'm not giving you answers, I'm just giving you things to think about as you look at this. And I provided some backup slides that just shows you the history of the vehicles, but that was all I had to present.
Can I ask you a question, Lynn?
Go ahead, Bo.
When you talk about risk, do you mean like loss of mission numbers?
Yes.
Okay.
There are questions about are we ready to launch or not? Are you willing to go? Do you want to go on a vehicle that has a long history of successful missions, or are you willing to accept a higher risk and be a demonstration payload or an early payload on a new mission? Those kinds of things.
Yeah. Let me just follow up on it. You had on this table on page 5, I guess, low, medium, low for the risk. Do you actually use numbers like LOM, like our Constellation friends do, or do you?
We actually have a series of, we go by a set of categories where once a vehicle has been certified to a certain category, then we have our payloads certified to a particular category. So if you are, let's say, a Mars rover mission that we consider very critical, one of a kind, put a huge investment into it, then we're going to want to go on a vehicle that has a more reliable history or has been certified to a certain level. If you are a payload that's in a different category that's willing to accept risk, then we'll match it to a different type of vehicle. So it's not so much loss of mission numbers as it is trying to pair from the beginning which payload goes on what kind of vehicle.
Thank you. I think it's really great that you have, as an organization, worked out how to manage all this risk and put nationally critical high-value payloads on these launchers. How much does that mission assurance activity that you do contribute to the total cost of the mission?
That's a hard one to measure, I think. There was a study done a number of years ago that looked across NASA, Air Force, and NRO management approaches and looked at our respective track records and came to the conclusion that we were adding value through that mission assurance approach, but I think it's always subject to some level of judgment as how far you go. In our contract, we have put in place certain things where we want to just have insight, and others where we want some stronger oversight, given that they're not our vehicles, but they are our payloads. And so I think over time we've worked through that with our contractors as to what our respective roles are. Any other questions? All right, I'll hand off to my ULA colleague.
Thank you very much. Mike?
Thank you, Lynn, and thanks for those questions. So hopefully I have some of the answers. Norm and committee, first I'd like to thank you for inviting United Launch Alliance to speak at this public hearing. My name is Michael Gass. I'm the President and Chief Executive Officer of United Launch Alliance. Like many who will be here before you, I share a deep appreciation for the importance of human spaceflight for the American people and indeed the entire world. I also share an awareness that we are in danger of seeing U.S. leadership in space exploration erode for the lack of clear consensus on an affordable, sustainable, and executable plan for United States human spaceflight. So on behalf of the 4,000 women and men of United Launch Alliance, entrusted with the task of delivering spacecraft safely and reliably to space, I want to thank the members of the committee for taking on this task. It will not be easy. My intention today is to share ideas of potential credible alternatives and to encourage the committee to create the forums for appropriate technical evaluation of the options and assess against affordability, sustainability to support our nation's priorities and acquisition approaches for human spaceflight. Let me just once again add my commitment, my personal and corporate commitment, that whatever the committee's recommendations and the President's decisions are, you have ULA's full support for its execution. The constancy and purpose of the nation of a consensus is more important than any company's or individual's ideas. Next slide, please. Joint utilization of flight-proven systems by NASA, DoD, and commercial providers does provide a safe, affordable, and sustainable approach to exploration. Leveraging the existing investments will reduce annual standalone lean costs. ULA is proud to operate 2 state-of-the-art evolved expendable launch vehicle systems, which have launched 24 successful missions. These systems are utilized to support our most critical national security space assets and the most audacious civil science programs, including the Lunar Reconnaissance Orbiter that we plan to launch tomorrow afternoon. We have learned over the course of history of developing and operating complex space systems, it is a financially stable program, whether commercially stable or through government funding stability, that enables a strong systems engineering capability that leverages product evolution, that encourages test and flight trial repetition that leads to reliability, innovation, and cost efficiency. Human spaceflight utilization of EELV will only improve the cost structure and reliability for all of our national users and make the entire EELV industrial base infrastructure more internationally competitive. We have also learned that the fixed cost of maintaining and operating launch infrastructure creates a long-term lean and shapes the budget challenges of entire agencies or companies for decades to come. ULA stands ready to support the committee on evaluation of options that would leverage the existing national and private investments made in the EELV system for future human spaceflight. Delta IV Heavy provides a safe, low-cost capability to launch Orion, we believe by 2014, with greater than 20% performance margin. If tasked, ULA working with NASA engineers, the Air Force, and their aerospace support team, we believe the Delta system can support Orion with credible cost forecasts and schedules based on the recent development experience and meet the reliability needs for human spaceflight sooner than any other alternative. Many of the system improvements contemplated for human spaceflight are already part of a planned evolution to benefit our national security missions that we are currently planning and supporting. Further, we believe Atlas V provides commercial crew capability to ISS and potentially even earlier. We have supported several commercial entrepreneurs that found that Atlas 401 well suited for these potential ventures. The challenge was not the technical solution, but closing the business case and the inherent market and venture risk. Further evolution of EELV systems and components provides options and flexibility to explore the moon and beyond. One of the issues I observed from past exploration architecture is the tendency to allow a point design for launch systems lock you into an inflexible architecture. The Atlas and Delta launch systems have an inherent flexibility in their design potential. We have developed evolutionary incremental variants of these systems all the way up to 100,000 metric tons plus for consideration. Not only are there vehicle flexibility, but there's options available for manufacturing, integration, and launch operations to address workforce transition and unique requirements. The ULA is prepared to support the committee with a thorough evaluation of all these options. So let me elaborate on some of these thoughts. Next slide, please. The pictures represent our diverse capabilities of the expendable launch vehicle fleet. ULA is proud of our role in our partnership supporting national programs and cherish the intellectual capital that we are entrusted with that was gained in over 50 years and 1,300 flight experiences that were accomplished by our heritage companies, Boeing and Lockheed Martin, and the predecessor firms that were consolidated over the past decades represent this experience. This intellectual capital for launch is embodied in our current experienced workforce and in the proven systems for engineering and management that we operate today. The recent successful development experience of Delta IV and Atlas V were developed in the last decade. The ELV systems represent over $4 billion of government and private investment that were fielded approximately 4 years from the authority to proceed to their first flight. The key theme I want to emphasize throughout this presentation is the benefit of reliability through the flight trials of that fleet and a robust infrastructure that comes with a sustained business architecture. Next slide. This slide represents a building blocks for exploration, and it represents 3 important parts. First, we believe the nation needs to go forth with an Orion launch capability to have human space capability with a government-provided launch capability. We also think in parallel there must be a commercial crew capability. As I mentioned, the Atlas and Delta are potential, and there's many entrepreneurs thinking about entering that market as well. And it should be done in parallel, and the government should create an environment to support that. And the market that it should have is that support to the International Space Station from 2014 to that 2020 timeframe to give that market an opportunity to mature. And on top of that, we show the third leg of those building blocks is the heavy lift variants. In the recommendations that we put forth is that it provides time for trade studies on that future architecture. As we're focused on the Orion and the commercial crew getting capability, we have some time to hone the architecture and pick the flight variant that could be fielded to support the mission beyond the low Earth orbit International Space Station. As stated, we think the NASA could leverage the Delta IV EELV system to support the current Orion with a safe architecture, and the time that we outlined on the schedule is equivalent to the time that we put forth for the entire development of 3 different versions of the Delta IV system to its first flight. Next slide, please. We do not pretend at ULA to be the nation's expert in human spaceflight, but we have been involved with NASA in commercial human rating launch studies for the past 8 years. We've worked with commercial ventures, and we are an active participant with NASA on the Ares 1X program. We believe flight experience is key to human rating. Detailed understanding of the system behavior and environments is getting the benefit of understanding your system margins and inherent risks. With the flight experience, we'll be able to develop precise abort criteria with a robust emergency detection system that would fly on every mission, both human and non-human space flights. Non-crewed missions retire the risk prior to that first crew mission. And I put, it looks like a ruler on the bottom, but that's actually our flight experience that goes on in parallel with an ongoing development program. And our lesson when we developed EELV, to blend that experience of current flight and development expertise is key to that message. Starting with a highly reliable system, addition of the emergency detection system, and the leveraging some redundant critical flight measurements, the abort criteria can be developed, and matched with a good crew safety system, we will deliver that safe human rating. Next slide, please. Delta IV Heavy was launched 2 times operationally with 100% mission success. The Delta IV human rating requirements is well understood. I've talked about the EDS. We believe, as Lynn mentioned, a separate launch pad with a separate crew ingress and egress is required. We also will have a good handle on some additional reliability improvements that we would incorporate into the vehicle, and it would be synergistically required with our national security missions. We believe there's greater than 20% performance margin for both the ISS and lunar trajectories that allows us to provide the shaping to eliminate any concerns of black zones for abort criteria. The DoD RS-68 engine upgrade we are currently working on is the enabler that provides this performance margin. Liquid systems of EELV have the ability to create more benign launch and abort environments. The changes to establish the capability are minimum, and the improvements are synergistic. We think we can be available within 4.5 years with credible cost estimates. Next slide. I mentioned in the beginning about concept of operations, and I offer 2 examples. The 2 examples, one is basically the maximum synergy, where we do the human spaceflight utilizing the existing ULA infrastructure combined with the DoD program, NASA science, and our commercial endeavors. That's what we used in those cost estimates that I shared before on the previous slide, is based on example 1. Example 2 is the one that we'd look forward to support and to go into more detail about, which is about more of a separation where NASA has an integrated operation role of some unique infrastructure. And let me elaborate that. But before we do, these are only 2 examples of many different ways that we could approach the problem. And I want to just highlight the example 2 for a moment on the next slide. Example 2 is highlighted here with a map of the United States that has 3 things identified. The smallest dots represent locations of our industrial base, the key suppliers for the EELV systems, critical resources to the success of the program. The larger red dots represent the locations of our ULA facilities, and the yellow stars represent some additional facilities we would recommend in relationship to this approach. The approach that would recommend that we maintain detailed part fabrication and tank manufacturing in our Decatur, Alabama facility with use of a common supply chain from that industrial base that's represented here. We would recommend that NASA establish an engineering leadership team at the Marshall Space Flight Center, which is only about 15-20 miles from our Decatur facility, to make sure they're the focus for the human rating elements and the integration of the Orion vehicle. We believe when looking at the overall constraints and needs of the program, additional area would be required for a final assembly of this vehicle. We'd hope it would have the same underlying technical baseline, but providing 2 assembly areas for production rate, and utilizing existing facilities like NASA's Michoud facility is recommended on this slide. The third element is, again, that launch complex, whether it's Launch Complex 37A adjacent to our existing launch complex or utilizing 39, should be evaluated carefully for best operational activity. One of the things we talk about many times when we talk about synergism and this approach is the efficiency of use of resources, and resources typically is about dollars. I want to emphasize the importance of the human capital resource of our nation, and we need to find a way to be able to harness the expertise and find jobs on this program to not only ensure the appropriate transition of that experienced resource, as well as creating the opportunity for the next generation. And this would enable some of those great opportunities. Next slide. Let me talk a little bit about EELV for commercial human space. Again, we believe the requirements are well understood. We've been working with several of the companies, and they were nice enough to let us use their pictures of their potential spacecraft, and we gave credit for them at the bottom of the slide. I would want to also acknowledge that United Launch Alliance, as part of our consent order and our master agreement, we're in the launch vehicle business. We cannot be a provider of that upper stage service. We could provide launch services to companies that want to be the prime for that service and build those spacecrafts. So it's being a merchant supplier of launch, we're capable of working with many teams. We believe we can offer them a low non-recurring opportunity. Again, if human spaceflight is coming onto the expendable launch vehicle, we'd recommend a second launch pad, and with increased rate, having a competitive or affordable cost. Again, as Lynn mentioned, the characterization from numerous flights, both for NASA, the DoD, the intelligence community, and some commercial spacecraft, provides the data to characterize for future flight safety. EELV and the launch vehicle itself is not on the critical path to this activity. We believe we can have the vehicle ready long before the development and qualification of those spacecraft that you see depicted. Again, the challenge for ULA and the potential commercial operators is the non-recurring implementation cost for both spacecraft development and launch vehicle integration, and our EELV recurring cost. We are working with our DoD, NRO, and NASA customers to buy launches more efficiently for government use, and which would enable better value for the potential domestic commercial ventures. Next slide, please. I talked about the evolution of that enables a flexible mission architecture. This is a chart that was started during some studies with NASA back in the 2003-2004 timeframe that we've further honed after we became United Launch Alliance. The original studies were done as two independent program teams. We joked when we were forming ULA that we'd end up with the Franken rocket, and lo and behold, it's coming true that there's best of both qualities that are being integrated in our future evolution. The important messages of this chart is the modularity of the approach, that there's different breakpoints and opportunities for different architectures, that all of the steps have value to all the customers, and that they be flight used on many of our current NRO DoD missions. The first step that we always highlight is the upper stage. It's the area that can give us more performance, more reliability, and the development of a common upper stage with either improved RL-10 or a new upper stage engine is something first and foremost in our roadmap. The areas in blue are things that we could do using the existing launch infrastructure and current engine systems. The orange, which we call Phase 3, represents things that would require new launch infrastructure, and you know the brick and mortar of launch pads, flame buckets, and all the GSC is the expensive non-recurring element, and would need new propulsion systems. The key message for all of this is that there are choices and that there is synergy in its use. Next slide. We believe human spaceflight on ELV could potentially enhance safety, lower cost, by enhancing and leveraging the flight tempo of the existing programs. We also believe we can accelerate initial capabilities to support the utilization of the International Space Station. We can enable, if we do develop those savings, enable those resources to be applied to supporting missions to the moon and other destinations beyond low Earth orbit. We believe a the right policy, the right acquisition strategies will stimulate commercial spaceflight capabilities, and we think we have provided options to address workforce transition and the unique operational requirements of human spaceflight. Again, we are prepared to support the committee and NASA with the detailed data for the evaluations. I encourage an open and thorough evaluation of options which will lead to the best solution for the nation, and I thank you for your leadership in doing that. I'd be available to answer questions.
Yeah, thank you very much. I think we have time for one or two questions if folks have them. Okay, Leroy and then Wanda.
Yeah, thanks very much for your presentation. I was interested in some of the points you made. In fact, in the summary page, you said you were going to enhance safety and lower costs. And I don't know if you saw the morning's presentation from the NASA folks, but it seems to run counter to what they're saying about their Ares family. I wonder if you could comment on that.
I did not get to see the presentation, and that's fundamentally the comment about open and thorough evaluation. Clearly need to have their expertise of what's in the reliability, their numbers and assessments. The aerospace team has done theirs. To date, all of these studies have been done compartmentalized, and I think just getting all the experts in the room, potentially with the committee's oversight, would get at the heart of some of those questions.
Hi, Mike. You showed a chart that indicated you've got suppliers across the country, and one of the concerns that has been raised to us is about the industrial base. Can you make a few comments about, in your summary chart, you did not address that. Could you say a few words about what the impact would be?
Absolutely. Dr. Austin, thank you for that question, and apologize for omitting it. The number one thing that I talk about, matter of fact, this morning's meeting with the intelligence community and Department of Defense, we were talking about the focus on the industrial base. It really is fragile. It's fragile for many reasons, one of which is the work of this committee. Without the knowledge and the commitment of a human spaceflight, nobody's investing, nobody's basically planning it into their future. We already know about the budget constraints of the nation, spending in Department of Defense, but fundamentally, things are getting really lean in some of those major factories. We encourage the use of expendable launch vehicles as a strategic program. It does have some key needs over the next 10 years, and the nation right now is not even using that capability strategically. We're buying launches one at a time, so we're not able to use EELV to give some anchor tenancy in some of those supplier base and the knowledge for them to either make investments. The other thing that's going on in the supplier base is an overcapacity. We still have a overcapacity in many of our facilities. We have a challenge. As a nation, we love our competition and have lots of competitors domestically. But in this industry, we're dealing is an international competition. We need to make a decision: is our competition the global competitors, or are we looking to compete internally in this nation? If we do that, we're going to dilute our industrial base by spreading it around to lots of suppliers that don't have enough business to keep the robust processes that you need for space flight.
Let's do one more question, Bo.
Yeah. Thank you for your terrific presentation, but I have one question that has to do with the mainstay of structural design in human systems that I've been exposed to for many years has been use 1.4 safety factor, structural safety factor. Is Delta 4 and Atlas 5 designed to a 1.4 safety factor? And if not, how would you overcome that challenge?
The answer, well, you're on the right, and I think we're consistent with all of those activities. And as Lynn was showing in her criteria, those are some of the kinds of criteria you have in those mature systems. We have 2.0 factor of safety and design margin. If it's untested, we use 1.4 and 1.25 depending on its testing environment and some of the different the modes it's in. But clearly, using the industry standards of 2.0 for untested structure, 1.4 for tested is kind of our mantra. And if we take exception to it, it's noted with risk, and we have the appropriate mitigations on that. So we think our system is well characterized, well understood on those margins on not only structure, but on every component throughout the system.
Can I throw one more in there on?
Okay, one last one.
I'll be quick. among the industrial-based concerns is what we do for ongoing development capability for large liquid rocket engines. I notice that in your future growth plan, you've got the potential for putting dual RD-180s on the Atlas V. Have you looked at all at what it would take to do a modern F-1 RD-180, RD-170 class replacement as an alternative to just putting more of those on?
Yes, Jeff, and thanks for that question. The number one issue for spaceflight is, if you will, it's not United Launch Alliance or the system prime, it's our propulsion industry and our propulsion capability. The fact that our nation does not have a LOX hydrocarbon engine capability is a problem, and if there was that extra investment dollar, that is a key resource across the NASA civil and DoD that we need to invest in it. From a commercial standpoint, if you will, the business case doesn't close. The crossover point is great. We have looked at not only domestic, doing it alone, we've looked at joint partnerships, joint developments. You had, I think, Mr. Perminoff on from the Roscosmos early. We worked with his team on a potential of kind of an RD-181 joint development activity, as well as other international partnerships. But LOX hydrogen for a first stage booster has been studied over and over again, and it comes out the right answer, and the fact that we don't have good, robust domestic capability is a problem.
Okay. Thank you very much. We appreciate your comments. Let's see, I think the aerospace presentation is next, if I'm not mistaken. Eric?
Good afternoon, Mr. Chairman, members of the committee. My name is Gary Pulliam, and I'm pleased to present to you today the initial look into Aerospace Corporation's work on this important subject. A word about aerospace. We are a California-based not-for-profit company formed in June 1960, 49 years ago this month, to provide technical and scientific support to Air Force and other government space programs. And that's the job we've been doing for those 49 years. We've been a strong partner with the Air Force and a strong partner with NASA for many, many years, and we're proud of that fact. With regard to this particular piece of work that NASA has asked us to do, we've been looking at the subject matter of the EELV system as a replacement for part of the constellation profile for some time, even before it became a profile. We began an initial look back in 2005 after the President had announced his vision, but before the architecture was well understood, and at that point we were simply asked to determine whether or not the ELV could be human rateable, and at that time we decided and determined yes, it could be. Then NASA came out with its architecture and proceeded along those developmental paths. Then about 3 years later, late last year, we were asked to look at it again now that NASA had begun its development of its programs, and now that the EELV, particularly the Delta IV, had flown, and now that NASA had implemented some of its own policies with regard to human rating factors and other matters, we were asked to come back and take another look at the state of information regarding human rating of the EELV, and we presented that information to the NASA headquarters to Dr. Griffin and staff in December. And then following that, we were given this final task, which is the last bullet there. Next chart, please. And the scope of that study was now to get a bit more precise and to look at the programmatic and technical feasibility of using a Delta IV Heavy in lieu of the Ares 1 mission, and specifically to look at that in the context of the overall effects on the constellation architecture. And that's a really important point for our work. We looked at the capability of using the Delta IV Heavy in lieu of the Ares 1 to take humans to low Earth orbit, and what that means to the rest of the constellation, and the intended mission of taking humans beyond low Earth orbit. So we did not look at alternatives to the job that NASA's been given. We did not look at alternatives to the architecture. Our study assumed that you want to leave low Earth orbit, and to do that you need a big rocket, and the big rocket of record is the Ares 5. We also did not assess the confidence levels or the executability of the current Ares 1 cost and schedule. We took the program of record and the progress that was initially established for the program and used those for comparability purposes. As we began to look at those, we came up with several options. First, we started with the Delta IV baseline program, which is not presently human rated. And then we began to look at excursions around that to bound our study. In option number 2, we looked at taking the Ares 1 upper stage and its J2X engine and using those on a Delta IV. We realized that the J2X engine, as being currently designed, has a good deal more thrust than this application would need. So that led us to an option number 3, where we would still use the Ares 1 upper stage with its engine, but at a reduced, resized level of thrust to be more appropriate for the mission at hand. Then we began to look at other kinds of upper stages. In option 4, we looked at a redesigned upper stage with a cluster of 4 RL-10 engines, and then we looked at could you do this mission with no upper stage at all, just using the Orion service module for final maneuvering, and then finally, what about the HR human-rated Delta IV with just a single RL-10 engine. We did not look at the Atlas V simply because the Delta IV Heavy was farther along. It had flown. We had more comparative data, so we concentrated our work at NASA's direction on the comparison of Delta IV Heavy to the Ares 1 program. As we completed this study, here are some of the top-level key findings that we have. First of all, as we understood how NASA was implementing the human rating requirements into the Ares 1 program, we were better able to make a determination about how these might flow into a human-rated Delta IV program. We tried to be as precise as we could and as comparable as we could as we made determinations about the Delta IV human rating program. The configurations that have either the J2X engine as the upper stage or RL-10 derivatives are feasible, and they have significant margin in terms of cost, in terms of performance to both the International Space Station point and to the LEO point for the lunar mission, which is a bit more demanding. We also looked at the Delta IV human rated with one single RL-10 derivative engine. We found that it meets the Ares 1 performance margins, but it is closer, as you would expect, one engine instead of a cluster of 4 engines, but we did find that it had sufficient gross margin performance for that mission. But we suggest that if the committee is interested in that particular option, that we need to be more precise and more work is required on the exact profiling of the launch and the ascent profiles and the performance margins to those very important targets. We looked briefly at the no upper stage configuration using the Orion service module, and our estimation and our findings are that while it could make performance to the ISS target, we didn't think it could make performance to the lunar target, which has a bit more upmass requirements. So that was our findings on that. As we looked at the constellation impacts piece on this possible trade, we believe that the industry can accommodate whatever increase in production might come from moving the Ares 1 into the Delta IV EELV human-rated family. However, we're quick to point out that the industrial base includes the large solid rocket motor industrial base, and that becomes a concern as we thought about the overall architecture at large. We recognize that the Delta IV Heavy can use some of the existing Ares 1 hardware infrastructure, ground processing and infrastructure, and we tried to take advantage of that in our assessments wherever we could. You just heard from ULA that they preferred SLIC 37A. That would work. We actually preferred SLIC 39 a bit more, but both those options are attainable depending on which way you wanted to go and how you worked the ground processing piece. The aerospace recommended option is for the human-rated Delta IV Heavy with a cluster of 4 redesigned RL-10 engines. That gives an engine-out ability, which we think is important, and it allows a different kind of thrusting and orbit insertion, a different kind of thrust level than you would need with only one engine, and that became our recommended option among the 6 we looked at. It is important to recognize as well, and this plays into the remainder of our findings, once you make that decision to go with any combination of RL-10 engines, assuming, as we did, that the Constellation program is still the program of record, which means you need a big rocket, and that big rocket is the Ares 5. Now you have to deal with what are you going to do about the solid rocket motor industrial base, and who's going to take care of the J2X engine development. As you would appropriately determine, because both the Ares 1 and the Ares 5 use the J2X engine, then those developmental costs are borne by the Ares 1 program. So if that went away, now that burden of developing that engine shifts over to the Ares 5 program, and we'll see that when our cost findings show up here in just a moment. Next chart. So the story now moves from the technical ability to use a Delta IV Heavy human-rated in a number of configurations to accomplish the mission into what does it mean to the constellation at large. So we start out with the idea of we're talking about 14 flights to LEO, to the ISS and lunar orbit targets, and we're presuming that NASA's job is still to take humans beyond low Earth orbit to accomplish the Moon mission and eventually the Mars mission. So again, we did not attempt to change that architecture at all. If you went with one upper stage, one RL-10 engine upper stage, and delivery to those two orbits, we believe that you could save about $6 billion relative to the Ares 1 program of record. Remember that we believe the performance margins there are a bit closer than they would be with our recommendation of 4 RL-10s. If you move into our recommendation of the 4 RL-10s, we find the savings to be about $3 billion from the Ares 1 program of record. And if you decide you're really going to use the Ares 1 upper stage with the J2X engine on top of the human-rated Delta IV, we think the cost comes out about the same in that trade. But immediately one must recognize for all those options, there are some increases in the present cost profile for the Ares 5 program. Particularly if you choose an option that does not have the J2X engine, then those costs are going to shift to the Ares 5 program and have to be borne by it in order to have the J2X engine ready for that rocket. So we find that those cost uppers for the Ares 5 program would be somewhere between 1.1 and $3.6 billion, depending on which of these other options you choose and period of implementation and some of those details. If one cancels the Ares 1 program, NASA asserts to aerospace, and it was a given in our study, that it has to add back a substantial amount of funding in order to accomplish the constellation architecture mission as originally given to them. You can see in the final bullets there are elements of that number that NASA's given to us of between $14 and $16 billion. There are industrial base issues there. There are sustainment of the workforce issues. There are the increased cost of development of the J2X if you're now not doing that under the Ares 1 program. We've called out one of those elements in the middle bullet there about increased DDT&E cost of the Ares 5 program. Those costs might be partially or perhaps even fully accounted for in NASA's number, but the point is NASA has confirmed that if we went to the Delta IV Heavy, they believe at this moment that they would have a requirement for this much additional money back into the program to accomplish the mission they've been given. Next chart, please. With regard to schedule, we believe that human rating of the Delta IV is on the order of 5.5 to 7 years. That is aerospace's conservative estimate. No doubt there's some time in there to get started. The go-ahead for that would certainly not be today. And we've done conservative things as you would expect us to do as we contemplated historical times for human development activity, and we believe it's in the range of 5.5 to 7 years. We did not compare that in a date on the calendar to what Ares 1 is doing. We accept the IOC as presently given for the Ares 1 program, and this is simply a statement of how long we think this program would take. We think the ground facilities and the launch vehicle components actually are pretty close to the critical path. Both of them are going to take some amount of time. We think Orion need not be on the critical path because it's farther along, and if you want to redesign a new upper stage, you can shift the preponderance of that technical burden over to the new upper stage and try to disrupt Orion as little as possible. So we think there's a way to work that. With regard to the Ares 5 schedule, it again depends on programmatic and program management activities. With more time for the Ares 5 program, the schedule actually could be positively impacted. But if, on the other hand, NASA were to cancel the Ares 1 program and wait a long time before it turned its attention to the Ares 5 program, it could actually be damaged. So the opportunities there exist to actually help the Ares 5 schedule. We see nothing inherent about using a Delta IV Heavy that detracts from the Ares 5 schedule, other than one now needs to really pay close attention to this industrial base issue to make sure those capabilities are there for you when you need them. Same with the Orion schedule. NASA's indicated to us that if you move the Orion over to a new or redesigned upper stage, it might take as much as a year to revalidate, recertify, requalify the interfaces. Even if you're not redesigning that capsule, you need to now make sure it's going to fit on the new upper stage that you've decided to do if you put it on a Delta IV instead of the Ares vehicle. And we would say that in all cases, if such a decision were made, those decisions need to happen immediately so that planning can begin and long lead items can occur and all the things that would be required not to have that schedule slip. We were also asked to contemplate what effects might be on national security space. And again, it could be positive and it could be detrimental depending on your point of view. Certainly, more production of EELVs for more than one customer would serve to bolster supplier chain robustness. It would have the opportunity to bring down costs for all customers potentially. It perhaps would get suppliers and factories running back closer to the kinds of capabilities and capacities they had in mind when they designed those. On the other hand, as was mentioned by both previous briefers, you could wind up with two configurations of the Delta IV Heavy in the same plant. One would have to understand what differences those make if the human-rated Delta IV is a slightly different vehicle than the non-human rated, then those issues would have to be managed. We think they could be, and that would be easily accommodated. You could wind up with a single vehicle that accommodates both users, and one would have to really understand what the payload capacity is for that vehicle in light of all of the missions that it now has to do on behalf of national security space programs. We think that the idea of national security space and NASA working alongside could be managed to the good of the nation, but it would be something that everyone would need to pay attention to. And we think the pad and range issues, regardless of which pad you go to, are manageable and doable, as both presenters prior to me have indicated. So finally, just to reiterate, that the constellation architecture as designed by NASA in 2005 is an architecture, and it behaves like an architecture. The Ares 1 program feeds into the Ares 5 program. Developmental costs for engines are borne in the early part of the program and then used in both segments of the program. So when one starts contemplating replacing pieces of that architecture, all kinds of things begin to happen, as you see here. You see industrial sustainment cost, workforce issues, perhaps pad issues that you hadn't contemplated. So when viewing the particular small slice of can the Delta IV Heavy take humans to low Earth orbit for less money than the Ares 1, the Aerospace Center answer is, depending on which option you pick, yes. Quickly followed by, are you still going to build an Ares 5, and do you still want to maintain that infrastructure, at which time, frankly, the total cost of the total mission for NASA depends heavily on what NASA needs to do to sustain that program, should such a decision be made. Mr. Chairman, it's my pleasure to present this initial look into our work, and I'd be happy to entertain your questions.
Thank you very much. We've got, I think, just a couple of minutes if anybody has questions.
I have a question, Norm.
Okay, fine. We've got two here. I saw both.
You go first this
time.
Okay.
All right. I've got two, but they're quick. I just want to make sure I'm not misreading what's in here.
Okay.
The no upper stage option for the existing Orion capsule, that's the same service module that was already previously planned. Is that correct? And it just burns to do the rest of the Delta V. If it were true that we had the ability to do on-orbit propellant supply, then you could also do the next piece of the mission by putting the gas back in, right?
Looking at my expert across the room. Yeah.
Okay.
We didn't study it for this. But.
Okay, no problem. And the second very quick one is, you said that this 5.5 to 7 year human rating development time is based on the past historical experience, but the only past historical experience I can think of is when we put people on the original Atlas and the original Titan. What did it take to human rate those vehicles?
Can you help me, Ray?
Well, it went through much the same process. They had to look at things like redundant actuators on the engines, they had to look at structural margins, things like that.
But it took 5.5 to 7 years?
that. I think that those were done much more quickly under the circumstances, but we base it on what they have looked at for the human rating of other systems, but also it's just simply the development of recent space systems, how long it's taken, is part of what we looked at.
This is Mr. Ray Johnson, who manages our entire group for launch vehicles at the Aerospace Corporation. So it is a conservative estimate. We'd be delighted if it were less than that, but as we looked at the things that we think go into it and how long we would take, we came up with that band of 5.5 to 7. Yes, sir.
Yeah. A question, if you replace Ares 1 with Delta IV Heavy, production of solid rocket segments goes from, to support a shuttle, around 50 a year. For Ares 1, it drops down to some smaller number and then later picks up when you bring on Ares 5. In this scenario, and I don't know if you guys had a chance to look at that, if you, let's say, propose and get a Delta IV to fly to ISS, you essentially went to cease production of the solid segments until you ultimately start needing it for Ares 5. And the question is that possible? We are killing a country's capability to do those solid motors?
So you put your finger right on what we believe is one of the critical issues surrounding any alternative one might choose. And you've said
Did you have it in your briefing? Or not? I missed it, I guess. If you
we did do some work on that, which will hopefully be releasable when the more detailed work comes out. We do acknowledge, exactly as you've said, that now there are two primary manufacturers of solid rocket motors, and only one of those that is the manufacturer of large segmented solids. The Ares 1 is intended to have a 5-segment solid. The Ares 5 is intended to have a 5.5 segment solid. So that is all understood from an industrial capacity. If you cease building the Ares 1, then the big question becomes, do you still need to have the ability to produce segmented solids in a few years? And if you're going to build an Ares 5, the answer to that is yes. So then the next question becomes, how do you do that? And NASA can give you the particulars, but that is a key factor in that number that they believe is required of them to sustain that kind of capability over the years. So one can take excursions on other ways of doing the large rocket, but again, for purposes of our scope for this program, we did look at that. We understand that if you, from a capacity perspective, if you stopped building segmented solids for a while until you needed them, that the resultant capacity in that industry should be viable, but I'm not the person trying to run that industry. I mean, the other supplier of that industry operates at about the level that the first supplier would wind up at, but what happens to the people and the tools and the artisans and the techniques and the recipes and the strike and missile defense area certainly would not sustain both those suppliers. So we believe that if one is serious about moving away from the Ares 1, that there's still a bit of work to do there so that we really understand the effect of large segmented solids.
Yeah, just wondering if you had done any PRA for loss of crew, loss of mission using this configuration.
We did not consider that for this one. It was more of a technical cost and schedule feasibility study.
Okay, thank you.
Mr. Chairman, just an information request. Clearly, this 5.5 to 7 year human rating timescale is a very important timescale. I'd like to ask if we could be given by Aerospace more detail on the origin of that number, perhaps something in writing explaining the origin and detail.
As you might expect,
Thanks.
enormous technical underpinning to all of these, and while we're pleased to bring to you what is releasable today, we recognize that the committee might desire to get some of the details behind these. We'll be happy to do that.
Gary, I had a similar request. It relates to the industrial base backup data and the human resource backup data.
Be happy.
Thank you very much.
Thank you, Mr. Chairman.
Appreciate it. Okay, we will now talk about some more commercial launch capability options. And the first one we'll talk about is the NASA COTS program. I think Doug Cook's going to make that presentation. You'll make it okay. And we've got 4 presentations in 1 hour and a half. And so if I've done my arithmetic right, it says we've got like 20 minutes, including questions per each. So we'd appreciate that.
Right. I'll try to keep this short because it should give the companies a chance to talk about what they're doing. We in Exploration Systems Mission Directorate have the management of the commercial crew and cargo effort at NASA known as COTS. And I guess we're looking for charts, but that is something that we've had in place, and it's an effort that we're proud of. We can go to the next chart. You can point back, and let's go ahead and go beyond that. I'm going to talk about these subjects. Let's go to the next one. You can point back in terms of national policy in space all the way back to the original Space Act in its promotion of commercial use of space. More recently, in 2004, with the Vision for Space Exploration, also known as the National Space Exploration Policy, there was specific interest in promoting commercial participation in exploration. There was also talk about providing for pursuing the provision of transportation low Earth orbit by commercial capabilities. The Authorization Acts of 2005 and 2008 supported this, and so we've been on that path. If we go to the next chart. We established the Commercial Crew and Cargo Program down at Johnson Space Center in 2005 to lead this effort. It's a small office down there, and their objectives are to implement this space policy and to facilitate U.S. private industry demonstration of cargo and crew capabilities. A particular tenet of all this is that this effort is the development and demonstration of this kind of capability, and what NASA does in this approach is to invest in these developments. It's not a funded contract per se. These are Space Act agreements that we have, and we are investing in their capabilities. So as they move through them, and I'll talk a little bit more about how that's done. And so we have a goal of achieving safe, reliable, and cost-effective access to low Earth orbit and create a market environment for this type of capability. We go to the next chart. As a part of this, in the budget, we have had a $500 million bucket that we have applied to this capability, these investments. We have been through 2 competitions on this. We're actually, in terms of commercial crew and cargo, and in this case, it's cargo. We have 2 phases. The first phase is a development and demonstration phase where we are making those investments. The second phase is actually a procurement of these services once the capabilities are developed, and I believe Mike Sorfadini is going to talk about that second phase. In phase 1, in going back in history, in August of 2006, we selected 2 companies for funded Space Act agreements. One was SpaceX, and that was for an amount of $278 million over a period of years. We are still going through that. The money is tied to milestones and development of different types of milestones, both funding and technical. We also, at that time, selected Rocket Plane Kistler as a recipient at, I can't read the number, I believe it was $208 million, for another funded Space Act agreement. We actually terminated that later because they could not make the milestones, and then we had another solicitation in which we awarded a Space Act agreement to Orbital Sciences in February of last year. So in phase 1, we've had 2 different solicitations, and we now have 2 funded Space Act agreements on board that are progressing. And I'll leave the phase 2 procurement part of this to the final presentation because they'll talk about that in more detail. We go to the next chart. So this is a diagram that talks about the COTS effort and the types of capabilities that we look to. And you hear about capability, COTS D and that sort of thing. So what we have is we have COTS A, which is external cargo delivery and disposal. We have COTS B, which is internal cargo delivery and disposal. We have COTS C, which is internal cargo delivery and return of cargo in that case. And then COTS D is commercial crew transport. So when you hear these terms, that's what they represent. And when we had the solicitations, the companies bid against those different capabilities, and they did not have to bid against all of them. So we had different approaches to how this would be done. We can go to the next one. So we have, as I said, two funded Space Act agreements. The one we selected first that's still on board is SpaceX. They bid at $278 million for the cargo part of this, and also in that proposal, they proposed crew capability at $308 million. It is with a Falcon 9 vehicle, with the Dragon crew and cargo development. We are funded actually for only the cargo part, so that's the part we are currently pursuing. If we go to the next one, the next one is Orbital Sciences, and once again we selected this last year. This was a $170 million award, once again tied to milestone payments, and it has a pressurized module that's based on the space station MPLM, the logistics module, and it has a unpressurized capability, and they launch out of Wallops. The SpaceX rocket is at pad 40C at Cape. So both of these have demonstrations that they get to, and that is as far as COTS, this part of the effort, COTS Phase 1, takes it. So we're once again in development and demonstration, and we reach culmination of that as these capabilities are demonstrated. So if we can go to the next one. We do have two unfunded Space Act agreements at this point, one with Space Dev and one with Planet Space, and we do interact with them, but these are unfunded, so we don't. But they are Space Act agreements, and we work with them. And next chart. So the next two charts you can't read, but I can't either in this case, but and I don't intend to. But this is for the committee. And for reference, these are what I've got listed on the next two pages are the milestones and the plan dates for those as of the different revs of the Space Act agreements, and it actually shows the amounts that are awarded with each milestone. These are negotiated in the Space Act agreement, and so we're stepping through those at this point. And for SpaceX, we have awarded, I believe it's about $234 million out of 278 at this point, and with Orbital Sciences, we're at 100 out of 170. So these represent milestones in progress on these efforts. So this is the way in which we invest in these capabilities. So with that, I want to move on to just another short topic on this subject. The next slide. In the American Recovery and Reinvestment Act, exploration received $400 million. It's allocated to exploration. 150 of this is planned for the commercial crew and cargo effort, and it's shown delineated here. 80 million is actually for a solicitation in order to get proposals on developing capabilities that will make progress toward the crew capability. There's $42 million to accelerate the development of a docking system that would help in terms of the crew capability and support of space station. There's $20 million to advance some of the work in getting to confidence in the capability as a part of the cargo development. And then there's an $8 million piece of this that's allocated to working on collecting and putting in one place the human rating, a set of human rating requirements. Right now we have a human rating requirements document, but it has fingers into a lot of different requirements and standards across the agency. This would be an effort to try to make that a more collected
So we'll do that. Let's see. SpaceX is next. Elon Musk. Where's our SpaceX? There he is.
All right, I think just waiting for the slides to pop up. Well, I think, yeah, there we go. That's just a photo of Falcon 9 on the launch pad at Cape We'll be carrying cargo to the space station. We'll do our first test flight later this year, carrying our Dragon spacecraft, and then next year we'll be doing our first flights that actually go to the space station, carrying cargo to bring it back. Before I jump into this, one thing I think it's very important for the public to realize is that we're currently on a path to sole source human spaceflight to the Russians. I don't think this is really, people have quite realized this in the general public, but that's what's going to happen right after the space shuttle retires. We are sole sourced to the Russians and will be so until there is an alternative. We believe we can eliminate that gap or substantially reduce it at least, and I think it's be money very well spent to have an American entrant into that race rather than the current sole source situation. Next slide. SpaceX is about 7 years old. But the primary goal of SpaceX is actually reliability. It's not reducing cost, although we do reduce cost quite a bit as well. We're about 800 employees. We're growing 50% a year. We're in California, Texas, and Florida primarily. And really the whole purpose of SpaceX from the beginning has been human spaceflight. That's the very reason I founded the company and created it. So, next slide. We've been able to get a lot of customers on board SpaceX. So in addition to NASA and the Defense Department, we've gotten Sweden, Malaysia, Canada, a number of commercial providers, all of whom have done technical and financial due diligence on SpaceX and concluded that SpaceX is a wise bet and put down deposits for launch. Next slide. We reached orbit last year. With Falcon 1. The Falcon 1 is a complete ground-up development. So we developed the main engine, the upper stage engine, the structures, the avionics, the launch infrastructure, and launched a rocket with cryogenic propellant from a remote tropical island, which is not easy. So it's also important to note that there are huge lessons learned in Falcon 1 going to Falcon 9. In fact, much of the same hardware that's in Falcon 1 goes into Falcon 9. As far as the engine is concerned, I think there was some questions raised earlier about development of engines. There have only been 3 engines developed in the United States that have seen orbital flight in the since I think the space shuttle main engine about almost 30 years ago is when it was developed. One of them was the RS-68, which is used in the Delta IV. The other 2 are the Merlin and Kestrel engines developed by SpaceX, which are hydrocarbon engines. Next slide. Here you can see some pictures of Falcon 1 getting prepared for its next flight. It'll be carrying a satellite for Malaysia. Next slide. I'm going to go very quickly through the slides since we only have 20 minutes. We've made substantial reductions in cost across the board in our engines, structures, avionics, and launch operation. Again, I'm going to be re-emphasizing this many times. Falcon 9 is designed from the beginning to be a human-carrying vessel. Also has something which people have taken for granted in airliners, which is engine-out capability. So I think a lot of people would be uncomfortable getting on an airliner with one engine. And yet that's par for the course in rockets. In fact, in a lot of rockets, it's even mission fails. With Falcon 9, we've designed it just in a way similar to the Saturn I and Saturn V, which had flawless flight records. Which is, if you lose an engine, it doesn't matter, you can still complete the mission. Next slide. There's a lot of videos on our website if people are curious. Just go to SpaceX.com and you can see the engine test videos. This year, SpaceX will manufacture more rocket engines than the rest of U.S. production combined. In fact, more than any country except Russia. Next year, we expect to exceed Russia. Next slide. That's the base of Falcon 9. There's similar resemblance to the base of, say, Saturn I, which had 8 engines rather than our 9. Some pretty epic engine firing videos, some very funny videos on YouTube of the locals observing the engine firings. Next slide. Some pictures of our factory in Hawthorne. You can see our engine production line. Next slide. Here's Falcon 9 going through final qualification. We expect to be ready to launch Falcon 9 later this year. Hopefully we'll have the first and second flight stages on the pad by the end of summer. So you can see pictures of the factory in various stages of qualification. Next slide. I'm going to go very quickly. So there's Falcon 9 on the launch pad at Cape Canaveral. Next slide. More Cape Canaveral stuff. Next slide. There's Dragon. That's a full flight fidelity structural test unit of our Dragon spacecraft. Again, our Dragon spacecraft is designed explicitly to meet the NASA human rating standards. We're 90% complete on that qualification. It's worth noting that Dragon has 4 windows, I should say, and you don't need windows for cargo. Say the obvious. Next slide. Dragon going through structural qualification testing. The 2 driving load cases for Dragon are the worst case abort. So if the system aborts at the worst case and you have these reentry loads, you can be coming in at 15 or 16 Gs. So it's designed to meet those loads. It's also designed to meet the loads associated with a launch escape tower. Next slide. That's more SpaceX hardware. I almost forgot to mention our Draco engine. That's our in-space engine. So SpaceX actually does a 3rd engine, which is used for in-space maneuvering, primarily for docking and orbit translation. Next slide. More hardware. There's our heat shield on the bottom left. We developed the Pika X, which is an improved form of Pika in conjunction with NASA Ames. Next slide. More hardware. This is the communications unit for communicating between Dragon and the space station, and that will be delivered at the end of the month. It's quite a tricky thing to do. Also the crew command panel. Next slide. Our Dragon Eye, this is a LiDAR system that's used to image the space station as Dragon approaches the space station. It's got to figure out relative orientation and the approach vectors, and then plot a course to berth with the space station. That's going to get flown on the STS-127, which is currently on the pad. So it'll be tested before we even do our first Dragon mission. Next slide. We've completed the Space Station Safety Review Panel Phase 1 and most of 2. We expect to finish Phase 3 in early next year. It's important to appreciate that Dragon has to, even for cargo, Dragon has to be human rated for the approach to space station, for being at space station, and for leaving space station, because there are people in the space station. Next slide. We've done 14 of the 22 milestones on schedule, all financing rounds, and all design reviews through critical design review. There have been several major hardware milestones also in there. There's going to be some slips in the remaining milestones, but we're talking about slips that are measured in months, not years, which is relatively minor in the space industry. And so we're expecting to complete all of our demonstrations next year, by summer next year. Next slide. As I mentioned, crew capability is the very reason SpaceX was founded. So we will do whatever we need to do to make this happen. Yeah. Next slide. So one of the advantages of using the Dragon for crew is that it will already have been flown many times with cargo. So you have essentially the same vehicle, the same spacecraft, and the same rocket that it will have flown many times before you even put people on board. This is a huge risk retirement approach. So it's should be pretty safe by the time you even want to put people on it. Next slide. Regarding the factors of safety, again, we're designed to the 1.4 factor of safety throughout the vehicle unequivocally. The ELVs would require some work, at least in some places, to get to the 1.4. The Falcon 9 does not. It was designed from that for the beginning. So let's see. Yeah. Next slide. So in terms of what is necessary to go from the cargo Dragon to the crew Dragon, there's only one major development item, and that is the launch escape system, and that drives the schedule for completion of crew capability, and that is an approximately 24-month development cycle. So we've already done the preliminary design on that. We need to complete the design, qualify it, and test it. So that's 2 years, basically, from the moment NASA says go. It's about 2 years minimum to get that capability working. If you add some margin in there, you add another sort of 6 to 9 months of margin. That says, I think, comfortably under 3 years to get from today to get human capability. So that really eliminates the gap from our standpoint. I mean, I do agree, by the way, with having both Soyuz flights and COTS crew flights at the same time. It was planned for the same year because you want to make sure that there's no gap there. So I do agree with the approach of that Space Operations Director of NASA has to purchase Soyuz flights. I would do the same in their position. I just think it makes sense to turn on commercial crew capability and have it planned for that same period of time.
For $300 million.
We can also do what's called a lifeboat Dragon, which is just an emergency escape vehicle. We can do that a lot faster than we could do the ascent phase because no launch escape system is needed. So we could do the lifeboat Dragon in 1.5 years, which would improve the capability of the space station because our Dragon crew capsule is capable of carrying 7 people rather than the 3 people for the Soyuz escape vehicle. Next slide. So basically, there's a lot of value that's been delivered under the COTS program. I mean, if you compare this to almost any other space development program, you say, what did the government get for $278 million? Actually, I haven't even paid $278 million yet. $230 million. This would be pretty darn high on the list of highest value for money. So, yeah. All right, next slide. So, yeah, next slide. I think I've probably got like 2 minutes left. I think we've seen this slide. Next slide. So, COTS is really an enabling function for NASA. By having COTS, commercial crew servicing of low Earth orbit activity at an affordable cost, that really enables NASA to go beyond low Earth orbit, to go to the moon, to go to Mars, and maybe go to visit an asteroid. On the other hand, if NASA's budget has to be dedicated to low Earth orbit servicing, then that's all NASA can do. And the reality is that NASA is not going to get a giant budget increase. So it seems like the only way forward, the only way we're going to do exciting things in human spaceflight is if commercial companies handle the low Earth orbit stuff and NASA focuses on the stuff beyond low Earth orbit. Next slide. And that's it. Any questions?
Great. Elon, thank you. Other questions? Please, Chris.
Thank you. On one of your early slides on the Falcon 9, you included the statement that it has a greater than 5 times cost reduction compared to domestic competitors. I simply don't understand what that's trying to tell me. Can you elaborate on it?
Had an equivalent ELV, you'd be paying closer to 200 million, or just below 200 million.
Thank you.
Particularly when you factor in the fact there's Air Force infrastructure payments that have to be divided by those flights, which we do not receive.
You're right.
Thanks. Thank you for your presentation. Congratulations on your success to date. I had a question on Falcon 9 and Dragon. Assuming COTS-D goes forward, do you have a test program identified for Falcon 9 before you'd have confidence to put a crew on board?
Yeah, absolutely.
How many flights do you envision having for that test program?
Well, I think we'd want to have at least a dozen flights of Falcon 9 before we put crew on board. But that's not going to be a problem because, I mean, we have right now 21 flights on manifest already.
Okay, and I assume also you'd have a test program for your crew escape system.
Yes.
And would that be part of that test program? Would it actually, would you test that system off of Falcon 9?
Yeah, there are two major tests. There's the pad abort test, which we would not need the rocket for. That could be done at White Sands or something like that. And then there's a high altitude abort, which is really the same cost as a mission, if not slightly greater. So we'd want to do both those tests.
Okay, and then once you get a manned capsule, how many flights do you envision manned flights into orbit before you declare operational capability?
Well, for that we would consult with NASA. I think that would be as much NASA's call as, if not more, than ours. But I figure at least 2 or 3. Because there's very little difference between our crew versus cargo version, it's kind of a different situation than many developments before, which have been dedicated to crew or dedicated to cargo.
Okay, thanks.
I think that gets it. Thank you very much.
All right, thank you.
Appreciate it, Elon. We'll turn to orbital next.
Good afternoon, Mr. Chairman and members of the Commission. Thank you very much for the opportunity to present to you today and to the members of the audience that are here. Just a couple of words of introduction about orbital before I give you the status of our COTS system and our COTS effort in our cargo resupply service program. Orbital has been in existence for approximately 27 years. We've deployed over 500 systems into space, satellites and various other orbiting vehicles. We, in the last 5 years, have over 60 successful launches, and the company is continuing to move in many different directions to support spaceflight, both commercially and for the U.S. government. And we think that this is a fantastic opportunity for the commercial sector to demonstrate what they can do to support this country in maintaining human spaceflight. The next slide, please. The COTS architecture is basically 5 elements. The Cygnus visiting vehicle includes the service module, and of course on the front of that is the cargo vehicle. Currently we are contracted for 8 missions on the CRS contract, so we have changed our plan on the COTS mission from an unpressurized cargo module to a pressurized cargo module to demonstrate that capability end to end, including opening the hatch and transferring. The Taurus II is our launch vehicle, and I'll go into more detail on that in a few minutes. And then, of course, we have the cargo operations, which will allow us to work with NASA on the necessary cargo to sustain the station, mission operations to support the flight, and then the integrated launch site operations at Wallops Flight Facility. Next slide. A brief overview of the mission itself from launch. I know this is a very busy slide, but for your read ahead tonight, I guess, on the plane. It shows you the sequence from launch to rendezvous with the station, berthing by the station arm, and then unberthing and deorbiting to take the unwanted material from the station. Next slide. Taurus 2. Taurus 2 was originally planned by the company to fill the medium launch vehicle need in the nation. With the impending end of the Delta II program and the gap that we perceived between some of our larger vehicles, such as the Taurus and Minotaur 4 and 5, and the heavy lift vehicles, the company decided to embark on a development program that was named Taurus II. As NASA's plans solidified on the COTS and then cargo resupply service, Taurus II became the vehicle that we decided to use for that effort, and is focused on that now. The cargo resupply is its first 9 customers, and of course we are marketing to other areas to use Taurus II for supplying the needs of the nation as well as commercial customers. It will have a great deal of capability and flexibility. It's currently original missions are planned out of Wallops, but we can launch out of other places, as you'll see in just a moment. Dual AJ-26 engines based on the NK-33 engines from Russia, with a second stage provided by a Castor 30, which is a Heritage 120 engine. We are also working towards an enhanced second stage to fill the higher cargo needs in the out years, and talking to providers of that second stage at this point. At the moment, we are looking towards a liquid fuel second stage. It incorporates flight-proven components from leading global suppliers and uses subsystems that we've already deployed on other orbital launch vehicles. As you'll see on the next slide, we have a legacy all the way back to Pegasus of using those systems, enhancing them, and increasing their capabilities. And if you trace through the various legacies, you can see that it leads to Taurus II, using the leverage of our heritage and the many years of launch success. Next slide. The next couple of slides are a little bit busy, but it's just to show the comparison of the Taurus II projected performance to both low Earth orbit and higher. And next slide, as well as a comparison to other known launch vehicles in terms of environments and performance. Next slide. Payload accommodations. It's a 3.9 meter fairing, so it will accommodate most science payloads, and of course will accommodate the pressurized cargo module for the COTS mission as well as the CRS program. It's designed to maximize payload integration to make it efficient and effective. It will be integrated finally in the flow in a horizontal fashion. Will give us access to the payload until 24 hours before launch, and of course we'll maintain all the required contamination control and power requirements as we proceed to the launch pad. Next slide. Potential launch sites are listed on this pad. Currently we are working with NASA and the Mid-Atlantic Regional Spaceport to develop the launch capabilities for a liquid rocket out of Wallops. That has not been done before, and so we are working through the development aspects of that with a lot of cooperation from our partners in that. Wallops will allow us to reach the space station orbit without any problem, either from performance or trajectory. If we have payloads that we're going to fly in the future that require polar or sun-synchronous, we have other options, as well as the potential to launch out of Cape Canaveral should that need arise in the future. Kodiak is very interested in talking to us about launching from there as they develop a new launch pad there, and then of course Vandenberg is an option for high inclination. Next slide. The work in progress at Wallops Island is depicted on this slide. You can see a number of facilities that will be either modified or updated or built to support this activity. In the upper left, the cargo processing building exists on the main base now, and that will be used for the early missions for processing the payloads. And then we're looking at developing additional facilities on the island to process as well as to fuel payloads. The horizontal integration facility is a new facility that will be built in the next year to process 2 vehicles simultaneously, and then the transporter erector will carry the vehicle from the horizontal integration facility to the pad. The pad is the previous 0A pad that was supported solid rockets and now is being modified to support liquid fueled rockets, and we're installing a liquid fueling facility, of course, to support that capability. There are some modifications required to the pad, of course, to support the higher thrust as well as the transporter erector that will carry the vehicle to the pad itself. On the next slide, you see a depiction of how that will look in the future. In the center of the photograph up there is artist rendering of the Taurus II on the pad, and the flame bucket extends out towards the seawall, and so the ramp comes up from inland towards the launch site, and then the transporter erector will place the rocket on the pad approximately less than 24 hours before launch. In addition to the work at Wallops, we are working with Stennis Space Center on constructing an engine test stand that will support our program, the testing of our engines prior to launch. Next slide, please. That's a big hole in the ground, and that's where they are right now, in addition to some support structure. But getting that hole started and building the flame trench to support the engine testing was a big step in cooperation with NASA under a Space Act agreement with Orbital. That will be a part of our flow of the engines coming from Aerojet in Sacramento. Next slide. These are the AJ-26 engines. In the lower right, you can see the number of engines that are in storage. That's about half of them. And then the engines themselves will be processed, modified, and then shipped to Stennis for testing, and then on to Wallops for integration testing there and for launch. Next slide. The upper stage on the early missions is a Castor 30. The static fire of that is scheduled for this month, though I've heard it may delay till July. ATK is developing this as an offshoot from the Castor 120, and will provide us with a lot of capability in the early missions, and possibly some growth directly out of that engine. Next slide. The payload fairing tool gives you an idea of the size of the payload fairing and the dimensions, or rather the configuration of it. Next slide. The Cygnus visiting vehicle. It's a service module on the right-hand side with the solar arrays, and then on the gray on the left side is the pressurized cargo module. As I mentioned, we modified our plans on the COTS mission to move to the pressurized cargo module in order to demonstrate that capability once we were awarded the CRS contract, and all of our missions were scheduled to be pressurized cargo. Next slide. The PCM itself will accommodate the number of CTBs that you see up there. We actually think that we can increase the efficiency of the cargo stowage inside the module, and we're working on plans to do that now, to carry more CTBs as well as carry them more efficiently and more securely. We can also support powered payloads and hard-mounted payloads as required as the manifest shapes up. Next slide. The service module itself, in an expanded view, shows you the various components. It's fairly standard spacecraft components. They come from a variety of providers integrated by Orbital at our facility in Dulles and tested there. And then the entire spacecraft will be finally assembled at Wallops itself after integrated testing and environmental testing, which we also do at Dulles. Next slide. One feature of our vehicle is the prox system. Similar to Elon's Cuckoo, it will allow us to do the rendezvous and approach to the station. It's based on the same system that the HTV is using, so there's some legacy there, as well as the ability for NASA to to monitor the performance of both systems on both spacecraft and to learn from them, so that we can, as we move down the road, increase capabilities for providing cargo as well as other vehicles more efficiently and safely to the space stations. Next slide. The Cygnus will approach in free flight to a point about 10 meters away from the station, at which point it will be grappled by the station's arm and installed on the node, and the hatch opened for next slide, for unloading of the cargo. You can see it'll be berthed at node 2. We plan on being there for 2 to 4 weeks, depending on the requirements of the crew and how long it takes to unload, as well as to load it with the material that would be discarded during deorbit. Next slide. Just some pictures of the standardized bags that we'll be carrying for reference. Next slide. And then also, of course, we can carry both powered stowage lockers to a certain extent, as well as ice pack lockers that can be late loaded for scientific specimens. Next slide. Trash on the ISS. On the right-hand side, that's Carl Waltz. That's not the trash. The left-hand side is elements of the station crew presence that need to be discarded periodically from the station. Keteos and Yedeves, most of which are carried back on the Progress now, but with 6 people up there, they need to be discarded more frequently, and we hope that everything in them burns up before it gets back to Earth. But that will be a part of our job, is to help offload the hardware and waste from the station and dispose of it in the atmosphere. Next slide. And we did bid on and have the capability to develop both unpressurized and return cargo capability. We've not been tasked to do that yet by NASA. If that were to happen in the future, then we would get to work on that and provide that capability on a reasonable schedule, along with what we're planning to do today. We do think that the work that we're doing today is very important for the future of human space flight from this country. Maintaining an American presence on the International Space Station, a robust American presence on the station, and being able to supply them is very critical, especially with the transportation gap of the shuttle finishing its missions. Keeping that presence up there is going to be watched by the rest of the world, watched by our own industry and our own young people as they make decisions on where they want to go with their futures and whether they want to go into technology and whether they have a place to go in space. So even though cargo doesn't seem like a glamorous profession to be in to start with, it's just one of the elements that we have to maintain in order to keep people flying in space and to keep this country maintaining the space station that we've invested so much in. Next slide. To summarize the status of our COTS program, we've completed 10 out of our 21 milestones. The system-level PDR is complete, and Phase 1 of the safety review panel is complete, with Phase 2 coming up in about 2 months. We changed, as I said, from the unpressurized cargo to pressurized cargo, and then updated the Space Act to reflect that, and changed the mission schedule from late 10 to early 11 to reflect the additional work required to execute that. For CRS, we completed the first 2 milestones for the cargo resupply service, and the next major milestone will be the vehicle baseline review at L-13 months. And we are currently working the cargo manifesting process with NASA to ensure that we understand not only what they're going to fly, but how they want it stowed and how they want it unloaded and how they want it handled in space. Next slide. And this is an overview of our schedule, as I've already described it, and you can see the dates on there for reference purposes. Next slide. To summarize, I'd like to say again that even though it's not glamorous carrying cargo, it is glamorous for our people to be working on the human spaceflight program, and they're very excited about being a part of this, being a part of the International Space Station, and helping continue that mission, because we know that even as we are working to achieve other goals in space, maintaining our presence on the International Space Station keeps the interest up, it keeps the attention on space, and it keeps Americans flying. That cannot be overemphasized, I believe. evolving that capability to understanding what it will take to go further in space, to live longer in space, and to take those capabilities further out from low Earth orbit requires the delivery of this cargo and the delivery of the experiments. And we intend to do that successfully and to do it cost effectively and efficiently and most importantly safely. So with that, Mr. Chairman, any questions?
Thank you very much. Are there questions? I guess you've answered the questions. We thank you.
Get off.
For the briefing.
Thank you very much for your attention.
Let's see. Mike Suffredini is next, the ISS Program Manager, and will talk to us a little bit about commercial resupply services from his perspective.
Good afternoon, Mr. Chairman and members of the committee. It's good to see you guys here this afternoon. And just last night, or this morning early, I was sitting over in Florida hoping John would launch the shuttle so we'd get on with the rest of assembly. But anyway, we're going to try that again in July, and we're looking forward to it. Before I go on, I made a huge error. Elon reminded me in looking at his photograph of his actual hardware. I should have done the same with Space Station, but Frank's chart 25, if you look at it, that's not an artist's rendition of what ISS is going to look like. That is a photograph of the space station, and it is largely complete as we know it today. It is also manned as recently as late May with a 6-person crew, and so we're continuing on in that program. And of course, a very important part of that is the ability to resupply and to get utilization on board so we can utilize the vehicle that we built. And so I thought I'd spend a little time talking to you about that today. So next chart, please. Of course, we all know we are going to retire the shuttle. The plan is retired at the end of 2010. And what that left us with was a significant gap in our ability to get resources to orbit between the time it retires and at that time, the planned life of the International Space Station, which is our plan is to operate through the end of 2015 and then deorbit it in the first quarter of 2016. And what we ended up with through our analysis is we found out we needed about 60 metric tons of upmass. And when you look at the vehicles that we have today that are available to us or will be available to us soon, we have, of course, we all know the Russian Progress vehicle for cargo and the Soyuz vehicle for crew. We recently had the first flight of the automated transfer vehicle, which is the European contribution to PAYPAC, what we call Common Systems Ops Cost. And that's going to be 4 more vehicles, the first one plus 4. And that'll be each year starting in 10. So 10, 11, 12, 13 will have an ATV vehicle. In addition to that, we're about to fly our first H-2 transfer vehicle, which is the JAXA contribution, also as a payback for Common Systems Ops costs. That will be 1 per year through the life of the program, starting with their first flight, which is going to occur here in September. Now, all those vehicles together, flying through those times that I just told you about, we still have a 60 metric ton shortfall. In addition to that, and you've heard folks talk about today, we also have a need to get crew to orbit. Today, of course, the shuttle had done that for us prior to the accident. We kind of evolved to doing most of the crew transport needs with the Soyuz spacecraft, although we still, up into the next couple flights, we have 1 crew member that we do rotate on the shuttle. And then the future, of course, for now, shows us having to procure those seats until the crew exploration vehicle is available. And the first flight where we can take 6 crew to orbit and it stays on orbit as a rescue vehicle is currently the fall of 2015. We have procured Soyuz spacecraft through the fall of 2012 with the return in 2013, and so we do have a gap there that we haven't procured to date. Next chart, please. So this chart, you've seen it before. This kind of just shows you the different capabilities. A couple of points I would make on this chart. First is you'll note that no vehicle other than the space shuttle is able to return unpressurized cargo. And that was a significant change for us. That drove us to go to what we refer to as a build and burn philosophy. Prior to this time, we built a limited number of orbit replaceable unit, or basically spare components. And when they failed, the intention was to return them home and repair them and fly them back up when we needed them. The external ORUs are all very I would say all, they're mostly all very, very large components, very heavy, and there was no capability at the time or planned capability we knew of to be able to handle the external ORUs, and in fact that's holding true today. Nobody is planning to do a return capability external ORUs. In addition to that, you'll see if we hadn't gone with the commercial resupply services contract, that there wasn't even a capability to bring a significant amount of pressurized cargo home. The Soyuz does bring home a little bit per our contract. For each seat we get about 17 kilograms in a very confined space, so we can bring home some samples, water samples, experiment samples, but it's fairly limited, and so we needed that capability as well. Now the HTV does have, it was at the time, but before CRS, HTV was the only vehicle that also had an upmass capability for her external ORU. So now we still have to get the spares to orbit. HTV was going to be the only capability to do that. And this is something we also got more capability with the CRS contract. So you can see just that chart alone will kind of makes you realize how big of an impact losing shuttle did to us. Now you have to remember, much of the shuttle capability, the whole program was built around assembly, and of course much of that capability that we utilize on shuttle has been for assembly as well. So it's hard to compare apples to apples on this chart just from pure upmass standpoint. Next chart. So all of this drove us to go into a procurement of a capability to take care of the remaining 60 metric tons that we had to procure in order to operate the ISS through 2015. I won't go through all these charts, but we did do a lengthy process to involve the industry early on to understand what they could and couldn't do, what was reasonable to expect. We were into a fixed price contract. We wanted to understand the application of that capability. All that drove us to an RFP on April 14th. And you can see down here at the bottom, it showed you basically what we put in as the need that the RFP was trying to fulfill. You'll notice it has upmass, both internal and external. It has only pressurized return, because that was the only capability we thought we could get in a return capability, and then this disposal down mass, which is just a nice way of saying trash, Frank mentioned earlier. Next chart, please. This chart, we spent a lot of time trying to decide what we could do and when we should do it. This chart is showing, it says it here in the title, using 2008 historical scheduled date. So in late 2007, we were trying to decide when to do the procurement, and this chart just kind of shows you. At this time, RPK was out of the picture. The COTS Phase 1 second re-award, if you will, hadn't taken place, so we knew what the SpaceX plan was going to be. We also knew from talking to our JAXA colleagues that they needed about a 36-month lead time to build an HTV. If we asked for one, they need about 36 months. And of course, we need additional time just to do the negotiations before the 36-month clock started. In addition to that, we found in talking to industry that it would probably take about 2 years to get any vehicle that we wanted. So if we ordered, we had to always order about 2 years in advance. And that's been true for the Progress vehicle as well. It's a pretty standard time. The human-rated spacecraft tend to take a little longer, and that's also borne out from our purchase of the Soyuz spacecraft. But in any event, 2011, early 2011 is when we decided was the deadline to have capability to orbit, and I'll talk a little bit about the challenges associated with any movement to the right of schedule here in a minute. But that drove us then to do the acquisition when we did. Next chart, please. This was going to be a new way of doing business, at least for us anyway. We're used to doing cost-plus contracts, controlling every aspect of the process, and we also are fairly hands-on, even in ELV land, in terms of what we watch and what data we get back, and we even give a go at launch time. And we were trying to change to a little more closer to the type of fixed price contract you'd expect. It's an end-to-end service type contract. In all these cases, we supply an ORU or a bag of supplies to the provider, and the provider gives it back to us when we get on space station. And so it's an end-to-end service. Now, To the extent we could let go of the launch vehicle we have, we've got relatively hands-off in terms of the launch vehicle prep and what they have to do to ensure mission success. There's still work they have to do working with the range and FAA to ensure safety for the people on the ground, but once you get past that point, it's really up to these contractors to ensure that they're going to be successful and get to ISS. And then we have this sphere around ISS, about 2 by 2 by 4 kilometer sphere around ISS, and anything that the spacecraft does inside that sphere, including the burn to get to that sphere, then is a little more tightly controlled, more like you expect NASA would do. But it really was only from a safety aspect. Anything to do with mission success, we took off those kinds of requirements we normally apply, and we applied just the requirements having to do with safety in order to ensure that we would be safe. But the whole idea was to put the monkey on the back of the provider to get to ISS and try to take some of our work out of that process. So it's a contract for fixed price, as I said here, for the internal, external upmass and the cargo return and cargo disposal. And in the end, we ended up selecting 2 vendors inside this contract. We had the option to select 1, 2, even could do more than 2 if we chose. Of course, more than 2, you'd run into a problem of having enough business to entice a contractor to play. We felt like we needed at least 2 because in the cases of what were proposed to us, it was all new vehicles. And so we felt like we needed some redundancy there to hope that if 2 applied, we would, of course, hope both will be successful, but if they don't, we still have a chance that 1 might be enough to keep us going until we get other capability to orbit. Next chart, please. So this is the result of the task order after we awarded the contract in late December. In about the March timeframe, we sat down with both companies and did what we called our task orders, and this is basically how the flights worked out. We picked year and month and kind of laid them out, and then as we get closer in, within about 2 years, we'll do ATP, and in about 18 months, then we'll actually select the launch date and a 90-day period that they have to launch within. And we'll agree to that at this vehicle baseline review that has occurred in one case and is to occur here shortly, as Frank mentioned. Next chart, please. So this just kind of gives you a sense of the 2-year window and how the flights line up. The red X's are the actual launch dates, and then the bar there is the time from ATP to launch. And it just kind of gives you a feel for where everything lays out. Remember, I told you the beginning of 2011 is when we wanted to be able to have cargo to orbit, and the current plan for the COTS part of this process was not to carry cargo to ISS. So the first cargo on either of the 2 vehicles was going to be on the SpaceX vehicle in late 2010. So when we made the award, we were already kind of late relative to our needs. Next chart, please. So I won't get into too much detail on these next 2 charts in order to save time, but you can kind of see the milestones that are listed here. We're coupled very closely to the COTS effort. The COTS program really manages the relationship with Orbital and SpaceX. All of the integration work, all the requirements, all of that is supplied by and verified by the International Space Station program, and that ensures that when the COTS fly occurs, and if it is successful, then transitioning to the CRS flight should be relatively seamless. Next chart, please. And this is just the specifics for the orbital flight as well. You'll notice there's a little bit of difference to orbital, and Frank mentioned it. They have a solid second stage early in their program, and after the first couple of flights, they go to a liquid stage, which provides more performance. And as the last 2 bullets say, really, this is a challenging business at best. It is a very difficult business. We all in this room, most of us in this room, have a lot of experience with this, and no matter how well we plan and how hard we work and how much money we put into it, there are always challenges to overcome. And even once you become operational, until you've flown a few times, you're still going to have challenges making schedule. And so we believe that even once we do the VBR, we need to be prepared for slips as much as 3 to 6 months and maybe more. Next chart, please. So this chart is an attempt to show you what the logistics are on board that we have to provide for on the International Space Station through the end of 2011. And I'll try to talk to you a little bit in large detail here. The green line is the crew supply, so that's water, food, clothing, all the things that the crew needs to survive. The orange line is the consumables, so those are filters, tanks, those big tanks you saw Frank show, those kinds of things are the consumables required to operate the systems for the crew. The dashed purple line is the utilization requirements, and you can see even today with the capability we have because of assembly, we're challenged early in 2010 to meet the needs of the utilization crowd. And then finally, the light gray is corrective maintenance, and so even as we plan today, we're relatively challenged to do the corrective maintenance. Now that's not a bad thing. This is all based on mean time between failure. Our mean time between failures on the majority of our components have been very friendly to us, and as you can expect early in the life of the space station, these systems are relatively young, and we would expect that we will continue to have positive performance from the hardware relative to failures. However, as the vehicle gets older, you wouldn't want to carry this kind of challenge because you can expect more failures as they get closer to their design life. Now, what we have done in the program to try to mitigate the risk of the potential for these vehicles to move to the right are two things. One is you see the dots that represent both the demo flights, the demo flights that actually berthed to the ISS, so Demo 3 for SpaceX and the single orbital demo. And then you see the first couple of flights for SpaceX there and the first CRS flight for orbital. None of that upmass is accommodated in that chart. So what that chart tells you is we could probably keep the ISS flying and utilize it the way we expect to utilize it through about the end of 2011. And at that point, if we don't have some upmass from one of these systems, we're going to be challenged to continue to utilize ISS in the long term. Now, I'll tell you a couple things. One is, of course, I told you that we haven't accommodated any upmass, so I haven't assumed any upmass from any of those vehicles. And second of all, even though the demos today are not intended to carry flight hardware to orbit, one of the things we're looking at is we want to make sure the demo is as realistic as possible. In order to do that, we believe we should manifest those vehicles as if they're flying as real vehicles, and it's all about how you pack it and how you're going to, once you get it to orbit, how you're going to unpack it and how you're going to fill it back up with trash. And so we believe that we have rationale to go ahead and manifest flight hardware on the orbit from the demonstration flights as well. So that's another mitigation. Any one of these flights makes it between now and the end of 2011. That's just more margin for us to continue on. So our job is to try to manage the ISS such that we can give as much to both orbital and SpaceX to move to the right as they naturally, as you might expect them to have to as they conquer problems. Part of that, of course, is working very closely with them not to let other slips occur. So you want to manage really hard to your milestones so you can deal with those problems that you're not expecting to have. And so that's part of what we've been working closely with both SpaceX and Orbital to talk about. And I'll just tell you up front right now, both companies have done just a great job of working with us and designing their systems and understanding our requirements. And we've been very impressed so far. We just know that the challenge is there no matter how good you are. Next chart, please. So this is really my summary chart. We selected two contracts to give us some mitigation to the possibility if one or the other didn't quite make it. We're working very closely with they call themselves C3PO, the office that manages the COTS program on behalf of the ESMD, and in fact are doing all the integration work for the COTS program to ensure that the COTS vehicles then can seamlessly become CRS vehicles when that occurs. We have great insight into their milestones. We're working closely with them when we see challenges coming along. And while the contractors do have quite a bit of work ahead of them, we think they're doing a great job, but we would expect schedule slips as you normally would. And we're working hard to help mitigate those, as we mentioned earlier. And that concludes my presentation, Mr. Chairman, and I'm ready to take any questions you might have.
Okay, terrific. Thanks very much, Mike. Questions from anybody? Okay. Jeff.
Back on your chart 11, I assume these jagged lines are your demand. This is what you want to fly.
That's what we will fly.
That's what you will fly.
Yes, sir.
Okay, I'm at a loss as to how things like in 2010, for example, how does some of these items like ISS utilization get negative?
They get negative when you know you're not supplying at the level. 0 represents what we believe we need to be above to meet the needs of the
So this
different
is basically
suppliers.
the margin you have.
Right.
Okay,
So,
gotcha.
so in this case, we're trying to meet the needs of utilization folks. I'll tell you that dip is for I'll say for utilization resupply. So all of the racks and capability that we need to put on orbit to use in the future, that all does make it to orbit.
See, I've got please go ahead, Bo.
Thank you. Michael, when we listened today to Mr. Perminov, the Russian Space Agency head, he didn't seem to be concerned about the fact that NASA budget for support to International Space Station today is not planned beyond 2016. I haven't heard any concern from either of the COTS contractors either, your suppliers. And I'm thinking, is it just everybody assumes that America and NASA will come to its senses and figure out how to fund it past 2016, or are these guys in it for short run? What am I missing?
Good. I was about to say we should ask him. So there's Frank up there. He's going, yes. Well, I'll tell you what my conversations are, and then I would encourage you to
Well, you order from all of these guys,
let
you know.
Frank and Elon come up here and talk, and I think Anatoly's gone. But all of the partners have expressed to us that they have made a major investment in ISS. And in fact, in the Russians' case, they want to build yet another module, and they kind of don't want to do that if it's only going to be on orbit for 2 or 3 years. That's a major investment for 2 or 3 years. So our discussions with the partners has been they would like to see us go beyond 2015. Now, as far as SpaceX and Orbital go, I got to believe, based on the way the contract's written, that they would like to see the opportunity to defray more of the cost that they made in their first investment to get to where they are and see us fly more so they could do more resupply. But Frank and Elon would have to comment, if you'd like. Was I close? Did I get it right? There you go. So,
Thank you.
Now, we're going to have lots of opportunities to talk about other things, and if you ever ask me what I think about that, it'll actually be even slightly different than how I answered for those guys.
I had a question I wanted to ask. From October 2010 to, for 5 years or thereabouts, the current plan would be dependent on the Russians to put astronauts on the station. If I go backwards in time from October of 2010, there's one more mission that carries a crew with the shuttle. Is that right? One remaining?
2 more.
Oh, there are 2 remaining missions.
2JA, which is on the pad, and 17A will rotate 1 U.S.
One
OS
beyond
crew
that.
member, and then we bring home that crew member on ULF-3.
And if I take literally today, go backwards in time, when was the previous flight of the shuttle that carried a crew?
The previous flight.
There was a previous flight. Okay, thank you very much.
We did the lion's share crew rotation on the shuttle till the accident, and then the Soyuz had to do all of it until we started flying again. After we started flying again, we started putting a single crew, doing 2 on the Soyuz and a single crew on the shuttle, and we've done that semi-consistently for a little while.
Got it. Very good. Are there any other questions? Hearing no other questions, well, thank you very much.
Very much. Appreciate it.
Let's see, the next item concerns alternative architectures. The first topic will be direct, and let's see, Steve Metch is going to do that. Steve?
Great. Good afternoon. Mr. Chairman and members of the Commission, my name is Steve Metchin. It is my privilege to present the direct proposal to you on behalf of a courageous group of engineers and other concerned citizens. This began for me 4 years ago when NASA asked my company for an analysis of all possible approaches that could meet the policy objectives of the VSC, or the vision, within the available budget. This analysis was refined and transformed by government and industry experts into the direct concept I'm showing today. Next slide. The direct plan is intended to help put the U.S. exploration plans back into alignment with the approved policy and within the limits of the available budget. The reductions in long-term discretionary spending make this even more imperative today. So what is the Jupiter? Jupiter is based on the Space Shuttle. The Space Shuttle is the horse we are currently riding today into orbit and represents a good foundation from which to create a new capability for the future. Jupiter retains the proven and already man-rated shuttle main engines and the solid rocket boosters. Now, ironically, the first thing all shuttle-derived systems do is they remove the shuttle. But they retain the heavy lift stack that has taken us to orbit now for almost 30 years. The primary modifications to the stack is to use the tooling at Michoud to actually produce the oxygen tank to turn it into an inline vehicle in which the core becomes the carrier for the payload. The primary new piece of structure we need is the aft thrust structure. We then replace the shuttle main engines that are already flying, the existing 4-segment rockets, and we produce what we call Jupiter core once we add the payload adapter and the avionics. Above that, we put the payload, which is completely separate from the spacecraft, so it does not affect the abort capabilities for that. And with the payload fairing, that's our entry-level vehicle, what we call the Jupiter 130, or some may want to call someday the Ares 3. Once you're at that point, we add a planned addition 4th engine to the core, which is already designed to handle the additional loads associated with an upper stage, which could be J2 or RL6 based. The avionics ring is then replaced with the Altair lander, payload fairing already developed with Orion, and that becomes Ares for the Jupiter 246 in this particular configuration. Direct is not a new concept. Next slide. Even before the shuttle first flew, NASA engineers suggested utilizing the hardware and infrastructure of the shuttle to develop a derivative heavy lift launch system. Following Challenger, NASA engineers once again studied this idea in even greater detail, ultimately recommending the National Launch System, or the NLS, which passed its preliminary design review milestone in 1993. Now, in a post-Columbia world, some NASA engineers have once again asserted, at great risk to their livelihood, that the best path forward is still a true direct, hence the name direct, shuttle derivative. Given the imminent destruction of America's second heavy lift system and infrastructure, this commission will ultimately help determine if a solution repeatedly advocated by NASA engineers over the last 30 years as a practical solution to America's heavy lift requirements will ever become reality. Next slide. The engineering feasibility, use of available tooling, flow within the existing external tank manufacturing facility, and transport of an inline core has been assessed in great detail by NASA repeatedly. In fact, the National Launch System Study produced a series of detailed studies of which the core alone had 1,000 pages of detail associated with the design and how one would accomplish that. Then as now, the most time-consuming and risky element of any rocket development effort is still the rocket engine, not the tank structure. Direct is the only man-ratable proposal on the table with man-rated rocket engines already flying, namely the shuttle main engines. Now, some have said direct is nothing more than paper rocket. Nothing could be further from the truth. Currently, the Ares 1 requires a new 5-segment solid rocket booster development. the Jupiter's 4-segment SRB is already flying on the shuttle. Ares requires a new upper stage engine development, the J2X. The Jupiter's engine, the shuttle main engine, is already man-rated and flying on the shuttle. Ares 1 is currently struggling to mitigate the serious thrust oscillation issues associated with an unproven configuration. The Jupiter's configuration utilizes a proven approach for dampening these vibrations. The Ares 1 requires a new launch infrastructure, whereas the Jupiter uses the current infrastructure while also incorporating cost-efficient improvements to the current side-mounted approach. The Ares 1 requires a staging event, whereas the Jupiter's main engines are ground-lit just like the shuttle before committing to launch. The Ares 1 lift limitations has required key safety mission systems and redundancy to be eliminated from Orion, while forcing the same to endure in an unprecedented vibrational environment for a lunar spacecraft. Jupiter has more than enough margin to put all these safety systems back in. Taken together, all the development costs for the Ares 1 makes it substantially more expensive to develop while simultaneously increasing both schedule risk over the Jupiter. Bottom line, we believe strongly that the Jupiter will close the gap within the current budget. More importantly, to see what we're getting for our money, with Ares, though I realize Ares develops a lot of technologies for the Ares 5, we'll get to that in a second, but with what we get out of the gate here, with Ares we spend about $14 billion for a launch system less capable than what we can buy today. Whereas with the Jupiter, while we spend $8 billion, we get a launch system that will be second to none in the world, while increasing substantially the crew safety. So let's look at the basic overview here. Ultimately, even our entry-level Jupiter, which has no upper stage, will offer a capability that no one else in the world has, especially in terms of volume capacity. But when it comes to lift capacity, we have roughly 3 times as much mass performance as the next largest operational launch system, the Delta IV Heavy. Next. It is also important to point out that the current plan requires the development of an even larger launch system, the Ares 5, that promises to bust the budget and will also require the deorbiting of the International Space Station 2016 in order to free up the cash necessary to pay for its development. Under the direct proposal, the only new component we require is an upper stage in order to deliver a sufficiently high performance, lower cost, and more flexible lunar architecture enabled by operating one launch system but launching it twice. While certainly not as inexpensive as abandoning the vision for space exploration and remaining in low Earth orbit for another 30 years, it is significantly less expensive than the current plan. Because the Jupiter's main engines and solid rocket boosters are already finished, our schedule and budget are not dictated by such costly and high schedule risk items. By stretching out the remaining shuttle flights by 1 or 2 years, we can deliver a significantly smoother and therefore safer flyout of the remaining shuttle missions by providing a future for the operations workforce we are depending on right now to stay at their posts despite our lack of commitment to them. DREC can do this even in the tough budget environment before us because the shuttle workforce in a direct approach is an asset we need in order to conduct the Jupiter test flights themselves and not a liability to be eliminated in order to fund the development cost of Ares. The primary tent pole for initial operating capability for the Jupiter to the IS is not the launch system, but is in fact the Orion spacecraft. Ultimately, well, the transition will not be pain-free by any means. America will have a much more capable system sooner than any other plan on the table at the end of that transition. A lot has been said about the importance of crew safety during the ascent portion of the mission. Yet, ascent risk represents a very small portion of the overall mission risk for beyond Earth orbit destinations. For these missions, it is in fact the redundancy and margins of the crew spacecraft that determines the overall mission safety level. Due in part to the Ares 1's limited lift capability and unprecedented vibrational environment, Orion has been forced to remove important safety systems and reduce overall redundancy. As a result, the overall crew safety has been significantly reduced during the whole mission, not just the first 8 minutes of it. The fact that the Ares 1 is composed of unproven systems, whereas the Jupiter is largely composed of existing flight-proven systems, only casts further doubt on the Ares 1 safety claims. Regardless, the Jupiter enables all the safety systems that NASA originally wanted on Orion, not the least of which is returning to the land landing capability once again for every mission. Even our entry-level launch system, the Jupiter 130, that's the system without the upper stage, will provide a remarkable range of new capabilities. For example, currently there is no way to repair or upgrade the James Webb Space Telescope. With direct, a servicing mission could be conducted using the Jupiter 130 to place both crew and equipment into a high Earth orbit, rendezvous with the telescope, and repair it in a similar fashion to what happened with Hubble, only in a much higher orbit. The same capability could be used to assemble a network of extremely large 12-meter diameter telescopes, enabling the ability to resolve other habitable planets in our galaxy, answering a question as old as mankind itself: are we alone? The Jupiter's increased payload diameter enables robust Mars sample return missions that would pioneer new entry and descent landing systems needed before we can ever land astronauts on Mars. On Earth, everywhere we find an energy source and liquid water, we find life. With our entry-level Jupiter, we enable the Earth departure mass required for these kind of large missions to the Jovian moons in order to find if a second genesis has indeed occurred within our own solar system. By removing the barriers that limit all future exploration, the Jupiter will ensure that NASA and therefore mankind's best days of discovery clearly lie ahead. As Carl Sagan once said, somewhere, something incredible is waiting to be known. The Jupiter 130 will also enable new missions to the planet Earth, starting with an inspirational mission that originally went to explore the moon, yet ended up rediscovering the Earth. As a man-made spacecraft looked back at Earth in 1968, all of mankind became aware that we are all astronauts and drove home the importance of protecting our delicate spacecraft world for this and future generations. We are quickly approaching a time where the majority of people on Earth were not yet born to experience, myself among them, this profound mission themselves. It would find it just as remarkable as the previous generation did. One potential Earth-focused use of the Jupiter 130 would be to launch space-based solar power systems in one ground-integrated package that can deliver environmentally friendly energy from space 24 hours a day. The same telescopes developed to discover the signs of life on other planets in our galaxy could also improve the resolution of Earth's climate by many orders of magnitude. With this increased data resolution, climate models could be significantly improved in accuracy, helping to guide trillion-dollar decisions concerning the environment. And of course, there are national security reasons to improve our ability to look back at Earth from space as well. It has been asserted that any system based on the shuttle will be just as unaffordable as the space shuttle. Nothing could be further from the truth. The cost breakout of the shuttle shown here is based on almost 3 decades of hard cost data generated by a mature system. Because the Jupiter is so closely associated with the shuttle, we can, with a high degree of confidence, predict what the cost structure will likely be for the Jupiter. Once the cost associated with the orbiter and crew training is removed, the cost of a cargo-only launch of the Jupiter 130 would be about 72% of the current shuttle. A step in the right direction, certainly, but not a large cost reduction. The primary improvement in the cost effectiveness in going from the shuttle to the Jupiter is not from the reduced cost, but from the increased lift capacity. By removing the dead weight of the orbiter, we can achieve almost a 5-fold increase in lift capacity. Taken together, the Jupiter will deliver almost a 7-fold improvement in dollars per kilogram delivered to orbit compared to that of the shuttle, dropping it almost below $5,000 per kilogram to orbit, a very competitive price indeed. Slide. The cost benefits of the Jupiter go well beyond launch costs. The Saturn V was the first and last time America had access to a high-volume, heavy-lift launch capacity. With the Saturn V, we were able to launch ground-integrated, more capable spacecraft into space using only one launch. After destroying our first heavy-lift launch system, we were then forced to assemble large spacecraft like the International Space Station in 20-ton chunks. Mike Griffin had it right when he said this was a step backwards in terms of cost effectiveness. Unmanned exploration experienced the same dynamic, with the development cost overruns of the James Webb Space Telescope and the Mars Science Laboratory now running many times their respective launch costs, due in part to trying to shoehorn more capability into existing launch systems capacities. It pays to use the right tool for the job. To grow beyond our past impressive accomplishments in both manned and unmanned exploration, America needs the Jupiter. NASA is on record of claiming the Jupiter cannot achieve a self-imposed performance objective that NASA has seen fit to place ahead of the real requirements of budget and policy. In fact, they took one step further and claimed the Jupiter actually violated the laws of physics. Yet, the recently leaked ESAS appendix shows that a lower performing configuration of the Jupiter will actually exceed NASA's self-imposed performance objective even while burdened by an inefficient upper stage design. A self-imposed performance objective that the technically challenged Ares 1 and the budget-busting Ares 5 still cannot achieve. Not only does DIRECT meet NASA's desired lunar performance objectives, but DIRECT will place NASA back within the confines of policy for a price we can actually afford. Based on this track record, we strongly recommend that this commission get a second opinion on the upper stage design by talking to experts at the United Launch Alliance. Engineers like Bernard Cutter have decades of experience designing, building, and flying advanced upper stages, something NASA has not done for nearly 3 decades. In fact, we would recommend a second independent expert opinion be sought on all critical issues brought before the Commission. What about the performance needed for Mars, though? This issue was addressed over 46 years ago by none other than Wernher von Braun himself, who had always dreamed of one day seeing man land on Mars. He said that once you reach the limit of whatever launch system you can afford, you're left with 2 options for increasing performance. The first option is what he called connect mode, where you assemble various spacecraft elements in Earth orbit. The second option, though, is called tanker mode, where the spacecraft is launched in one-piece drive necessary without propellant, but is then filled in orbit with propellant prior to departure. Von Braun clearly preferred tanker mode because he correctly understood that most of the mass needed for Mars, for a Mars mission, is in fact propellant, not spacecraft. Therefore, propellant is the primary component that we need to assemble in orbit. Well, the best way to assemble propellant in orbit is with the propellant depot. Propellant depot has a number of advantages, not all of them technical, some geopolitical as well. The propellant depot increases mission flexibility while opening up almost 70% of the mass required to commercial and international supply. In addition, one future option for potentially lowering the cost of space exploration is by producing propellant from the Moon, Mars, or other suitable bodies throughout our solar system. A critical first step, though, is the ability to store and transfer propellant in space. The propellant depot is also a critical step for lowering exploration costs still further by reusing the very expensive spacecraft, thereby eliminating the need to throw away these expensive systems after each mission. The utility of the propellant depot will also naturally attract international participation and funding as it improves the capabilities of all partner nations. Bottom line, once your volume capacity is sufficient to launch ground-integrated spacecraft as one unit, your launcher is large enough. The Saturn-class Jupiter is more than sufficient for the exploration program, while also having a lower fixed and variable cost than the Nova-class Ares 5. On the other extreme are those that would advocate an exclusive ELV COTS program, thereby resulting in the destruction of America's second heavy lift system and workforce. The direct plan meets that team more than halfway by opening up 70% of the mass needed in orbit to competitive bid. In addition, a significant barrier to entry for new companies and approaches is removed because cheap propellant is less expensive to insure than expensive spacecraft or people. Unlike opening up a few flights to the International Space Station per year, this approach represents more than enough demand to max out the launch capacity of most ELV COTS providers, enabling them to achieve the economies of production associated with high launch rates, lowering the cost for all their customers. Establishing an in-space market for propellant will also help build the business case to commercially develop propellant from the moon as well. It has now been almost 4 years since the basic of what I just presented here was first shown at NASA headquarters, but unfortunately rejected in favor of the Ares 1. Even now, because so much of the hardware, infrastructure, and workforce are still in place operating the shuttle, direct can be available much sooner while also delivering a significant increase in crew safety over the shuttle. Direct not only builds upon this existing multi-billion-dollar heritage, but simultaneously accelerates the progress already made by removing the bottleneck of the Ares 1 for IS access and retargeting its developments already underway for the subsequent lunar phase of the vision for space exploration. Ultimately, we strongly believe that direct is the only way our nation can hope to achieve the policy objectives within the limited budget we have before us. Direct will not only solve the looming issues facing the manned space exploration, which is the goal of this commission, but will present a new opportunity for unmanned exploration as well by removing the limits imposed by existing launch systems. The ability to lead from the front in capability will naturally attract other nations to join the American-led efforts and to a truly global effort, while at the same time providing a serious opportunity to the commercial sector to deliver most of the mass needed for the vision over the long term. Taken together, we strongly believe that direct is by far the best possible path to ultimate success for NASA, which is what's motivated the direct team from the very beginning, America, mankind, and in furthering space exploration and development. I carry 3 requests from the direct team to the Commission. The first request is the Commission asks the President to order NASA to cease any further destruction of the shuttle infrastructure until this Commission can make its recommendation to the President. Our second request is that the Commission endeavor to talk to the engineers at the working level of the Ares 1 technical problems and the Ares 5 cost problems as anonymously as possible in order to determine independently for themselves the ground truth of the present program. We have certain knowledge that this ground truth is being altered as it ascends the chain of command, and there's a significant amount of pressure being brought to bear to prevent any information from being provided to this Commission that is counter to the current party line. Our third request is for the Commission to get a second expert opinion on all critical issues or disagreements NASA may have with our plan, like the upper stage, for example, from sources independent of the current NASA chain of command. I thank you for your time, and I welcome any questions you may have.
Thank you very much. Those are very serious charges, as well as a very serious set of performance and cost data you've offered us. Let me ask if my colleagues have any questions to begin with, and I have one.
Yes, sir.
Steve, you may not be the right person to ask this, but in the ESAS study in 05, the sort of something that looked pretty close to this, two-launch, 70-ish ton vehicle, was pretty closely looked at, and in fact carried as one of the options, at least in the first and second cycle of the ESAS study. Do you understand what the rationale was in the ESAS study that caused the decision to be made into the so-called 1.5 launch options as opposed to the sort of 270-ton class launches? And what would your response be to that rationale?
I probably can't explain it to you because I don't understand it myself. I think it makes a lot of sense to develop one. We really only have the money to develop one launch system. And I think the efforts of SpaceX and the efforts with the ELVs and the COTS program are more than adequately covering that class of launch systems that Ares 1 represents. I think NASA's right position is to work on a heavy launch system. I would also suggest that the current Ares 5 has gone a great distance away from the Ares 5 that they recommended. The Jupiter is closer to the original Ares 5 than the current one. It uses shuttle main engines. We use 4, they use 5. Again, our main contention really is the Ares 1, not the heavy lift capability. And our only recommendation is the heavy lift capability needs to get back to a true shuttle drive system.
Thank you.
Yeah.
I've got 1,000 of them, not just one. So I'll ask a meta question first. Just let me get back to you with more questions.
Yes, definitely.
Okay, in that case, I'll pick only the highest one, which is, I'm well aware of the many advantages that you get from a propellant depot architecture. And I understand the concerns about the workforce, but set that aside for a moment. If you are going to do a depot capability, why not go farther? Because when you look at any of the systems architectures I'm familiar with, the spacecraft dry already fit on EELV-like objects.
They do mass-wise, they do not volume-wise. People keep forgetting the importance of volume. When I saw some of the Delta heavy configurations, they kept the same 5-meter. Yeah, if it's a big sack of hammers we're putting up there, they're probably right, but the average density of payload in space is about that of balsa wood. So you got to keep that in mind. You got to grow your volume at the same time you're growing your lift capacity, and the Jupiter does that.
Thank you.
Please, Leroy.
Yeah, I just have a question about who are you guys? I mean, is there a list of folks who are... I understand what you're saying about wanting to be anonymous, but are any of you besides you willing to be identified?
Well, when you find them, let me know, because I don't know them all either. In fact, none of us do. We're taking advantage of the new communication technologies that became available with computers and the internet, which I think is why going forward after this point, and we fully intend to abide by the recommendations of the Commission. This is not. There's no way to make money at this, by the way, of disagreeing with your customer. But
it's just difficult to assess the work without knowing who's doing it.
Well, we can get you names of people to talk to, but the anonymous part is critical. There's a certain amount of blood in the water, if you will. So I just think it would be, if we want to get to the bottom of what's going on, I think that's the best policy. I think that's the great thing about this commission, actually.
Yeah.
Bo?
Yeah, Steve, well, I'm impressed with your enthusiasm and with your boldness, but I do have one question. Your charts are not numbered, so this is a pie chart that talks about your Jupiter and STS cost comparison.
Yes.
Can we get the chart back for a second?
I think it's about slide
about halfway through the deck.
Well, let me go ahead with my question. You compare the current STS to your Jupiter 130, and you're saying cost of 5 flights, I believe, is 2.6 billion. And you contrasted with only 1.9 billion for Jupiter.
Correct.
But shouldn't you include cost of 5 Orions if you wanted to have like apples to apples comparison?
Well, this is a cargo version.
Well, you know, but you're comparing it to a vehicle that carries 7 astronauts also.
Actually, that's one of the big advantages of this approach. We can fly with a crew or not. And so we have both a cargo version and a crewed version. Obviously, if you fly with a crew, any launch system will be more expensive than if you don't fly with a crew. That's one of the utilities of this approach.
Okay, so this is a cargo version, you're
Correct.
comparing it to a crew faring
But see,
vehicle.
that's the interesting thing about the shuttle. They combine cargo and crew together,
Right.
which not only affected the safety and the abort possibilities, because our cargo is carried below the crew. If the crew comes along with the mission equipment, they're carried below it like Apollo, so they are unaffected by their abort. So we believe that was the fundamental recommendation from the Columbia report. Let's not have such a large launch system that we can't quickly and safely extract the crew should something go wrong. Likewise, it works on a cost basis, which means now you can have a cargo version that's less expensive and also fly crew when you need to as well.
Okay, thank you. Thank you.
Yes, you stated that the Jupiter system would represent an improvement in crew safety with compared to the shuttle. Could you quantify that?
Well, right away, if you assume we had the same safety levels as the shuttle, the 2 accidents that we know of, the Challenger being the SRB leaking, could have been abortable had we been watching those for those kinds of things, the leaking SRB. And then, of course, in the Columbia accident, the heat shield's entirely protected during the ascent. So just having a quick escape system on the shuttle, which we currently really do not have, and assuming that's 1 out of 10, it fails 1 out of 10 times, you get a 10-fold improvement. Now, I'm glad you brought that up because there's another big advantage. In our architecture, even in a lunar program, half the time we're launching uncrewed. So as long as the vehicle's being processed and treated as if we have a crew on it, the probability of an accident occurring on a crewed flight is naturally cut in half. That's one of the advantages that the EOV and the other programs have, is that they're essentially continually testing the entire system, which is not just hardware, it's people, the culture. Every time they launch, they're testing everything. Many times these hardware safety-based assessments, I think, are incorrect. When we look at the accidents that have happened, they've been an impact. They've interacted with the hardware, certainly, but there's a certain aspect of culture that came into it.
Okay, I'll take the last question, I think, if that's all right with the group. Many years ago, NASA looked at a configuration quite similar to the Jupiter 130 that, based on the external tank, the solid rocket motors, and so on, and didn't continue it. With your folks' apparent background and knowledge of NASA, do you have any idea why that was dropped?
I think they didn't want to operate both. They didn't have the money to operate both the shuttle and that system at the same time. I think now that the retirement of the shuttle is now official national policy, we can now afford to entertain. It keeps coming back to the same principle. I think we only have the money to operate one launch system, so let's make it as capable and as expandable as we can. And I think the inline version of a shuttle drive system achieves that objective.
Well, thank you very much for your presentation. We will take it very seriously.
Yeah.
Let's turn then to the final scheduled speaker for the day, and we're going to hear about side mount options from John Shannon.
Okay. You guys didn't tell me there was blood in the water before I volunteered to do this. And I, just as a senior NASA manager, let me say I don't agree with that. And I felt perfectly comfortable coming up here and talking about an alternate architecture, something that we've looked at for many years. And Jeff and Steve Cook and company have embraced, and we've talked about it. We talk about transition between programs all the time. So if you're worried about going to talk to anybody, come talk to me. Talk to Wayne Hale, talk to Mike Suffredini, talk to Brent. Just come talk to us, and we'll, if you don't want us to attribute things to you, we can we can certainly do that, but we're always looking for good ideas. And I think just the fact that I'm standing up here talking about something that departs from the current baseline should maybe prove that to you. Stay on the title page for a minute. I want to preface the presentation with some other comments here that NASA has a plan. NASA has a baseline plan, and I think it was a well thought out plan in the time of ESAS, and that the Constellation program has put together a viable architecture. And I'm not going to talk about an architecture. I'm just going to talk about a launch vehicle. But it has not been funded. It has not been funded to the level that we would need to see it through. And I see that on the shuttle side from the transition. Jeff Hanley and myself worked with our teams. We had a very close-knit transition plan, not just for civil servants, but also for contractors. And because of the funding problems, that has become unknit, and we have gaps in the industrial capability and in the workforce, which is causing all this. I don't think it is some big conspiracy. I don't think they've had cost overruns. I think they've just not been funded the way that they were. The plan was originally produced. You know, we talked about this a couple weeks ago, and I think that the first option should be to fund the plan that we have. But if we can't do that, I don't think we're ready to seed human spaceflight. Like Elon said, we're not ready to seed support of the ISS. We're not ready to seed the opportunity to go outside of low Earth orbit. So I've had a small team inside the shuttle program that has kept alive some of the side mount discussions. And when I say small, it is 3 people that go and grab some information from other people to think about new things. And I'm going to talk a little bit about that. But you need to realize it has been a small effort. It has not been across NASA. It has not had the advantage of being looked at across the agency for good reason. It's because we have another plan, and it's just now that we're looking at it and seeing the budget does not quite align with it. So what I'm going to tell you today is promising. It has some benefits, some things that could that are obvious advantages, but it needs to be looked at to a much greater level than what my team has been able to do. Now, we're still on the title page, and I've burned like 4 minutes. This does not look like Shuttle C. I don't even call it Shuttle C. We call it a heavy lift vehicle. Shuttle C was an autonomous vehicle that separated from the external tank just like the orbiters, had orbital maneuvering capability, attitude capability, thermal capability, a lot of different things that this does not have. This is simply a first and second stage to inject the payload into a 30 nautical mile by 120 nautical mile orbit. That payload is assumed to be autonomous. It takes care of itself. When it's injected, it goes off and does its thing. And all that you see in the title page picture goes into the ocean. So it's just it's a foundational kind of a launch capability. Let's go to the next chart. We've looked at this a lot. It's been called a lot of different things. You can see what I was talking about on the upper left. It was looked at by industry 5 years ago. It was a 2-year study, so there was a lot of data out there. I know we've provided a lot of that to you. It did not have a deployable fairing when you get out of the atmosphere, and this team I have added that, which gave you a little bit more performance. It also, the beauty of, I think, the most recent concept the team has come up with is that it does not try to reuse engines. We have learned from life cycle costs on SSMEs that reusability is a myth, in my opinion. You don't buy your engines and then you never have to talk to the engine manufacturer again. You just keep using them. That's not true at all because parts wear out, you have failures, you have design issues. So you have to keep your production line going or at least available to you, and that's a significant cost. And then you buy one of pieces whenever you need new parts, and that gets to be extremely expensive. So we would take I think the approach of you get rid of the very, I'll say hazardous, it's probably the most hazardous part I think on the orbiter of that interface between the main engines and the external tank. And you just have straight pipes. You don't have all of your disconnects and your pyro systems and all of those things. Let's go to the next chart. So that chart was just supposed to say we've looked at this many times over many years, and I think most of the people in this room are familiar with a lot of that. This is just the basic cargo configuration. If you notice, it doesn't modify the external tank at all. It's exactly the external tank we produce right now. It's the solid rocket boosters we produce right now. The boat tail that holds the SSMEs that are unchanged is simplified because it is bolted directly onto the external tank. It does not have the separation plane, which causes that complexity. An avionics module in front of it. I'll talk about avionics in a minute. And then a separable fairing that provides that performance boost up to about 72 metric tons to that 30 by 120 orbit. Next chart. This is an important chart here. Let me back up for a second here. I think Elon Musk hit it exactly right. The way the Russians do things is really smart. I wish we would have done Shuttle C in the 80s or the 90s. I think the Space Shuttle Orbiter would be a safer vehicle to fly if we had done Shuttle C back then. Because if you have a cargo vehicle that is the same configuration as your crewed vehicle, you have the opportunity to roll in new design, new enhancements on that cargo vehicle much easier than you do on your manned vehicle. And that's what the Russians do. For the most part, they'll fly new hardware on their Progress several times before they roll it into the Soyuz. And we have a terrible track record in the Space Shuttle program from upgrades. We did main engine upgrades, controller upgrades, some things like that. It cost us way too much money. It took way too much time. I think that is because you do not have a combined environments test capability except to go fly the vehicle with a crew on it. So that made it very difficult. I think if we'd have done Shuttle C, we would have been able to roll in those upgrades on the cargo vehicle and verify through combined environment flight testing they actually are effective, and then you can roll them into the crewed vehicle. And I'm just guessing, but I think that our upgrades program would have been much more successful from that standpoint. So the thought here was that you build this Block 1, which is just a two-stage capability to get to low Earth orbit. I said before, no change to the external tank, no change to the SRBs, no change to the SSMEs. You use existing avionics. And I grew up in the guidance, navigation, and control world, and that is absolutely possible. The one thing that nobody has talked about in all the rocket designs that we've seen that is an enormous bullet, and those of you that have ever worked with rockets or even our modern aircraft, is flight software. It will eat your lunch. It is critical path from the day you put the first rocket drawing down on paper, and getting flight software to work with your hardware from a timing standpoint is extremely difficult. We've been flying the Space Shuttle for 30 years, and we'll still find things through simulation that we did not expect in the way software interacts with hardware. This Block 1 capability, you can use your existing flight software. You can use the computers that we have right now. You can use the rate gyros, the IMUs, the accelerometer assemblies, all of those things required to fly any spacecraft, but you've already got 30 years of flight test behind it and use it. Now, I would not use the full suite that we use on an orbiter. You can use one of each and be perfectly safe. The flight software can be modified just to no-op the channels that you're not flying on that particular spacecraft. The other one that nobody's talked about that we spend a lot of time and money on is your systems integration tools, the acoustic models, your aerodynamic models, structural models, loads, your trajectory models. Extremely important. As you all know, and Bo actually wrote a paper on it not too long ago, we totally blew the acoustics for STS-1 and almost lost the vehicle. We had a structural member buckle in the OMS pod just because we did not have the water flow and the acoustics right. So if you use a more evolutionary approach that has the same or similar mold line of the Space Shuttle stack now, you already have that history, and you can roll it into your next vehicle, and that's a big deal. Those are two things, I think, flight software and your environmental tools that people really overlook when they're starting to design a vehicle and don't understand very well. Existing pad structure that follows the launch and ground control software, that's important because that, again, it's software and it'll eat your lunch if you don't get it right. That high-risk aft interface, it's just bolted on, so you got rid of that. You don't have fuel cells, you'd have batteries. You don't have the cryo systems because you don't have fuel cells or people on it. Nitrogen tanks, the cooling systems, your orbital maneuvering system, your RCs. You don't have any hypergulls on it at all. So it's a very slimmed down and streamlined kind of vehicle. And that's all very different from the Shuttle C. Block 2, of course, you can do things to get more performance, and at some point we will run out of spares and hardware that is cannibalized from orbital vehicles, and you would end up building. But the nice thing is you're doing flight tests with your basic design as you're beginning to procure your follow-on avionics. Next chart. I already talked about infrastructure facilities. You all know how we do space shuttles. You can obviously see that you don't have to buy a new ET barge. Nobody's talked about that. You don't have to buy a new Pegasus. You don't have to do a solid rocket booster or anything like that. That changes. And my complete unadeptness at PowerPoint means that cargo carrier is really fat there. I just noticed that, but I just stretched the picture out, and that's why it looks like that. Next chart. The last one, great graphics. That was good. The team has looked at payload envelopes and designs, and actually I think we found from the industry study that we would have a CG problem, and the center main engine would hit its gimbal limits. So we actually shrunk the payload envelope a little bit. They've done some studies. Again, this is something that needs a great deal of work from the broader community, from the NASA team, from the aerospace team to show. It does look like, with the 72 metric tons that you could do quite a bit with that payload capacity. Next chart. Everyone had one incomprehensible chart. So this is mine, and it is just the flow of avionics and hardware required between Block 1 and then a follow-on Block 1 that has some new stuff, and then a Block 2 where you go to all the new stuff. And basically, if you look across the top, there's no really new builds for avionics in the Block 1 architecture. We could build it with the hardware we have in hand right now. Excuse me. Next chart. SSMEs, everybody comes, Shuttle C is great, but you got to throw your SSMEs away, and that makes it unsustainable and it's unaffordable, and let's move on to the next vehicle. SSME, we have 1 million seconds of runtime on. We understand SSME performance very well. I have 14 assets right now, limited by nozzles that you could go fly in a test program. We have all the hardware. We're set up to do the test. There is, Pratt & Whitney Rocketdyne can provide you books of data on the RS-25E, which is expendable, which is your channel wall nozzle, the non-refurbished turbo pumps. The fact that you're not trying to refly these engines means you don't have inspection ports and you don't have a lot of different requirements that we have built into the SSME. That has caused the cost to be significant. And you can't really take an SSME cost and say, well, that's what the expendable cost would be, because what you do for expendables is you put them on a production line and you would commoditize it basically. And that's how you would build a certain number per year, and then you'd have the economy of scale to do that. So there's a lot of data on there, and we'll let PWR go get it if you guys want. Next chart. I really debated putting cost estimates in here. The team needs to validate these. I wasn't going to put them in because I said, well, you guys haven't spent enough time on this. Then I looked at the industry study that was done in 04-05. The costs were almost exactly the same. I put them in here for your interest. Take your big grain of salt right now, and we need to go validate these numbers externally. Next chart. Everything I just said about cost, I'll say about schedule. The industry team and the NASA team somewhat independently came up with, if you turn it on, it's a 4.5-year project to fly your first test flight. We need to work on this some more and debate it and get a better schedule. So take your second big grain of salt now. Next chart. We did some design reference missions just to show, is this even something that would be useful? It is obviously at 70 plus metric tons. A heavy lifter there is not another vehicle right now other than the space shuttle that provides that kind of injection capability. But would it be useful? And this gets a little bit into architecture, and I don't want to get into architecture. I just want to talk to you about the launch vehicle. But these are some of the ideas the team has thrown out. And again, I would say that this needs a lot of work with the broader community. Next chart. Thought being, this is, you can kind of see the approach, normal solid rocket booster separation, fairing separation. You hit MECO and off goes your upper stage with autonomous rendezvous and docking capability, which actually, if we would have launched this morning, we were going to demonstrate the autonomous rendezvous and docking capability. We put some sensors in the payload bay of Endeavour, and we'll demonstrate that software. And I hope, although doing it within 8 flights is going to be difficult, I hope to have the capability to demonstrate the shuttle autonomous docking to the ISS. At least we'll get the sensor data and then put it on the ground through simulation and be able to show that. And then you toss your external tank with the big keel structure that goes up to the bipod fitting that holds the boat tail into the Pacific Ocean. Next chart. Design reference mission, just what it looks like, and obviously a phase with station. Next chart. Okay, on time. We have looked at crewed options. This was the ISS crew piece. We have done some early assessments on the launch abort system, being close to the intertank, and it looks doable. Again, this is a prime area of heavy study to look at the last. You'll see a chart where I show safety. It all depends on how effective we can make a launch abort system work. Thought here would be that you would end up injecting the carrier with an MPLM or external payloads, and you would fly actually around and dock with it and then fly it to the station. Next chart. This is the crew and logistics launch just like before. Next chart. There's also a profile where you could do a 2 launch, one from pad A, one from pad B. You may have noticed before Hubble we had a shuttle sitting out at each of the 2 pads. So from a ground op standpoint, that was maybe a precursor look at how you could do that. Lunar lander with an Earth departure stage on it. Next chart. And then fly Orion, same discussion we had on LAS with its Earth departure stage. Next chart. And again, we're into architecture. What I would do is, as opposed to training 2 EDSs with a lander and a CV, I would go and put the lunar lander in lunar orbit, and then if it has hypergulls on it, you can go whenever you want. You can launch your crewed vehicle. I'll say right out, this is not the lunar lander that is currently in the baseline architecture. This is a different lunar lander. The guys just were running some calculations. It was a 28 metric ton lander. Doug, what's the Altair right now is 45-ish. Apollo was 16-ish. So it's a different architecture, and that's something you have to understand right off. It's not as capable as what the Ares 5 architecture looks like. You know, we can talk the same depot discussion. I like depots, but there's, again, there are different architectures than what we have right now, and this has not received sufficient study time from the broader community to say this is the answer in any way at all. Next chart. Oh, okay, I got 2 incomprehensible charts. This is a baseball card of just performance between the cargo version for Block 1 and Block 2, and then the crewed version. Next chart. This is, I'm not going to spend a lot of time on this. We are flying at the max rate on the shuttle program in fiscal year 10. If we were going to move into something like this, I would lobby strongly to spread out the fiscal year 10 launches into 11 and in 12. And as we restarted production for solid rocket boosters and external tanks, and the configuration is so similar, you know, production is really what you have to worry about. And you could essentially get rid of most of the gap by doing that. Now, you will have a gap because Orion, the Orion development time is what would pace the next crewed vehicle. Next chart. There are some growth options from the 81 tons. I didn't just magically go from 72 to 81. It's a suborbital staging. You load up the vehicle more. You end up with MECO that is a suborbital, but then you separate your 3rd stage with either a J2 or an SSME, and off you go. You get to 81 tons by doing that suborbital staging. If you ran your SSMEs at 109%, and I wouldn't let you do that with crew on it, but with cargo on it, you might want to do it. 5-segment SRBs we've talked about before. If you had an SSME on your departure stage, there's a few things you could do to maybe get above 90 metric tons. There are some these things are lines on a chart, but there would be great expense and a significant amount of development testing required before you would sign up to do any of these. So I wouldn't say, hey, this idea will get you above 90 metric tons. It's, those are thoughts. Next chart. I asked my guys to go off and say, hey, let's just do a PRA. We know what all the different pieces are, all the different components are, except I don't know the EDS or I don't know what's under the fairing, but for the stuff that you see in the little picture on the lower right, where would you get? And we did a 5%, 95% study, and you can see the numbers for the loss of vehicle that we got. Again, this is your third big grain of salt here. Next chart. Boy, this just makes sense, right? Is that if your launch abort system is 100% successful, you're flying a pretty safe rocket. It will not be. And it actually may be low if we look at the shock interactions between the LAS and the external tank. This is an area that needs a significant amount of study. And I think if we were at all serious about doing something like this, we would go work on that as the first thing we would go do. Next chart. SEP design. I told them I didn't want any RCS. I didn't want any active propulsion system. So post-MECO, of course, your fairing is gone. And it's they designed, some of the guys at JSC, a spring mechanism that just pops it out, and you would add the ET tumble valve back on to give you a good clean separation. We think this is a very solvable problem. Next chart. And we did a little bit of thing there. Next chart. The first bullet is the most important bullet. The HLV design, it is less capable than the current baseline, and we need to stress that fact. And it has not been studied to the amount where I feel very comfortable coming up here and telling you a whole lot about it. I think it is something that if we decided we were not going to get the money to do the baseline plan, and we wanted a backup that would provide a lunar capability or a human servicing of the station capability, that this is something that we would want to go study again. And again, we've spent 30 years studying it, so we have a lot of background to do that. Benefits are obvious. We basically have the parts to build everything. What we don't have is some structural parts for the keel, for the fairing, and for the boat tail to mount up the engines. If you're going to have a development or a program, I think the structural piece is probably the one you would pick. You wouldn't be flight software or engines or anything else like that. Another thing that's kind of near and dear to my heart is that the HLV retains the contractor and civil servant skill base that we have right now, especially in concert with spreading out some of the shuttle flights that we currently have on the manifest. I'm very concerned about the industrial base. I'll tell you that you know, the congressional budget numbers that have been provided to NASA basically took away the lunar program, and that's where all of my space shuttle civil servants were going to go. The folks at Marshall were going to go to Ares 5. The folks at Johnson Space Center were going to go work on Altair. And of course, if the lunar program is gone, I have got to make a place for civil servants. And it's just worse on the contractor side if the lunar program goes away. Potentially support ISS for crew and cargo. We talked about that a little bit. And I really don't want to get into architecture discussions, especially with Dr. Crawley, because he knows a whole lot more about it than I do. But he left, so okay. Let's talk architecture for a minute. You know, because that's not what I'm here to talk about. I'm talking about a capability to provide a heavy lift capability into low Earth orbit, and then off you go. I did have because this is a little bit different than Shuttle C, I had a short movie, a couple minutes. Go ahead. And I think it just helps you. The music is really corny. I did not pick up the music on this, so maybe if the sound is turned off, I'll tip somebody really good. Very nice. And it just shows the buildup of the vehicle. And this is very simplistic, right? But it shows you fairing, and there's a whole bunch of different things. My graphics guys got really excited on me here. What I really want you to see is the launch and the fairing separation. So, here it comes. Great. No tip for you. Yeah. And as people are watching, we could ask questions that are really loud and drown out the sound if you would like. I don't know about you guys, but I'm blown away by what they can do with graphics nowadays. And this was just a conceptual lunar lander piece on an EDS to be designed. I didn't pick the music myself. It was not. This was stolen from the Constellation program guidance. That's probably all we can stand up in, so I'll give you half of it if you get off here. Okay, so that gives you a little better idea, and again, I want to really stress the fact that this has not been vetted or discussed in the level of detail it needs to be throughout the entire NASA and contractor communities. It's an old idea, and there's a few changes to an old idea, and that's all I was going to present today.
Terrific. That was very well done. Please go ahead, Leroy.
Yeah, thanks, John. Let's see, I just wanted to ask you about your first conclusion. HLB design is less capable than the current baseline. You mean that it's less capable than the current baseline because the current baseline includes Ares 5, is that correct?
Yes.
Okay. And so,
and the current baseline is an architecture that has a very large, very capable lander, and there's no way
Sure.
to do that on this vehicle, both from the volume side or the propulsion side.
right. But if we're just thinking of Ares 1, comparing this to Ares 1, let me make sure, understanding that your numbers are extremely preliminary and haven't been vetted by the community. 4.5 years, 6.6 billion, 72 metric tons of cargo, and Orion with crew to orbit.
With your caveats, I would
With the
agree.
caveats,
Yes.
right. Okay, so in that context, maybe you or maybe Doug can kind of give us a high-level answer. I mean, I'm sure ESAS looked at this kind of architecture as well as the direct-type architecture. Can you kind of give us a high-level big picture of why the current architecture was selected over, why these architectures were rejected?
It's a requirement. Well, no, it's a requirements discussion. It's what kind of lander do you want to put on the moon? What kind of capability do you want to have
Driven by the
on
lander.
moon? And
Right, okay.
and they were given a mission, and they built an architecture that would support that mission. This vehicle will not support that mission. It'll support a different mission, but we'd have to go and change that architecture.
Okay.
Is that fair, Doug? It's a requirements discussion.
So it was pretty much driven by the lunar mission and the lander requirements.
Why don't you come up so everybody can hear you?
I don't think they actually studied, or they didn't look at directly the crewed version of it because they considered it a safety issue. I think probably because it was next to the tank. But they looked at the cargo capability, and they were looking at the mission overall, I think.
Okay, thanks.
Yeah, and if you automatically said it was uncrewed, that gives you 3 launches, right? Because you're going to put the crew on Ares, and then you had an EDS with the lander and another EDS for the crewed thing that went up, and 3 launches is.
My question relates to that same sort of line of thinking. Many years ago, I was involved in a study where we had actually recommended building a Shuttle C or something very similar to it. At that time, it seemed to make sense because you could pair it with the shuttle.
Right.
And so you didn't have to risk astronauts to provide trucking.
Right.
And you could use astronauts to fix Hubbles and the likes. It seemed to make more sense to us. And today, if you were to say you aren't going to have a shuttle for whatever reason, if you weren't, then you've almost got to go to the Orion version or something like that. But your reliability figures, loss of crew figures, if my memory is correct, showed the Orion version of what you might call a Shuttle C derived or something was much less reliable, less safe than the Constellation configuration. And that surprises me. Could you elaborate a bit?
No. Why? Because I don't have any knowledge of the Constellation numbers. I can tell you shuttle program numbers are not as good as what Jeff presented earlier. Our mean is 1 in 81, or 5% 95%, or 1 in 57, and 1 in 117. Those are numbers that are very near and dear to my heart. I think that the effectiveness of the launch abort system is going to completely drive what the final number is going to be, and I have no idea how effective that is going to be because we haven't studied it.
That should be relatively independent of which vehicle it was on, though, if that's the driver.
Perhaps.
No. Well, we shouldn't design vehicles today.
I'd like to. I mean, I had a ball today because, you know, if you like space, this is kind of neat stuff. But
the other thing that occurred to me, I've not been that close in recent time, but the concern over Sophie peeling off, that was a problem for the shuttle, clearly, because the leading edge of the shuttle was exposed. With this configuration, would that be viewed as a problem, or?
Okay, the shuttle program manager piece of me says we fixed that problem. We're very vigilant about it, but we understand it and have fixed that problem. But it doesn't matter if we did or not because, of course, you have a very robust fairing with no TPS issues.
You have a different geometry here too.
Right.
Okay. Other questions from the committee?
Just to follow this up, so I'm sure I understand that it seems like the conclusion is that the biggest problem identified with this external system was the loss of crew probability. But you showed a graphic, and I understand all the caveats you applied to everything that you showed us.
Good.
This plot of probability of loss of crew with the launch abort system, and it looks like, you know, at least at one end of that plot, one gets into the range for loss of crew accidents that the current architecture is in. Is that correct?
Again, it is completely dependent on the launch abort system capability.
So it's just not quantified well enough.
You know,
to
and I kind of laugh, right, because after Challenger, we made a big run at trying to put an abort capability, crew capsule capability at the tip of the orbiter, but you just can't do it from a weight standpoint and a design complexity standpoint. This is basically that same thing. So we have some studies that have some of the dynamics associated with that, but we need to go back and really go through that and really understand that because the safety of this vehicle depends exactly on that one thing.
Okay, we thank you very much.
Real quick.
Oh, I'm sorry, one more. Bo.
But basically, Doug, LAS improves a launch vehicle loss of crew by a factor of 10, roughly. I mean, you know, John had this curve, but, and I think you guys are talking effectiveness of like 90% effective, so that would increase it by a factor of 10, I guess, right?
Well, it's
Do you agree with
90%
that?
on top of a rocket, though, and this is a different,
Yes, yeah.
different design.
The failure modes of the rocket and the trajectories, the actual ascent profile differ between different designs. Where you are when there is a failure, if there's a range destruct on a tank, do you want to be sitting next to it? Kind of, you know, that sort of discussion can get into this. If you're sitting up on top and do a range destruct because you're off course, that tends to look better. I mean, back when I was in the shuttle program office after Challenger, and we were getting ready to fly Galileo, which had RTG on it, and we studied the Titan 34D launch destruct. We looked at how the boosters destructed on Challenger because they did a range destruct after the accident because they kept flying, and they recovered hardware out of the ocean, and looked at how the boosters came apart, and they tended to fly sideways more than they did up. So it matters where you are in terms of what failure and what mode of destruct you're in. So I mean that's a long discussion, okay. but those kind of things do come into
But by the same token, and again, I don't want to design rockets here. Well, maybe I do, but we shouldn't.
I do.
If you slide the cargo the side mount forward, you could still have the escape capsule you say not.
We need to, I'll design, but the CG becomes a real issue then. And you end up saturating your gimbal capability, so you don't. Of course, we don't have a range package on the ET. We have them on the solid rocket boosters, and if we were going off course, you've got plenty of warning before the range takes action.
Okay, we probably should.
It does.
Move ahead. Well,
that is true about every single page I just showed. It has to be studied if we want to go look at it. So.
Thank you very much.
You bet.
Let's see, we're 30 seconds behind here, slipping up this afternoon. We then come to the time for public comment. We've allowed up to 30 minutes for comments. If there's anyone who didn't comment this morning that would like to comment, the 2 microphones are here. We'd certainly welcome comments. We'd ask that you hold them to 3 minutes or less, so that we could give as many folks a chance to speak as possible. And why don't we, I guess we'll start here. And would you identify yourself, please?
Good afternoon. My name is Mike Snyder. I'm from Houston, Texas, and I appreciate the opportunity to share my personal opinions and thoughts with you here today. You've heard a lot of good ideas and a lot of different concepts, and so I'd like to tell you a little bit, maybe bring it a little bit onto the personal side of things. I'm in my early 30s, and I was born after Apollo. My only connection to that program is the historical pictures and the videos that everyone sees. The fact that I drive by the Saturn V's every day laying on the ground, and still get the chance now and again to talk to the people that used to work on that program and hear about all the great efforts that they did. Of course, I inherited the shuttle, and while it's an outstanding vehicle with a lot of great capabilities, and it's one that I think that this nation should not be so quick to give up, it is limited to only low Earth orbit. And we spent the last 30 years there doing that, basically calling it exploration. I have a lot of opinions on this, and one of my larger opinions is that our current strategy does not do enough to engage the private sector and promote the development of the budding commercial space environment and the capabilities that they may one day have, such as the propellant depots that folks talked about. We do not seem to appear to be building a true spacefaring architecture and infrastructure, actively encouraging the private sector or taking advantage of any of the design reference missions that have been discussed so many times and revised so many times throughout the decades. What we currently have has been referred to as Apollo on steroids, but Apollo was labeled unsustainable. And I ask, why will this time be any different with all the extra developments that we have to do? With regards to what I mentioned above, Ares 1 and Ares 5 is not what was recommended in ESAS. While we have put a significant amount of money in there, there's obviously been issues, both technical, cost, and schedule. Second, with the current designs, I worry that we're going to have 2 separate launch developments, 2 large development programs, and then the operations costs that are going to be required to sustain both. In today's economic climate, I'm not sure that that's the best strategic decision we can make. What I believe we need to do is leverage the launch vehicle from as much of the existing hardware as possible to do the job required, while private enterprise is off developing its own capabilities. This allows for the development costs to be minimized and operations costs to be forecasted much more accurately and with higher confidence. We heard today both about the Jupiter, the National Launch System derived vehicle, and both the side-mounted vehicle that John just talked about. This class of vehicle has been
called... Could I ask you to wrap up?
Certainly.
Comments, please?
This class of vehicle has sometimes been called overkill for ISS. But it is exactly that vehicle that we are flying today to construct and build the space station. And I would like to see that gain serious consideration by this program and by this commission. Finally, the only thing I have to say then is that, like I said, I was born after Apollo. I sincerely want and hope to see us go beyond low Earth orbit. I would like to be able to do that and have that as part of my career. I sincerely hope that my 2 little girls, who are very small, don't grow up in a world where they have to too look to the history books to see what we were used to be able to, what we were at one time capable of doing. I know you all have a great job to do and a very tough job to do, and appreciate the opportunity to talk to you. And whatever decisions you make, hopefully they're good ones. Thank you.
Thank you very much. Sir.
Hi, I'm Randy Simpson. I'm a taxpayer and an IBMer. I just want to recall, I know you know this, and other people have said it, just the importance of this review. And to think back, because this isn't the first one you've done, think back in 1990 when you did a similar review like this, and maybe, and I'm sure you've done this and gone through your head, but I think it would be good for you and for the panel to think about it maybe out loud, to think about what was the environment back in 1990, technology, from a technology perspective, from a political perspective, and think about the process that you went through, the decisions that you made, and how it impacted the next 20 years. And in looking at that, take those lessons learned and think to yourself what the decisions you're going to make now are going to do for the next 20 years. So just think about it from a visionary standpoint. And in the process of doing that, remember that there are a lot of little eyes that are looking at you. You know, what they want to know what the next 20 years are going to be like. There was a discussion about our youth. I've got a herd of youth at home in my family. They're watching you. They're watching NASA. They're watching me. They're wanting me to be excited about NASA, which I am, and for them to be able to move into the space business. We need to do something that's going to, in your recommendations, energize the current workforce and the workforce that's coming in later. This is an amazing place that we're in. We're surrounded by Psalm 19 all around the wall. We're under Elihu Root. I don't know if you know who that is, but you ought to look it up. It's amazing. And you've got a big job, and I hope you do it well.
We'll certainly do our best. Thank you. Sir.
Good afternoon, Mr. Chairman and panel. My name is David Turner. I'm from right here in Washington, D.C. Like many people, I was very excited 5 years ago in 2004 when President Bush announced the VSE. I was very excited about that, and here we are in 2009, 5 years later, and where are we? Well, this morning we saw the Constellation video, which was very impressive and would indicate that everything is fine. We're progressing along. Yet, I feel that if things were fine, we wouldn't be here today having this meeting. We've seen a lot of excellent presentations this afternoon, and over the past few years, as I've been following this as a concerned citizen, it seems that we're only going to, well, because of the economic issues, we're more than likely only going to get one rocket system that Congress and the White House will support. I've gotten more concerned that if Ares 1 is selected, that we're going to end up only with that Ares 5 won't reach the funding point when it's time for its development. I'm a child of Apollo, and I was a young teen when the moon was taken away from us in the early 70s. And speaking for my generation, I'm still young. I want the moon back. I'd like to have it back. And I'm afraid that if we only have Ares 1, we won't get the moon again for decades. So it seems to me that whatever rocket we select needs to have the most functionality, the most flexibility to grow. And Ares 1 isn't designed to do that. So I hope that the rocket system that you all choose has that in mind, that it's whatever it can do today, it also has flexibility for growth in the future to ensure that we do get the moon. Thank you.
Thank you very much. Thank you. Sir.
Yes. My name is Earl Lake. I'm probably one of the only average citizens in here. I don't have a dog in this fight. You know, I don't care how we launch, as long as it's done safely. You know, I took off work to come down here to show you and to show everyone that there are average citizens out there that look to NASA as inspiration still, and has been for the past 50 years. So really, actually, when I look back at it, I find that the space station, when it was first proposed, you know, I was a young father, had a small one-year-old daughter. Now, as it's coming to fruition, I'm a grandfather. What I'm really hoping for is that Orion can come along before I become a great-grandfather.
Or worse.
Or worse. So what I'm hoping for is Constellation really has to be capable, it has to be safe, and it has to be soon, or else you're going to lose another generation of children and that just do not know the excitement of space exploration. I mean, Dr. Cho's been to the space station, I believe. It's exciting for that person in that position. For the rest of us except for people like me, not so much. But, you know, we need to inspire our youth. So basically, I think what really should come out of this commission is the fact that whatever we decide to take, it has to be supported by Congress for a long term, and it has to be properly funded. It just, if the figures come out and we need this amount of money to get it done in this amount of time, it has to be allocated. We can't go along thinking, oh, we'll make it up later, because we never do. So that's what I'm hoping that you can do for us.
Well, thank you very much for those comments. And each of you who've made public comments certainly inspire us with the importance of what we've been tasked to do. I assure you we're all committed to do our very best. As you can see, this is not an easy task. And as I've visited on Capitol Hill quite a bit, I've discovered there are a lot of different views there too, all strongly held, mostly contradictory. So we're aware of what we're into, and we're aware of the importance of it, and we will do our best. Let me thank all of you in the audience who've stuck with us to the bitter end here today. Appreciate your interest. I want to thank the people at NASA on behalf of my colleagues, the people at NASA who made the briefings, and people who provided the logistics of pulling this all together today. It was, I think, a very worthwhile day from our standpoint. Let me just ask if any of my colleagues would like to have the last word here. Jeff, do you want to, or Bo, or?
Oh, also, I can't resist the temptation to say something.
Please.
But so as to be non-controversial, it was something I've said on the public record before. You know, and I'm reminded of it because of the comments I got here in the public meeting. You know, I stood up at an occasion much like this when I was on that side of the microphone, and I told the story that, you know, I've had that moment that we used to say about laughingly when my little boy came to me and said, "Daddy, did they really used to go to the moon when you were a boy?" And you know, I am only one of us, and we have a really hard job to do. And at the end of the day, we make recommendations, and other people have their hard job to do. But if I can, I'm going to make sure that that when they grow up, their kids don't have to ask that.
Bo, do you want to add anything?
I only have just one thought. You know, this gentleman who took off work came to talk to us, what resonated with me when he said, soon. You know, this was like the most powerful word I almost heard today. We had a lot of briefings, a lot of fancy stuff, a lot of clever stuff, smart stuff, and there is a good citizen who takes up work, he says, guys, do something soon. And I think this is one area that we have fallen behind in this country. I've been in this industry longer than my memory serves me to remember, but we have slowed down in the way we do things. We do well things, we do with little resources, we somehow have forgotten or maybe never learned, or we didn't think it was important to do things soon. And I appreciate what you have said. We will try to see if we can maybe advise somebody to do things soon. Thank you.
Leroy?
Well, thanks, Norm. I'd just like to say what a great honor it is for me to serve on this commission, and like my fellow committee members, I take my responsibilities very seriously and intend to do the best job I can to help move the process forward. It really touches me to see all the folks that came out, people who took time off their jobs, people who made a special trip out to D.C. to participate in the meeting today and stayed all day. Really, I'm also impressed with people who've come out and made bold presentations and statements, and you know, it just shows that people do care about space in this country, and I think this commission will play an important role in ensuring that this country continues to be a leader in human spaceflight. So thank you all for coming.
The task we have before us is, I think, pretty important, and I think I want to assure all of you listening today that we really understand that deeply. The previous NASA administrator said on a number of occasions that the main task of his administration was to get the first launch vehicle rolling and get the first spacecraft rolling, and basically the rest of the program was budget ahead of us and payload on top. And that it would in fact be the responsibility of the next, now current administration to really decide where we were going to go beyond low Earth orbit and how we were going to get there, other than with the launch systems and first spacecraft. And I think that we're at a time and place in history where the recommendations of this panel, as we heard from the elected representative of the people this morning, will really be listened to, and we take that responsibility with great seriousness. Someone referenced previous studies. Norm has chaired these studies before. Sally was on both of the accident investigation boards, Columbia and Challenger. I happen to be on the 16 years ago on the space station study that was begun in the first year of the Clinton administration, called the VEST report. And one of the outcomes of that report was the decision to move the space station to 51.5 degrees orbital inclination and invite the Russians to participate. On the day when Columbia was tragically lost, I had one warm feeling in my heart that the astronauts who were then on orbit would not be because of the recommendation of that committee. So these committees do, in fact, sometimes change history, and I think we're in a position to do that at this time.
Thank you, Ed. Chris?
Thank you. First, I'd like to thank the chairman and my co-panelists and the presenters today, but above all, the members of the public who gave us their views. Our responsibility as a committee, Mr. Chairman, I believe, is to look at a set of options and present, look at a very wide set of options and present a somewhat winnowed down set of options to the White House and NASA, also to Congress and to the public. I think it's important for us to look across a very wide number of options and to be very clear what the choices are. What the choices are with respect to the goals. Those options may have different goals that imply different destinations. What the choices mean for national infrastructures and capabilities. What the choices mean for the time scale, how soon we will be doing different things, and what the realistic budget requirements for those different options are. And ultimately, the choice is not going to be made by this group, of course. It's going to be made by an elaborate dance between the executive and legislative branches and ultimately the American public. Our job, I think, is to queue up the options as clearly as we can so that the people, through their representatives, can choose.
Well, thank you. I guess I would just observe that my small grandchildren, the two things that I think excite them the most are space and dinosaurs, and we're very short on dinosaurs. So thank you very much. Good job. That's what we have to do.